Welcome to Cloud Applications class. This is the first of two, and we're going to get you programming, and in the second class you're going to be running more sort of data applications on top of the cloud to see how it all works. In this introduction, what I want you to do is to get a feel for how a cloud is built and how it's organized. In other MOOCs, like Indy's MOOC, you will have heard about all the algorithms that go into building a cloud. But now this course is dealing with how is the cloud structured? How have they organized the cloud to be so effective? What we're going to look at in the next sections are all of the mechanisms used to build those clouds. We split it up. There's separate sections. I've got some introductions for you for those individual pieces, and you can skip ahead and listen to those. Then we've got the real materials for those particular sections with lots of details. We're going to have exercises, quizzes, and even some exercises where you will be able to see what we're talking about with the cloud by doing some helped programming. We're going to give you lots of help to do this, but you'll be able to step through and actually see how all of these things fit together. So at the end, I want you to feel that you understand where we're going with the cloud, how we build them, why they're not frightening things, how you can actually sort of take the cloud infrastructure to heart and actually use it to build your businesses, use it to get the programming, to get the data that you want to get out of the cloud. And the whole course comes together at the end. And I hope with giving you lots of confidence to face the next course where we will be talking about using the cloud to do data structures and big data of all sorts. So take your time, go through the materials carefully, look at all of the terminology, and feel free to go back and forwards through the notes because they build on each other. As you understand one concept, it'll very often help you understand all the others. Thank you. Let's just sort of review first what you know about clouds, and perhaps we can compare experiences. Pretty much everybody nowadays uses a cloud sooner or later, probably multiple times a day. And you do it without thinking. You use the search algorithms, you're using storage, you're using news, notifications, you're probably members of LinkedIn and sort of using that as a knowledge base. How did this revolution in the way we think and provide computing to people come about? So in our introduction, we're going to briefly mention what is driving the move towards a cloud. You see that pretty much all of the industries are now focused on building out their cloud infrastructure and providing services. And the government is similarly following through that pattern, seeing how it can introduce people to digital government by putting the government on the cloud. Same thing all the way through different services, different applications, tremendous changes. So Cloudonomics, as it's said, will introduce you, this is the next set of lectures, will introduce you to what is driving that. And it's really sort of because you only use computing occasionally, but then when you do want to use it, you want to use lots of powerful operators, lots of data. That spikiness of the cloud allows you to share the cloud infrastructure between tens of thousands, maybe millions of people. And one of the big benefits, as we could keep coming back to, is you're just paying a small amount for a cloud, but it's a huge benefit to you, and that system is being shared amongst all sorts of people, but you think really the cloud is working for you. And what it does is to take the load off your workstation, allows you to use your mobile, it allows you all the freedom, all of, if you like, the democracy of being able to see what the data is out there, accessing everything in order to make your own decisions. So Cloudonomics is really all about how you benefit from having that shared environment. In fact, there are books that describe going back with to the times of electricity and when electricity moved out of just a single generator per house to electric power being provided over the grid. What a radical change that was in the way we used electricity. Similarly, I think you're going to find that cloud computing makes that same statement for computing. All of a sudden we're sharing, all of a sudden the costs are divided, everybody can get access to that compute facility. And what it's enabling is a different sort of economy. And this is where I think as we get into the second course, we'll be talking about this more, but just touching up in our big data section, what you're going to see here is we are going to be addressing large amounts of data, doing analytics, providing it very easily in very suitable forms for you to read, to use, to manage. Now, the key thing is how do you as computer professionals use this cloud to do data analytics? We will be mentioning this in the first part and going over how the cloud is built, but in the second part, we will start emphasizing exactly how you can look at data analytics, how you can build your own data analytics from a cloud using all of the tools that have developed. So that really sort of introduces why I think cloud computing is exciting. It's a revolution, it's a change in the way we do computing. Now, in order to provide that revolution to everyone, we are actually looking at changing our organization of computing. Instead of thinking it perhaps of hardware that's you have to carry around, you put in your laptop or you put in your briefcase and move about, what we're going to be thinking about is designing very, very large systems in a way that give you a very modular design, very easy to change, very easy to access, easy to construct businesses on top of information services. This is called software-defined architecture, and it's really the key driver for cloud development. What we're looking at now is what are the interfaces? How do you make RESTful interfaces, HTTP, whatever interfaces that are easy to use, straightforward, that can be included in your programs easily, that you can generate all sorts of applications. This approach, pioneered by companies like Amazon, IBM, Microsoft, what it does is to open up the world, democratizes the world, allows people to access information, build businesses with little overhead, establishing just a completely different way of doing industrialization, commerce, entrepreneurship, and also allowing the citizen access to all that information. As computer professionals, you will want to know what is underlying software-defined architecture. What does it mean to have a RESTful interface? What does it mean to have these layers? What does it mean to have virtualization? So software-defined architecture introduces you to these concepts, and then we move on from there to the type of cloud services we can build on top of software-defined architecture. So next, we'll be moving on to talk about, well, infrastructure as a service, and this is a real sort of late development, you might say, but a very fine point to understand. Once you think of computing as a service, you can think of providing CPUs, disk stores, networks, security, huge number of different basic elements as a service. Now, you're not buying them, you're renting use of them. You can use your own data, you can rent data to use them. All this is coming together. It's almost like sort of a complete sort of mixing of all that we know about computing into a set of services from which you can build pretty much anything. Now, infrastructure as a service is building from basically operating systems and perhaps even lower, perhaps even down to the metal, and building those systems from there upwards. There are other layers, and those we will deal with in the next section after infrastructure as a service. Welcome to the very first lesson of the Cloud Application class. We're going to start off talking about cloud computing, a motivation for it, and then describe a little bit of what you're going to see later on in the rest of the course. We're very excited to be giving this to you, to be frank. This has taken us a while to put together. It's gathered from lots of different sources, and what we've tried to do is to condense it for you and to make it much more personalized to your own career goals. So we're excited because this has real impact in the world. This is going to change the world. And we're excited for you. We would like you to join in this revolution, this change. We would like you to be in control, to have mastery of this new area. And I think by the end of the lecture, by the end of the series, you are going to have some skills that will really set you apart and allow you to participate in what is happening in the computer industry right now. So, tremendous buzz. Let's look at what people are saying about cloud computing or have said. So the first is Nicholas Carr. He's written a book, a very important book about cloud computing, and sort of epitomizes what's going on by saying, you know, revolution. It's the biggest upheaval since the invention of the PC back in the 1970s. IT departments will have little to do once the bulk of business computing shifts to the cloud. This is a real dramatic statement, and we'll try and give you some ideas about why Nicholas Carr actually said that. If you go over to the money side of the world, cloud computing also has lots of impact, and Money Control has written domestic cloud computing is estimated to grow at 53%. Now what we see is that growth has mainly happened, that what we're reaching now is a different level of performance in terms of growth, but it is enormous and it has affected industry. So let's move on to the first slide. And what I want to talk to you about really is, if you have computing, why would you go and consider cloud computing? So there's a number of arguments you can make, and those arguments really evolve around economics and costs, ease of use. If you own your own information systems, well, you've got control of everything. You can set your own agendas. You can do whatever you want on those machines. But you have to pay for them. There's a capital investment. As soon as you pay that capital, you are paying our interest payments, right? So if you're doing a startup, that capital investment is big and looks bad for you. There are heavy fixed costs. You have to have somehow building, you have to have air conditioning, you have to have power, you have to have staff to run it. So those heavy fixed costs you've got to consider in your equation for your business. There's redundant expenditures. You are going to have to pay for people to work on this. You're going to have to pay for programmers. You're going to have lots of overlapping duties because you'll have to have more than one person doing each of these things for redundancy. You're going to have backups. All of those costs will affect your business. Next, energy cost. Everybody talks nowadays about the high price of energy and carbon neutral and trying to be sustainable. Well, energy cost for cloud is high. You don't get that much CPU utilization for the amount of energy you're putting in. Reason, you want computing to be ubiquitous, you want it to be easy to use, there when you need it, but you're not going to be using it 100%, and so it is more expensive. Then dealing with unreliable hardware. We're going to be talking about scaling things up, making things big, taking lots and lots of computing, putting it on machines, lots of data and spreading it across lots of machines. We're going to be using COTS, custom, well, consumer off-the-shelf type of hardware because it's cheaper. But if you have 10,000 PCs, well, they might work, one PC might work very well in your house, but 10,000 PCs, they have, say, a failure rate one out of every, well, once or twice every year. When you put 10,000 together in one room, you're going to see lots of those machines die every hour. So unreliable hardware means you're going to have to be chasing around doing lots of maintenance. Last, you have lots of capacity. What are you going to use it for? When you're not using it, it's just going to sit there idle, warming up your site. Right? There's technology, labor going into this. All of that is a constant, but your use of the computing is variable. So bottom line on this, if you are a corporate and you're using your own computing facilities, it really isn't sustainable in the modern age. So let's go back a bit. We'll go back to 1961. Cloud computing has been predicted. It's been predicted by many people. One of the most famous people is John McCarthy, inventor of Lisp, which was an early programming language. What he said was, computing is someday going to be organized as a public utility, just as the telephone system is organized as a public utility back in, obviously back in 61. Nowadays it's sort of morphed into cellular. So we would like to build our future and incorporate this notion of utility computing, and the cloud is the first step to that. So what is a cloud? This diagram is produced from a description by NIST of what cloud computing is. And what I'm going to do is to describe all the various parts of it and give you some examples. So first of all, the cloud is out there, anybody can use it from anywhere, so availability is good and accessibility is good. It really becomes a ubiquitous computing environment. It's convenient, 24/7. You don't have to turn it off, turn it back on, whatever. It's always running for you. And because of all of the input from all of the industries into cloud computing, it's becoming very convenient to use. You want to use it? Well, you've got on-demand access. Now, supposing you've got clients, you've got, let's say 100 clients, you're a startup. Instant access, they can use it. Now, what about 10,000 clients? What about 1 million clients? It's the same story. You have on-demand across the network to that cloud to deliver the services that your company produces. It can be rapidly provisioned. You want to start up a website, you want to start a database, you can sit down at a console mapped into that cloud computing and create one of these applications in 10 minutes, half an hour, have it up and running, decide what size it should be, scale it up if you've got it wrong. That's what's meant by rapid provisioning. So your IT business, the business you are selling to the public, can be rapidly released with minimal management, lots of convenient software to configure it and so on. And it can give you service provider interaction with sort of communicating with those services, getting those services linked in to all of the different other subsystems you have. All of that is facilitated in this cloud. So let's look inside the cloud. You have various pieces. You have a network. Typically, you're going to have a data center switch and then top of rack switches, and then Ethernet to all of the different computers in the cloud. You're going to have servers, and they're going to be connected by Ethernet. They're going to be where you do all your work. They're probably multi-processors, and they probably have lots of memory. You have storage. That storage is shared between all of those machines. It's optimized to give you best bandwidth from a server to the storage. We won't discuss that now. We will come back to that and revisit it. But that sort of network itself has to be managed and maintained better for the customer just to delegate that to the cloud producer. Then you have the set of services you wanted to provide. And we're going to talk about stacked services. There's not just one service. There's a whole set of layers of service that are really crucial to building the type of enterprise you want to have your public view. Then on the side of that, we have all of the applications. And the applications can radically be different. So we can talk about web services. So if you want a website to deliver 10,000 pages a second or whatever, you can build your app. So it's on multiple machines, but it's one web engine. And when requests come into that cloud, they're going to get load balanced across all the servers, and those servers are all going to be coordinated to give you that web presence. So that's one part. You could have search, and of course, pretty much everybody's familiar with search. You issue a request, the search engine goes away, looks at all of its stored data, and comes back with the top 10,000, 20,000 recommendations. Search is really powerful. It's really very, very fast. What's happening is you get the request coming in from outside. It's fed to an appropriate server. That server looks at the request, decides how it's going to execute. Maybe it decides it should be a distributed query and gets multiple servers to work with it. They will look at the databases, all the files, produce all the results, and then the particular server you contacted will return your results. All of that under the cover, very easy to use for the customer, very easy to use for the search provider. Other applications are email. Email nowadays is done in the same way. Google Mail, for example, is typical, where you can serve huge numbers, millions of people, email off a cloud, and you can have very good facilities like spam removal and so on, because it's all centralized, it can all be managed. Facebook, we can build social networks. We can have interaction between people. We can have pictures, videos, all sorts of things, because we've centralized all those facilities and we share them. So Office has always been Microsoft's power in the way it produces computers and the software for computers. Well, they've produced Office 365. So you can have your Office on the cloud now instead of at home. So any device, mobile or otherwise, can access your own Office, use your Office. So if you have a small company and you're sharing documents, Office 365 makes it a real necessity. Google Docs, similar sort of offering. Other applications allows you to do all sorts of similar things to Office, but now it's a separate entity, but it's organized the same way. So backing off a second, let's just step back. What we're doing is something really novel. We're discussing a really novel issue. Cloud computing is providing all of those facilities. It's providing it very, very conveniently, very economically, and it's simple for the enterprise to use, it's simple for the customer to use, and that is the attraction of cloud computing. So let's talk about the excitement that cloud computing has created. Gartner has a hype cycle, which is a good way of representing excitement from the community. And what you see in this diagram is steady growth from the invention of cloud computing to a maximum, and then it's going to drop as people realize what it's good for and what it isn't good for, and then it climbs back up as people build on all of the successes of cloud and actually make it a viable enterprise type of enhancing product. We start off and we move forward to a peak of inflated expectations. This occurred about 2011 when Carr was writing his book. From there, there's only down, you might say. What people discovered was there's privacy, there's security problems, there's just the problems of being able to interact with lots of software. What you see happen is a drop in discussions, in excitement about cloud computing. And about 2014, we sort of reached the bottom of that trough. It was still pretty high discussion rate, but people realized there are limitations, we need to fix those, and we also need to move the cloud, the things that are working well, into massive production. And that's what you see on this diagram beginning to happen. You notice that the slope is up. If we move to this year, what you see is we move to the bottom and we start rising. And now pretty much everybody's accepted that if they're going to have an enterprise IT, they're going to put it on a cloud. Now, it doesn't stop there. If we look forward into the future and start looking at our tea leaves and making predictions, we see that actually companies are making plans to move heavily into the cloud industry. This is really where people have understood what cloud computing means to the world. What I want to talk to you now about is how the services of the cloud get delivered to the customer. And there's basically three different ways, three different models for delivery. Let's look at infrastructure as a service. There, what we're doing is to provide computer hardware in terms of processors, disks, network. We're allowing people to use those services, to rent them. We're providing a infrastructure as a service that you can go to. You can declare how many computers you want, what are the hardware facilities you want. Then it's up to you to put your own software on top of that system, even your own operating system on top of that system, and you just provide your customers with all that software, but you've rented the hardware. The next level is platform as a service, PaaS. Here what you're doing is deploying customer-created applications. So the applications are running on what you're providing in terms of operating system and hardware as a cloud provider. So App Engine is an example. Google provides App Engine. You write your application with App Engine, and all of a sudden you can run from 1 to however many, 200,000, 600,000 machines on Google. Then we have software as a service. Here what we're using is the user's applications. We're providing the user applications over a network, and they would just interact with those applications. So for example, if you're doing email, if you're doing Office 365, there are companies out there that are making huge amounts of money out of providing services to customers. And one of them is Salesforce. What Salesforce does, it provides customer relationship management software, amongst others. It tailors that. It has a whole suite of software that allow customers to pick and choose particular forms of CRM or whatever, and allows them to use that for their businesses. We talked about synergy. One of the bigger issues that I want to get across is that we're just not on the entry level of clouds, or even, just on this rise of enlightenment. There is a lot of things happening that really make cloud computing very exciting. This synergy is best looked at just what sort of interests over time have happened. What are the news events? What are the discussion points? Now, we talked about big data and virtualization. If I plot those in time, you'll see how they're interacting. The first is that we have a virtualization effort just here, rising up and creating all sorts of potential possibilities. Then what we see is cloud computing overtaking that, using it to build an infrastructure. We've talked about the different ways that can be delivered, and that has been huge impact. Now what we're seeing is a rise in big data, and big data is exploiting the cloud computing to provide information for everyone. Anyone can do analytics essentially on massive amounts of data. That is provoking a huge amount of change. So, big data, where will it take us? Well, it's another revolution. It's built on clouds. The data collection's too large to transmit economically over the internet. You're talking about petabytes of collections. The computation is data intensive, lots of disk, networks, and CPUs. The overhead of maintaining the cyber infrastructure for that is very expensive, but why not share it amongst the community? So, for example, Google Maps is a huge infrastructure investment, but it allows all sorts of businesses. You're going to see smart cities building on some of those infrastructures, on some of the data collected for smart cities. Users buy big data services from clouds and they share the overhead. So they're sharing out the cost of putting all that big data together. The essential part to all of this is here. This big data is going to be easy to use. It's going to be easy to write programs for. It's going to provide you fast turnaround so you know what the economy is doing, what the stock market is doing. How do you do that? You make programming very easy so that programmers can easily deliver those values to the community. How do they do that? We will be talking about some developments on cloud computing that allow this to occur. They are MapReduce. There's several other topics that we'll come across, but MapReduce is the main one. We will talk about real-time processing in real time. But let's first just deal with MapReduce. What's caused that to happen? Why has MapReduce suddenly become the focus of lots and lots of big data computations? Well, part of it's because the applications are there. The applications that implement MapReduce, like Hadoop, the applications that allow you to take one MapReduce operation and combine it with multiple others, like Pig, The MapReduce operations operate on the big data, but the big data has to come from somewhere. It has to come from storage. So you're talking about storage systems. HDFS is a distributed file store, which is reliable, redundant, fault tolerant, and distributed. And we'll be talking about HDFS. You can use it with databases, and HBase is an example of that, distributed over multiple machines, so you can make queries over huge numbers of machines. So today, we've sort of introduced you to the world of big data in our lecture. What drives cloud adoption? Why clouds make economic sense? How clouds support the big data revolution? Who benefits from clouds? Our course is now going to go off and look at some of these questions in more detail. We're going to start by looking at the economics. Just why do clouds rise as sort of imperative for enterprises to use in this sort of current day? So on to the economics of clouds.
So I've been at Yahoo for about 3 years. I'm currently a Senior Director of Product Management for the Cloud and Big Data Platforms. So pleasure speaking with you here. When you think about cloud at Yahoo, or perhaps any other consumer internet company that operates at web scale or the scale we operate at, obviously one of the first things you would think about is scale. And some of the other things that come to mind, if you ask us or the people across Yahoo, it would be service, would be an attribute that would come to people. Service level agreement, SLA or latency is another thing that would come to mind, and then performance. So these are the types of attributes that people would associate to cloud computing, right? Ease of use of consuming technology, expectations around services. Those are the types of things that would come to people's mind or our developers' mind because it's a private cloud. Our services are for internal consumption to Yahoos and Yahoo developers. So the products and applications that we host or the platform services that we provide to our developers are for our developers, in our applications. So Yahoo Mail, some of our mobile applications, search, and all kinds of other things we do, or the businesses we operate in, is what our cloud is supposed to serve or expected to serve. We don't offer retail services to, let's say, consumers outside of Yahoo or our publishers or anybody else. So that's what I mean by private cloud. It's really, in my mind, the stacks and the technologies that we put together are more or less the same as, let's say, a leading public cloud. But the primary difference here is what we focus on versus what they focus on. And the second is that it's not a retail service in any sense. The IP space is private. Not just Hadoop, but if you think about the big data space, we have all kinds of other services now that either run on the same Hadoop infrastructure like Swarm or Spark. We have introduced those years ago, at least a couple of years ago, when it came to Storm, and now have some of the largest clusters for streaming technologies and other things. So it's not just Hadoop anymore, and that's why I like to call it now Hadoop and Big Data Platforms as our group. And then when you come to more traditional cloud services, which are beyond big data, particularly on the serving side, a lot of it is infrastructure services. So we orchestrate that through OpenStack. We're a Gold Foundation member of the OpenStack consortium. I talk about storage services, both structured and unstructured services. We also talk about hosted search service, dynamic serving, something that we're pretty proud of or is really essential to a consumer web company is the serving stack. So we have orchestrated the full serving stack through our cloud services. We have a set of shared services like messaging across applications, across data centers, hosted messaging services, monitoring services. So a lot and complete edge services like suite of video hosting service, dynamic streaming. We have our own CDN. We have our own cloud proxy infrastructure. So it's a full suite of service. Just as you may look at, let's say, something else which is more transparent to people outside, like Amazon Web Services, and if you look at their suite of services, our suite of services look exactly the same. So we live and die distributed computing. And we're the ones who are building, let's say, the Hadoops, the Hive, the HBase, and things like those for our company, right? As well as contributing to the open source community across all of these technologies. So for us, it's extremely important. But for a user of HBase, for a user of Hadoop, it may or may not be equally important. For them, I guess what's more important to know is the capabilities of these platforms, rather than what underlying algorithm does the storage technology is based off of. So I'll give you a good example. We have a storage system called Sherpa. Sherpa is based off of a work that was done out of Yahoo Labs a long time ago, and it was one of the largest NoSQL installs anywhere in the world at that time. It's called Peanuts. Now Sherpa also uses some of the LSM technologies, and LSM's common across, let's say, Sherpa and HBase. Now, does a person outside of our platforms organization need to know about these things? I'm not quite sure. What they ought to be worried about is like, what's my read latency, what's my write latency, what's my read throughput, what's my write throughput if I'm using this storage system versus that storage system. Is this optimal for my use case? Is that optimal for my use case? And I think we help our customers a lot in making those decisions. But at the same time, I think customers ought to be smart enough to disseminate the nuances between a million different DBs and NoSQL stacks out there. Yeah, I think we have a philosophy. I mean, we both contribute heavily to the open source technologies. We have open sourced a lot of our own technologies for the benefit of the community, Hadoop being one that we open sourced in 2009, which is probably one of the most successful, I would say, stories that Yahoo has as far as open source is concerned. ATS is another one, Apache Traffic Server, which was earlier Inktomi Traffic Server, later became. And that's widely used across companies that operate in the cloud computing space. We're doing a lot of work in open source as well on technologies that were not developed at Yahoo. So I'll give you an example, like Storm, like Spark, like HBase, like Hive. A lot of these were not invented at Yahoo, right? So we brought them from outside, and we contribute a lot to those as well. We have done pretty, I would say, important work when it comes to HBase in terms of developing multi-tenancy and security, and types of things that Yahoo needs, types of things that our customers need from the platform. We've gone ahead and built those in these open source technologies that were brought from outside, and in the process of, or have already contributed a lot of that back to the community. So I think the philosophy really is about what's useful for Yahoo. Be it the decision of open sourcing something that we have developed, or bringing something from outside and contributing to it. And it works both ways. But really the essential idea behind making that decision is to how it's going to benefit Yahoo. And then how it's going to benefit the community, and what would be the impact to Yahoo as well as the technology landscape in a longer term. The question can be answered, again, as I said earlier to you, in two different sort of realms. The enterprises think about cloud in somewhat different way, particularly in the industry, as we, the web scale cloud consumer internet companies, think about cloud. And I think if you ask those people, like the enterprise-centric people about cloud, they would talk about the debate between public and private cloud and how everything is evolving as a hybrid model where workloads can seamlessly transfer on and off premise. They would talk about things like multi-cloud and private and members cloud and all kinds of other notions around how the cloud services, the public cloud services, will be consumed by the enterprises, the security models and things like that. And I think the general consensus is this hybrid model is how it's going to evolve into. But again, a very services-centric view, not a technology-centric view. As far as technology itself is concerned, obviously a company that operates in that space will promote its own technology and agenda, a long-term view of how things are going to evolve. Some would say it's all going to be open or based on OpenStack or based on something else. Somebody will have some other notion. But as far as Yahoo is concerned and where things are headed, I think we will continue to focus on things that we're focused on today. In my opinion, that battle will never cease. And I think one of the primary battles we have in this space is around latency. Everything we do within the data center all the way to the end customer, really reducing that serving time from when the request was made to when the response was served, is something we're going to continue to focus on across our stack, across our services. I don't think that'll ever go away, or that focus will ever go away. This notion of instantaneous response, you click something and you have the answer, that'll never go away. So our technologies, our services will continue to focus on that. We will continue to refine our SLAs that we make with our customers around throughput, around latencies, and they are going to stay as our focus. I also think that from a technology standpoint, there is a blurring of boundaries between the backstage infrastructure platform as well as the serving infrastructure platform, and they are now sort of converging, right? So Hadoop was sort of our asynchronous processing platform. We had a bunch of proprietary technologies in the serving stack. And as you can see, a lot of these are now merging, right? People are demanding real-time responses from Hadoop-type infrastructure, as well as people are expecting more and more, deep edge capabilities, deep analytics capabilities right at the edge with the advent of Internet of Things, and that's not quite possible given the size and the processing power of these edge devices. So I think there is a lot of blurring of this boundary between asynchronous processing and serving infrastructure, and I think technologies will evolve in both of these spaces that will try to do more of both. So integrating analytics on the edge where you can't send everything back to the data center and expect real-time response back to the edge. Those types of things will not happen. So you will develop newer types of capabilities. As I said, our cloud covers everything from the edge back to the data center. So there will be a lot of invention, a lot of, I would say, evolution of technologies that we use today, both in our video infrastructure and CDN, object CDN infrastructure will evolve a lot to take care of things like the evolution of Internet of Things and other things, and as we as consumer internet company latches onto some of those, so it's 5 to 10 years is definitely going to be extremely exciting. That is all I can say. This space has myriads of possibilities where things will head. But one thing I can say with confidence is that it will be extremely interesting. Absolutely, and not just again Yahoo. I would say it's the platforms, the cloud platforms, the foundation of any consumer web company. I mean, not just for Yahoo. In many cases, platforms and technologies become competitive advantage. And so the usage of cloud, the importance of cloud, the importance of platforms have not gone down. It's only becoming more and more important as we try to bring more, I would say, innovative user experiences, mobile experiences out in their market at a quicker pace. The role of platform only I would say increases. So it actually helps us get things out in the market faster. And that's exactly what we're focused on right now in terms of delivering new and interesting user experiences that, as we call as, will become the daily habits of people. And the importance of cloud, the importance of platform, it has really, really increased. It has not gone down. So for me, the whole platform space, the cloud, the big data space was very interesting. So when I was making the transition into Yahoo, that was the space I wanted to get into. So I was somewhat domain-centric, less company-focused. And I got all of that. I got to do all of that. I got to work in cloud. I got to work at scale. That is unbelievable. We have, give or take how you define the users, 800 to 1 billion unique users, and that drives a lot of interesting scale challenges on the technology side, on the platform side. You get to see all of that. The other interesting thing I find, which keeps me extremely happy here, is this idea of, so when it comes to big data, Hadoop, I mean, this was the birthplace of Hadoop, right? So you have a very strong development team that has, let's say, more than 50% of its members as committers or PMCs in leadership roles in the open source community. So they control a lot of, what happens in the open source community. So it's always interesting to work with them on the development side. And then we also have one of the world's largest footprints in the world when it comes to the infrastructure itself. And the services we offer to the rest of Yahoo. Pretty much the entire business runs on the platform. So you get to see both these sides at the same place, in the same job, which is pretty exciting. So that to me has been invaluable. I don't think I'm going to get that in a pure software distribution house or in a pure public cloud company. Over here, I think I get to see both all the engineering and development aspects of the technology as well as the services aspect when you deploy a lot of what we develop on one of the world's largest private cloud infrastructures. So no issues, no complaints.
Economics really is the foundation of cloud computing. Cloud computing revolution really started because people were considering the costs involved in providing computational facilities and whether there's a better way to manage all that data centers, computational infrastructure, networks, and everything. We first look at utility pricing, and later we will look at benefits of common infrastructure in a different video. This topic is based on a paper by Joe Weinman, Cloudonomics, and I suggest you take a look at that as well. There are more details in that paper and more benefits explained. We picked these two. So, looking at the value of utility pricing, we want to explain why you can have cloud services that are more expensive than owning your own infrastructure per hour or per day, whatever, and still be economical, right? Let's look at an example. Consider a car. You can buy or lease a car for, let's say, I don't know, $10 a day. Numbers that not important, but let's say $10 a day. And let's say if you want to rent a car for a day, it costs you $45 a day, right? So very obviously, renting a car is more expensive than owning a car per day. But let's say you go to a trip. Let's say you take 2 days and for a vacation and you go somewhere. You don't buy a car over there. You take an airplane trip, and then you rent a car for 2 days, because buying wouldn't make much sense over there. So it totally depends on the type of demand that you have to figure out if it's more economical to rent or buy car or services. So let's look at this in a little bit more detail. We try to model this using a simple mathematical model and figure out how everything is going to work out. So let's say you have demand. Demand is shown here by demand of T that denotes that it's demand per time. One day you might have a lot of computing demand. Another day your demand could go down. We are looking at this for a certain time period between 0 and time capital T. Let's say capital T is, I don't know, a whole year, 365 days. During this time, your demand goes up and down, right? So P is the peak demand. During one day throughout this 365 days, your maximum demand, we can denote by P. What else do we have? We can talk about the average demand. You take the mathematical mean of all the demand throughout the year. B would be the baseline cost of your computing unit. So for example, if a computer costs $10 a day, that would be your B here, right? So let me just write $10. Therefore, what is B of T? B of T would be the total cost of owning infrastructure throughout the year. And we will try to compute this value. What about cloud cost? Cloud unit cost is the cost of cloud resources, say again, per day. We want to compute what is the total cost of renting cloud computing resources throughout the year. Now, finally, we have the utility premium, which is defined as the ratio of cloud cost over baseline cost, right? So for example, if your cloud cost is $45 and baseline cost is $10, your utility premium would be 4.5. Okay? So our mission here is trying to find out the total baseline cost per year and total cloud cost per year, and then comparing them, right? So to find it, well, let's actually start from total baseline cost. This is easy. If your demand goes up and down, let's say this is your demand throughout the year and goes up and down, you need to provide the services to your customers every day. And you don't go and buy new machines every day, right? So since this is your peak demand, you need that many machines throughout the year. You need 200 machines. That means that throughout the year, you need all of 200 machines to be sitting there. And that's actually really the reason why we go through to the argument of cloud computing. But let's continue. So the total cost of owning would be the baseline cost multiplied by the time period, 365 days, multiplied by how many machines do you have? P, the total, the maximum number of machines that you need to answer your workload for peak demand. Now, what about cloud cost? For cloud cost, it's actually a little bit more detailed. You can very quickly get and release resources from the cloud provider as your demand goes up and down, right? So now we can actually do an integration, right? Integral of the cost of the cloud, that's actually U multiplied by B. Just look at here. Cloud cost is really U multiplied by B. And you do an integral over time throughout the year from first day to the last day. If you compute this, you get this value for the cloud cost. Okay, so now the question is, when is clouds going to be cheaper than owning? CT less than BT. If we substitute these values that we just computed in this argument, we want to find out when is A multiplied by U multiplied by B multiplied by T less than P multiplied by B multiplied by T. If you do the math, implies that clouds are cheaper than baseline when the utility premium is less than the ratio of peak demand to average demand. So if your workload is very highly various, it goes up and at some point goes down and goes up again and goes down, say here your average is a certain value and your peak is a certain value. If the ratio of peak to average is more than the utility premium that the cloud provider is asking, it becomes more economical to use cloud computing. So in real world, that was a simple mathematical model. What about in real world? So in real world, in practice, demands are often very spiky, which is good for cloud computing, right? You have news stories coming in, something happening, everybody's interested, goes to the news website, tries to find out, and then within a day or two, nobody cares anymore. The demand goes down. Marketing promotions. Manufacturer wants to sell their things. There's a 1 week, 2 week time period. Everybody wants to use a certain sale, and then the sale is done. Product launches, the same thing. Internet flash floods. Your article or blog somehow made it to Slashdot website. Everybody in the world comes and checks out your blog, and you need to resources to respond to that sort of demand. And then within a few days again, the demand goes down. Tax season, everybody has to file taxes within a certain time period throughout the year. The rest of the year, nobody goes to that website. So in reality, lots of demands are spiky. Now, often, a hybrid cloud computing model provides the best advantage. So going back to our car example, in your own town, you own a car, you use it for your daily commute, go around. Whenever you travel, you rent a car, right? So, or for example, when you need to move from one house to another house, you rent a van. You don't own a van all the time, even in your own hometown. So the key factor is really figuring out the ratio of your peak demand to the average demand that you have, and own part of your computing infrastructure yourself for your average demand, and be able to move on to cloud computing providers whenever there is a need to. Although, of course, I should mention here that it's not very simple, as I just implied. You should also consider the network costs, because if you're providing a hybrid model, you have to have a good network that connects your infrastructure to the cloud infrastructure. You need to provide interoperability between your own cloud and the public cloud, so that might cost a little bit. And of course, you need to consider reliability requirements, accessibility requirements that you have. So it's a little bit more detailed, but what we see today is that a lot of entities go towards hybrid cloud computing. So to summarize, utility pricing is good when demand varies over time, as is the case for startup companies, seasonal businesses, etc. When utility premium is less than the ratio of peak demand to average demand, cloud computing is beneficial and makes sense. In the next video, we will look at the possible savings on the other side for the cloud providers that they can create by using statistical multiplexing. That's putting different jobs from different customers together. We saw how utility pricing could help the cloud customer. Now let's look at how, by multiplexing demand, the cloud providers can gain some economic advantage. That's what we call benefits of common infrastructure. So there's value for aggregating demands for the cloud provider, right? Let's consider two different case studies. Case study 1. You build your infrastructure to be able to accept the peak demand in a period of time, say a year, right? For example, if your demand in one day of the year goes to 200 units, you have to build your infrastructure to support that. So let's say you have that. Now, what happens if you multiplex demand? This results in higher utilization of your resources, right? So if you've paid the money to build out those 200 computers throughout the year, you have to maintain them. Okay, now let's multiplex some other demand in the days that your infrastructure is not used to its maximum, and that increases the utilization of your computing resources, right? So that results in lower cost per delivered resource compared to unconsolidated workloads. Now let's look at another case study. Let's say your infrastructure was built to less than the peak, right? So in a very few days of the year where you had like the peak demand, your infrastructure could not handle it. You had to do cloud bursting, for example, move the rest of the demand to an outside provider. But okay, so you already have a certain amount of hardware resources available. If you multiplex demand, what happens? You reduce the unserved demand, right? So the amount of the portion of the demand that remains unserved goes down. That results in a lower loss of revenue. Or for example, if you have a service level agreement to provide a certain level of service, it reduces your violation payout. So let's actually look into this a little bit more detailed with a mathematical model. Here we introduce this notion of smoothness. We have this notion of C of V, coefficient of variation, which we define by dividing the value of standard deviation to the mean of the workloads. So if you have a bunch of workloads and you can model them as a random variable, the standard deviation of these workloads divided by the mean can result into C of V, right? Now, C of V, coefficient variation, is really a measure of smoothness. If you have this value as a small number, that means that the standard deviation, that means ups and downs compared to the mean, was small. Therefore, you really have something like that. That means that your workloads were smoother. And if we really want smoother workloads, you can either have larger mean or you can have smaller standard deviation or both. Both of these cases result in smoother aggregate demand. So the implications that we have for smoothness is that a fixed asset facility. So what do I mean by fixed asset facility? That means that you've bought a certain number of machines, resources, and they're not changing per minute or something, right? You have a data center, it's there. So a fixed asset facility like that, servicing a highly variable set of jobs, yields low utilization. And this is very logical, right? If your job goes up and down during the week, one day you need 200 resources, another day you need only 10 resources, and you had to buy 200 machines to handle those days that you have 200 demand. On other days, your infrastructure is utilized to a lower amount. Now, if you were somehow successful in creating a smooth set of jobs, right? So day one, you have 198. Day two, you have 185. They're all kind of around 200, 190. The utilization of your infrastructure goes higher. That's what you want, right? Multiplexing jobs with different distributions may reduce the coefficient of variation. So it depends on the type of jobs that you put together to run on a certain infrastructure to reduce the variation to make the set of jobs smoother. Let's look at a couple of case studies here too. Let's say you have n different jobs modeled as n different random variables. Let's say the standard variation is delta, mean is mu. And all of these random variables, let's say in this case, have the same standard variation and mean. Now, if you put these jobs all together, what happens to the mean of the aggregate and variance of the aggregate? So the mean of the aggregate, because they all have the same standard deviation and mean, becomes the sum of means. That's n mu. Variance becomes the sum of variances, again, because they all have the same variance. So you have n sigma 2. So the aggregate coefficient of variation, as we know, coefficient of variation is defined by standard deviation over mean. So standard deviation is the square root of variance. So you have square root of n multiplied by sigma over n mu. And you can simplify this to this expression, 1 over square root of n of the original C of v, right? So what does that mean? That means that adding n independent random variables, n independent jobs. They're independent, they just happen to have the same mean and random and distribution. Adding n of these jobs together reduces the coefficient of variance by 1 over square root of n. So, for example, aggregating 100 workloads of these types brings the penalty down to 10%, right? So this is good. Penalty of insufficient or excess resources grows smaller. Not as much as you would like. If you add 100 of them, you would reduce the penalty by 10% to 10%, not 100 times, 10 times. Still, it's good. Now, let's look at 2 other case studies here. Let's look at the best case. How can you best put different jobs, computing jobs, together to run a certain infrastructure? The best case happens when we call it negative correlation. What does negative correlation mean? I can model negative correlation by 2 random variables, x and 1 minus x, right? If you have these 2 random variables, when x is high, 1 minus x is low, and when 1 minus x is high, x is low, right? So in any case, the sum of these 2, again, hypothetical, right? Random variables is always 1, and if you have a random variable which is 1, its standard deviation is 0, therefore the coefficient of variance becomes 0, right? This would be, again, a hypothetical, doesn't happen in real world, but a optimally smoothed best CPU utilization, right? So you manage to put jobs from customer A that happens to always be low when jobs from customer B is high. Doesn't happen in real world. It would be great if it happened. You would get the best smoothness possible. What about the worst case? Worst case is what we call positive correlation. What do I mean? I mean that if job A peaks, job B also peaks, and job C also peaks. When none of job A doesn't have too much demand, job B also doesn't have too much demand. Job C also doesn't have too much demand, right? In this case, the mean becomes n multiplied by the original mu, standard deviation n multiplied by sigma, and the aggregate, if you do the computation, remains exactly the same, right? So if you put these jobs that are exactly similar, what do you get? Nothing changes. The smoothness exactly remains the same, which makes sense. So what do I get from theory? For the case of negative correlated jobs, right? So that's when you had like the best case possibility. If that could be possible, and this is a result from theory, if that could be possible, whether you have a private, mid-sized, or large-sized provider, all of them could experience the same similar statistics of scale. If you had independent jobs, mid-sized providers could achieve similar statistics of economics. Why? Because you have a square root of n, right? So it doesn't matter if you can put 10,000 jobs together or 100 jobs together. The square root kind of makes them look similar. But what about real world? Of course, I talked about theory using our simple modeling. But what happens in real world? The amount of data that we have on economy of scale is kind of mixed, right? Of course, we want to use the same COTS computers and components, whether we are a large provider or a small provider or mid-sized provider, right? So that doesn't differentiate much between the different providers. Everybody can try to locate their resources and put their data centers near cheap power supplies. So again, doesn't matter if you're small or large. You can argue that early entrants in the cloud computing game have an advantage of having better automation tools. But then the third-party tools, particularly open source tools, which we talk about them in this course in detail, a lot of them, they kind of negate that. So, but the takeaway lesson I want to say here is that you really, if you're a cloud provider, you really don't need to be a really large company, a really large cloud provider to be able to compete with them, right? Because if you are careful in putting together multiple demands, according to the value of common structure, this video, you have a measure of economy that helps you if you can actually at least try to put jobs that are as complementary as possible. Of course, you won't be able to do complete negative correlation, but as much as you can do, and hopefully you can get a little bit better utilization from your resources.
This lecture is about big data. It's a singular phrase, you might say. We're looking at a collection of data sets so large and so complex it's impossible to process it on one computer. And it's impossible to process it with the sort of usual databases and tools that have existed for the last 40 years in computer science. Because of its size and complexity, big data is hard to capture. It's hard to store, copy, delete. There's privacy issues. It's hard to search. It's hard to share. It's hard to analyze. And it's hard to visualize. So it provides multiple different challenges. But what it allows happen are all sorts of very, very good things. So descriptions of big data. I guess if you want to look at definitions, big data represents the information assets that are characterized by such a high volume, by its high velocity, you're getting lots of data in, by the variety, all the different types of data you're actually seeing. And it requires specific technology and analytical methods. It gets transformed into values that are worthwhile for society or for businesses. So those aspects are generally becoming accepted as to what big data means. So what are the challenges? Well, we're moving into the Internet of Things. We have a huge amount of data on social networks. We have instruments that record huge amounts of information like the Halley telescope. So all those devices, and I've sort of listed them here, provide enormous amounts of data. And some of those data, like cameras, now produce 30, 40 megs just as a snapshot. Medical data is going to be a big leverage. When you think of genomics and its interaction, you will see all sorts of possibilities for huge amounts of data. So what do we want to do with this? Well, that's this next piece. This is a processing piece. Analytics. But you've got to do analytics on something, so you have to capture it. You have to curate that data, just like you create books in a library. You need to search, share. You need to store it, transfer, visualize it, because eyeballs are a lot more efficient input processes for humans than just text. And then you've got to protect everybody's privacy. What do we expect to get out of it? This is, if you like, the gold. What we're looking for is predictive analytics. So you can sit down and say, your company is going to do this next year. Or you can look at science and say, oh, there's some connection here, some correlation here. We need to investigate that. Maybe there's a new physics law. Or, oh, people with this gene are having this disease. Maybe we should look at how to fix that problem. So it's doing predictive analysis, better decision making, discovery. What does it look like in terms of graphs? Our growth in data has been enormous over the last decade. And this is all happening because of cloud computing, because of the ubiquity, the ease of use of gathering that information. You can see it outranks phones, the way that cellular phones have increased, and it's outranked all sorts of things, including businesses. It has really sort of grown tremendously, exponential growth. I'll give you an example of how it's influencing bio. So bioinformatics, down in the 1980s, we were sort of looking down microscopes at slab gels and sort of gathering data off those. As we move forward till today, we're analyzing huge proteins. We're looking at DNA. We're looking at all the implications of life itself in terms of information. And so that has made a massive increase, and it allows discoveries that just are unparalleled, and we're beginning to learn how to approach things like cancer. Astronomy is another example where enormous amounts of data are coming to us. We start off down here back in the 70s, and really we were limited by our I/O devices and the storage. Now we're way up here. We are inventing new telescopes. We have new telescopes in the sky and on land, and they're producing petabytes a day. So that's a huge amount of information to suck in, process, and use. And you would really like to go back and look at all this astronomy databases once you've got a whole sky survey. Well, where are we going? I'll give you some numbers just so you can see the exponential growth. We've taken a lot of different examples from a lot of different areas and stuck them into one graph. But I want to just sort of outline some key points on this. So we have a database of 150 species and their genomes, and that takes up about, well, just below 16 terabytes of data. If we look today at social networks, then Twitter and all those crowd, they're operating around that area, maybe 300-400 terabytes of information. But as we go forward, we're going to be sort of investigating very, very complicated things like brains. The human brain is way up in complexity, millions and millions of vertices. So that direction is what we would like to get to. So where's the future? Well, we have scientists locally here, Gene Robinson, for example. What he would like to do is to combine DNA with RNA, with proteins, neurons, brain circuits, behavior. So you could take a honeybee and you could have a model of a honeybee that would predict how it goes out and forages. Put that into a computer. You can't. put that into a cloud? You can't. That could occupy all of the machines today. But we need to be able to do that to understand how life occurs and how we can do optimizations. And that applies not only in the BIOS world, but it has enormous implications on economies and on businesses. So we have this scaling of real-world entities. Up here, right at the top, is our target. We can't actually do this yet, but this is where we're moving. This is where we might be tomorrow. This is where we are today. There are multiple reasons for cloud adoption. Clouds allow economics. They allow you to provide computing and services to your users very inexpensively, and they save you the problem of building infrastructure. But they also allow you to share things, and sharing data is a really essential issue these days. And there are all sorts of reasons coming for using that big data to provide value to your company, to provide value to science, to provide value to medicine. So it's another round in innovation, and it's all enabled through virtualization, cloud computing, big data, that's going to provide a tremendous economic boost. Everyone benefits. What does that mean for you? Almost everybody will use cloud computing. They will use search, video streaming, social networking, just to name a few things. IT specialists in particular need to know about clouds, when to outsource, how to build applications, what its uses are. There are different concerns about how you architect a cloud, how you share data, privacy. Really crucial to all of this is being able to program cloud apps, use clouds effectively. And efficiency is going to be the bottom line because everybody's competing for the best use and for the economy. Everybody wants to use the scalability and the parallelism of the cloud to make their enterprises the fastest, the best, whether it's in science or business. So what about the general audience? Why should you be interested in cloud computing if you're just a carpenter or a mum or whatever? And the answer is, this is really actually a revolution. There is a general audience out there. It's going to have a huge impact on society, business, government. It's going to give everyone, from your children up to retirees, it's going to give everyone a new capability, a new way of viewing things, a new way of looking at policies, a new ways to communicate, as shown by our social networks, Facebook and Twitter and so on. And again, it has influence in other areas like privacy and security. What's next in our lectures? Well, we're going to have a demonstration. You're going to be doing this. You're going to learn how to write a web service. It's going to be one of these web servers that scales. So you can use 1, 2, or however many web servers you want to provide web service. And we're going to use load balancing to actually provide a fair distribution over all of the machines in the cloud to serve those web requests you're getting to your enterprise. So at the end of that unit, you will have confidence in actually being able to approach a cloud and use it to build a service. We're going to demonstrate that application. And essentially, it's a fundamental user application on the web because everybody, like or not, is going to access the cloud over the web. Then we're going to move to other lectures. So we're going to talk about software-defined architecture, how you build a cloud, what is its components essentially. We're going to talk about management controls, billing, software modules available. We're going to talk in general about distributed computing and reliability and parallelism, why distributed computing is so essential, why it enabled clouds to be built. And then we're going to provide insight to the power of sharing data. What does that really mean? So, in summary, cloud computing, it has 4 legs, if you like. One is economics, one is big data, another is this move towards taking cloud computing and providing utility computing that everybody can access across the globe. And the last is it provides a wealth of careers, of new careers in a new technology, taking us in new directions. Welcome to this lesson on software-defined architectures. In this lesson, what we're going to learn is how to actually create services, use services. You're going to end up producing a web server that can scale. But to begin with, let's talk about how services are created, how services can control other services, and then how that's all put together in the principal architectural components of a cloud and how they interact. There's got to be a framework, an architecture to do all this. That's what we're going to be talking about this time. And that leads into just how do you then use this framework, this orchestration, the services to build things like infrastructure as a service, platform as a service, software as a service. So at the end of this lecture, you should be able to go in and you should be able to construct a service, a platform as a service system. And the actual machine problem that you're going to be working on is to build web services which scale. So this all gets around to what Gartner and a lot of other people are now calling software-defined architectures. And rather than sort of lead you historically to where we're at, we're going to leap right in. So a software-defined architecture actually provides a facility for providing services complete with orchestration and provisioning. And this is all layered in a sort of structure that can be replicated. And later on, what we find is that you can apply software-defined architectures to pretty much anything. We're going to talk about networks, we're going to talk about storage, we're going to talk about compute, but people are talking about software-defined architectures for cities. So the cloud itself provides services. It has to have a way for the customers to control those services. And so you're going to have some mechanism to actually manage those services through the interfaces into the cloud, and that's called service orchestration. It's going to have provisioning, assigning services to individual machines, and it's got to have interfaces that allow people to manage that connection. We said clouds must provide these different infrastructures, IaaS, PaaS, SaaS. They've got to have both internal and external application programming interfaces. They need external ones for the customer, for the person accessing the cloud remotely, and they have to have internal ones. If you run a software system on your cloud, that software has to talk to the pieces of the cloud internally. So you need APIs both externally and internally. And some of these services will be actually the service you intend to provide, and some of them will be the management services that you need to control those first set of services. So the mechanisms and concepts of providing service orchestration and provisioning is called a software-defined architecture. And you're going to find that clouds, they will contain other software-defined entities. And we've just referred to them earlier, but you are going to see that the future of the cloud is sort of building on software-defined networks, software-defined storage, and software-defined compute. So here's a pretty picture which outlines just the sort of complexities we've got. What you see there is that there's an application development, there's there's IT infrastructure and operations, there's business process operations, and they're all going on concurrently into the cloud. You see that we have a multiple level of different services being provided. It's very difficult to build up to say software as a service if you can't manage the hardware. And so it's likely you're going to have infrastructure as a service. It's likely you're going to put operating systems and other sorts of systems on top to make it easier to use, which will be platform as a service. And it's likely that you're going to want to put software on top of that. So it's going to be like a cake with layers, right? Each layer providing a different level of services. Sometimes those layers will be providing service, like this IaaS will be providing service to the next level up, and sometimes that layer will be providing service to the next layer up too. Sometimes you'll expose IaaS to the customer and allow that customer to get infrastructure as a service. That's the layers of the cake. There has to be, first of all, mechanisms to actually use that system. So you need APIs for your apps and your scenarios, your providing mail services, whatever. There has to be APIs to do this. And that's, well, we've loosely called that business process operations in this diagram. At another level, the customer has to be able to produce those services, refine them, develop them, and then sell them to whoever its customers are. So you need to be able to develop, test, manage, control usage, build scenarios of that use. And that's the application development. You need interfaces to be able to help the customer do that. Down here, the customer is going to need to control the resources, deploy, manage, if he wants to scale things. Also, the cloud provider himself may need to develop, test, and deploy his infrastructures. And so you have different APIs corresponding to the different places where you need to be able to do the control, plus the actual services you're offering. All of that is called orchestration. The cloud service orchestration allows you to compose the architecture, has tools and processes used by humans to deliver a defined service, allows you to stitch the software together, the hardware components together to actually provide a defined service, connects and automates all the workflows going through that complicated cloud structure so that when you request a cloud, let's suppose you request a web page to a cloud, you are going to get routed through the cloud to the right web server, and it's going to respond back to you. Connecting that workflow together is part of orchestration, and it has to be set up by someone. When I want to scale up my web service, then orchestration will allow me to do that, bringing on new hardware and providing new routes to the system, providing duplicate web pages so I can serve a larger number of web requests. And you'll see that, you know, when you do up-down scaling, it can have different effects. If you're doing billing, you're doing assurance on QoS, each of these may impact those effects, and they need to be controlled. So we need a structure. What sort of structure should we have? And this is where cloud computing is moving the direction we're going at the moment. We are defining things called software-defined architectures. And the key part to the software-defined architecture, first of all, it provides services, but those services are completely abstract. They might be providing the user his application. They might be providing the service provider some way to control what his service is, and there might be some part of it allowing the cloud provider to control the allocation of resources and the smooth operations, the maintenance, and so on of that cloud system. All of those come in through APIs, and because of the complexity of all this, because you want customers just to know about their particular piece of the cloud, and you would like the cloud provider to know about all of the cloud, what we do is to employ virtualization and access control to actually give them those abstractions so they can manage it. Then underneath that layer, there's service logic to provide the services. There's provider logic, and there's cloud logic, all trying to provide different aspects of the totality of what the cloud offers. A middleware layer offers that type of infrastructure, and its design we will touch upon in this course, but not delve too deeply because we are really concerned with applications. The middleware matches all these services with the hardware, software, and data that's on the system. Now you notice over the side of here there's two boxes, control and resources. The cloud provider is going to actually offer control, provide resource allocation and access control, and he does that through software designed to do that, and that's going to interact with mechanisms to actually allocate the resources. So that's my overall software-defined architecture. Now, that's very abstract, and I apologize for that. What we're going to talk about is some concrete examples of this, and we're going to finish up with you actually programming one of these. So let's look at a data center, a software-defined data center, example of an architecture. You have your users doing applications, and those applications will go in through a portal that offers all the different services, the APIs. Those APIs will split up the requests into different types of requests. It would be, oh, this particular request requires so much network, requires access to the storage, requires this compute. Well, the portal divides these things up into tasks associated with the network, associated with the storage, and associated with the compute. But the user doesn't know anything about the real hardware. So these are all virtualized. You're going to have underlying this controls and schedulers to actually allocate the resources and to orderly progress through the tasks that have been assigned. Those in turn will end up talking to the actual hardware provided by the data center, the network, the storage, and the compute. Somewhere in there, those two boxes on the right on the previous diagram, there's a lot of automation going on, and that is going to be the middleware. That is going to be the software that allows clouds to actually serve all the customers. So today, what we've learned about is software-defined architectures. What we need to do is to tackle this question that's arisen about virtualization. It's a key abstraction in building software-defined architectures, and it's a key abstraction in actually building the first ever clouds. We're going to learn what software-defined networks are, what software-defined storage is, what software-defined compute is, and we're going to relate that to the clouds and talk about it all in terms of virtualization. Then, and very importantly, we need to get you some practical experience of building an example. So we're going to just take a simple web service, map it onto a data center, and allow you to scale it using load balancing to send web requests to the appropriate services. So after that lesson, what you're going to learn, well, what you're going to be able to do is actually build your own type of system on a software-defined architecture, whether it's Amazon, whether it's Google, or whether it's OpenStack. After that, we're going to look through, or in this particular lesson, we're going to look through exactly what does infrastructure as a service mean, because clearly you've got to start somewhere. Allocating machines and building services on top of those machines is a good place to focus. We're going to move up that sort of software stack and look at some of the middleware. And there, we're going to be looking at Mirantis and OpenStack as examples. We're going to learn how they actually orchestrate, how they provide views into the system through dashboards. We're going to see how they're controlled and how they control the cloud itself. And by the end of this lesson, you will have an appreciation of how systems are structured with these abstractions and with orchestration using all these tools, so that now when we finish this lesson, we'll be able to launch into some examples of applications. We're going to be doing MapReduce as the next module. But first, let's just move on to virtualization and think about how does virtualization support this idea we've got of software-defined architecture. Well, this lecture is to introduce you to the different interfaces you can use and the different setups that you can use to get your infrastructure. You can get different sorts of, well, infrastructure as a service, platform as a service, and software as a service, and we'll compare those. And what we're going to do is to use what the major cloud companies provide as a sort of set of examples, and they also will help us sort of visualize what could be done. So here's a comparison between all the different services that are provided on a major set of services. Split them up into three: infrastructure, the platform, and then the software as a service. And if you look at the diagram in more detail, what you see is it really matters what you contribute as the client towards the operations of the system as to which one of the IaaS, PaaS, SaaS you actually fit into. So in the packaged software, where you're sort of providing everything, you manage the whole of the system. And in the infrastructure as a system, that's decreased. And what you're doing is getting from the provider the bottom level, that pink level, virtualization, services, storage, network, and you're having to manage the application's data runtime, middleware, and operating system. If you move to a platform as a service, then this extends and you get the operating system, middleware, runtime. You only have to manage the applications and data as a service, or the applications and data in your service. If you go to a software as a service, then it's all managed for you by the vendor, and the applications, what's provided is the client to the client, and so the client doesn't have to manage anything. So these different diagrams show you how much involvement you get and what you can do. And of course, associated with each of these is a degree of flexibility about what you can actually do. So infrastructure as a service, a lot of the on-demand, Amazon EC2, VMware, vCloud, those type of systems are how it's being provided and what's being provided. Platform as a service, there you have on-demand application hosting. You've got Google App Engine is the prime sort of system. Salesforce.com uses a turnkey system, but they also allow you platform as a service. And Windows, Azure, and Amazon all offer you the same sorts of things. Software as a service, there what you're looking at is the sort of Microsoft web companion, the things like Gmail and so on, that it's just turnkey, use the applications. So moving to platform as a service first, it's a cloud computing environment, and it allows the users to run applications on the cloud. It's above infrastructure. PaaS doesn't require users to develop their own operating system environment, and what we have is sort of a middle ground, a development platform for the customers, yes. It offers an application development platform that scales sometimes with demand, although many times automatic scaling is something that the user still has to provide the details for, although there's primitives to allow you to do the scaling, but you still have to figure out how that scaling should occur. And the name of the game with this is to provide a cheap service. What you're doing is renting the computer and the operating system essentially. You're providing a sort of environment that you're going to build for your user, and this is a sort of cheap accommodation or inexpensive accommodation. You're benefiting from having all of those clouds support, but you're having to do some support yourself, and that support is added value that you're giving to the customer. And so in that diagram, you're really sort of focusing on this type of territory. As you can see, if you move backwards and forwards in this diagram, if you go for infrastructure as a service, then you're having to do much more, and if you're doing software as a service, you're doing much less. So there's an official definition from NIST. I don't want to dwell on all of that definition, but the key things, you get control as the consumer, but what you can do is to provide your customers with deployed applications and configuration settings for those applications, and it requires you to do a little bit of work. These systems work together with other parts of your infrastructure. So, for example, Google can also provide infrastructure as a service, but it mainly provides the PaaS, the Google App Engine. If you look at sort of Amazon provides a range of facilities. It doesn't actually specialize in providing a platform as a service, and so it's the sort of low end, you get much more involved in providing things for the system. Whereas the Google App Engine, you can use multiple different languages, you can use databases, you can use all sorts of support in order to provide those applications to your customers. So let's just, to be sort of fair to everyone, we'll look around at other systems. Windows Azure, it provides both a platform as a service, and as we later show, it also provides infrastructure as a service. It provides sort of compute and storage and an application fabric within which to work using its .NET and other types of systems. So it's kind of a very sophisticated platform as a service that you can provide, and obviously you can you can actually go to Azure and get beneath that as the infrastructure as a service, so you can have a sort of continuum. So how does that rate? Well, platform as a service can be better for cost than than infrastructure as a service. The systems are optimized to run applications efficiently. You're benefiting from the actual server company optimizing the PaaS for the particular platform that you're running. In sometimes when you go out there and you get an information as infrastructure as a service, it's only going to provide the hardware, and the clients have to be in charge of everything, including load balancing and networking. So from the point of view of time spent from the consumer's point of view, platform as a service can be a better deal. It can give you better optimization. But if you want something very, very special, then you may have to just choose to go with infrastructure as a service and build your own. One of the benefits of platform as a service is that the vendor of the services, the actual service provider, can employ multi-tenancy on the platform as a service, and so optimize their infrastructure by allowing many people to be using, consumers of that PaaS to be using the system. So this can give you an overall lower cost in how things are being operated. Multi-tenancy means that many users may share the same physical computer and databases, and typically if you have to provide your own IaaS, infrastructure as a service, multi-tenancy, then you would get involved in all that complexity. Well, the PaaS avoids you having to think about it. PaaS is better suited for multi-tenancy than IaaS because an IaaS may provide each user with their own virtual machine, may create a clear separation of resources, and in the PaaS you can get finer grain. You don't have to switch from one VM to another VM or such sort of sharing techniques. However, when you've got a PaaS, the users will notice that they're sharing this machine, so as they look at the performance that they're getting, it'll be degraded as more and more users are doing a multi-tenancy of that particular platform. So you've got a trade-off. In one you can control it, but then you have to manage it and you have to do the switching. In the other, much more flexible, much faster, but then there's hidden costs that your users will actually take cycles away from each other or share the cycles out between them at least, and this will look like worse performance. So a lot of people worry about vendor lock-in, particularly with platform as a service. The idea there is the platform as a service locks in applications by requiring users to develop apps using proprietary interfaces and languages of the vendor. So if you want to switch from one platform as a service to another, that's going to be difficult for you to do. So that naturally leads to, if you're using a system, you get locked into the prices, locked into the vendor, and your business really depends on the dependability and the availability of that platform as a service. If you go for an infrastructure as a service, then you have a lot more flexibility because most of that problem is hidden in the virtual machine. You can move your virtual machines to a different provider, and you can therefore keep sort of offering the same sort of level of customizability and everything else to your clients, but well, you're paying that penalty of having to work with a whole stack. Development tools. Many PaaSs offer browser-based development tools. In this way, developers can create their own applications online. There's an ease of deployment. You can get things up and running very fast. The platform typically provides you primitives to take care of scaling, so that's much, much more easy. So the development tool base for platform as a service is usually richer. On the software development side, as a developer, your objective is to create an application in the quickest, most effective way. You don't want to create applications that use convoluted methods that take a long time to complete, and the user only sees the end product, not the development process. So in a sense, by having a platform as a service, if the platform is a good platform to work with, then you're cutting out all the maintenance, all the thinking, all of the work associated with providing that platform, and you're building on, if you like, the skills of your platform as a service vendor to make your system also much more effective, particularly in software development and cutting the costs to getting to market. So these are all pluses. So overall, you do have to, when you go to a cloud provider, think about what sort of service you want to provide, whether you can do it as a platform as a service or whether you have to go with an infrastructure as a service. You need to make those decisions. They have long-term consequences on your business, so you need to think them out well. If you choose to use a platform as a service and get your application vendor locked in, then your business may fail if the platform as a service greatly increases their prices, or if they provide an adequate service. And you won't be able to get out of that, you won't be able to move, since your application can't easily be migrated. And then an application that's used to fulfill a temporary need may be handed to a PaaS solution very, very fast, and so that's a benefit. An application may need to be deployed quickly, so again, a PaaS would be a benefit. If your software team is small, then running on a PaaS may be the better thing because you have the backing of the actual PaaS providers. Their team will be there supporting, making your life easier. So that ends the first step, and what we're going to look at now is all the different companies, what they provide, how much. I won't detail how much they cost. You can go on the web to look at that. What I want to do, though, is to show you how each of the different providers is operating. Sometimes they are mainly focused on infrastructure as a service and then provide platform as a service as an option, or sometimes they provide platform as a service and they have infrastructure as a service as an add-on, and sometimes they don't provide that at all. They just go for maybe software as a service. So let's go on and have a look at some of these companies. Now we've got virtualization, we're going to look at how you build infrastructure as a service. And I'm going to take you through a number of steps. I'm going to look at some early days in building infrastructure as a service, and then we'll look at OpenStack. The first approach was a very interesting university research project from Cambridge, development of an operating system, Zen, that provides full virtualization on the x86. And what it did was to provide a layer of interpretation to allow you to have a hypervisor-like module that interpreted different Linux kernels on top of it in a VM manner. And it didn't really sort of create enormous changes in the operating systems that were being run. Typically they're called guest operating systems. It was called para-virtualization. One of the things that needed to be done in order to make each of those virtual machines independent from one another was to make sure that as they wrote to devices, they didn't step on each other. And so there was work done to try and separate the devices, make the devices work with the VMs in a collaborative, cooperative way without causing disturbance. And that was all done in what's described as domain 0 of Zen, which was an instance of Zen that was doing the I/O. So there was lots of distributions, great maintenance on this, and it took off. Since then, companies like Intel and AMD have produced virtualization hardware. We've moved along with the virtualization, so it's now in most of the operating systems. And what we will find is when we move to OpenStack, it's kind of assumed that you do have all of the virtual machine support that you need. Now, this ability to run a hypervisor and then to run an operating system, a guest operating system on top of it, allows you to bring up operating systems when you need. And so there's an actual movement, if you like, to say, well, okay, can I also just bring up different hypervisors on bare hardware? And since the bare hardware has evolved and hardware can be organized for data centers, what has occurred is that we've moved towards bringing up very different versions of an operating system, of a hypervisor or whatever software you like, on an Intel x86 under control from somewhere else. Remember we talked about control and the processes that we control. That has occurred to a great extent in this, in that you have a controller to actually bring up various machines in different guises, whether they're whatever operating system, whatever hypervisor they want to run on bare metal. So if you like, Zen was a sort of trigger, and from that we developed further ideas. The notion of how do you bring up a machine from idle state to running an operating system had been solved sometime earlier with Pixie Boot, meaning that when you boot an operating system, you actually booted it across a network from an image stored on a file server. So it brings that software across. It has enough of a BIOS in one of its, well, actually it's in the Ethernet card, to bring that across, load it in, and then start operating, and it brings the rest of it across in a bootstrap and runs that process. So that brings us to the present day and looking at OpenStack. And I want to give you a sort of example, a commercial example of how people actually do the sort of things I was describing. Mirantis provides a complete package solution you can download on your laptop if you like, but it will work on bare hardware too, of bringing up infrastructure as a service on whatever you choose. If you put it on your laptop, what it will do is to run a virtual machine and bring up on top of your virtual machine various images that represent virtual machines in accordance with what you would actually do if you were on bare hardware. If you put it on bare hardware, what it will do is the same thing, and it will actually allow you to choose which hardware and which software to bring up on which piece of hardware. So let's just look at what Mirantis is doing. First of all, it has a dashboard for controlling for which image you want to actually run. And the dashboard is connected into what they call a controller. The algorithm, the component that runs all this is called Fuel, and Fuel actually exists for beyond Mirantis in other sorts of OpenStack implementations. What Fuel does is to connect your hardware, if you like, to your virtual machines. So Fuel runs as a controller in that control space across your system, and what it will allow you to do is through the dashboard load and run images that are stored from a disk. And they can be compute images, they can be things like controllers, they can be boot servers, they can be network operating systems to control the network, they can be storage operating systems to control storage. And so you have a mechanism now to actually deploy your different services on your nodes. And the assumption is you've got a fair number of nodes, so you can choose. You can then create these environments for computation. Say you want to build a cloud with a particular Ubuntu release, you can build that stepwise, saying, okay, first I need some sort of controller for that cloud, and then perhaps you would choose OpenStack to do that, and then you would choose all the various releases of Ubuntu. So here in this diagram, what I'm showing is the dashboard is connected to Fuel. Fuel can talk to the nodes and talk to the boot server. What it can do is to organize what gets PXE booted onto the various nodes, and it can start those PXE boots on those various nodes. And it's just started OpenStack on one of the elements, one of the nodes there. That will be a compute server because it's actually a controller. It's all about processors. It would be known as a controller to Fuel as it's running, but initially it would just be another image that you download onto a node, comes up with the OpenStack framework, and boom, then that becomes your controller for your Ubuntu images that are going to run on other nodes. So that slide leads into this slide where the dashboard now becomes OpenStack, and OpenStack is talking to the OpenStack controller, which is now fully operating as control as opposed to data for everything. And now the OpenStack controller allows you to bring up other nodes like network, compute, and storage all off the same boot server, but now different types of images. If you want a network operating system to control the switches and the routers to give you a network virtualization, that would be one, the network operating system. If you want a compute server to provide Ubuntu, then you would bring down the Ubuntu operating system, put that onto a compute server and create that. If you wanted your storage, you would do the same thing. And so you construct piecewise all of the different pieces of your virtual data center now on the hardware. Eventually what you're going to do is to talk to the network operating system, and you're going to tell the network operating system that you actually want to allow user applications into this system, so you're going to publish some IP addresses that the users can actually use to access the compute and storage of your virtual data center. And so the story goes. So you've taken, if you like, a virtual description of a data center, this OpenStack description. What you've done is to map that onto hardware, and you've instantiated it. And all of that mechanism has been allowed because of this infrastructure as a service from Mirantis, which had its own front end and allowed you to allocate machines. Now, because you want to automate this, you are allowed to store scripts for all these different operations. So if you want to repeat this, you can do so very readily. If you want to scale it, you would say you want to add processors or storage to it, you can do so very easily because it's all scriptable and you can just add those scripts, whether doing it through a visual element, through another dashboard, or whether programmatically. So let's just sort of reflect on that Mirantis. What Mirantis was doing was to bring up a Fuel controller. The controller allowed you to bring up OpenStack controller, the networks, the compute servers, and the storage. You can look at how Mirantis works in practice of a training manual that Mirantis has provided. It's just an example. There are lots of other ways to do this. There's lots of other versions of Mirantis to do this, not necessarily commercial. There's ones in Genie, and various other large corporations have their own version of it. But the principle is all the same. What you're doing is recursively building up your virtual cloud, you're instantiating your virtual cloud, you're gradually sort of building it up from the baseline and then allowing the public, your app users, to actually access this, and you're still retaining control over it. You can still modify it, you can scale it up later, and so it's all becoming very programmable. It's making your data center effectively a programmable element that can run on bare hardware. We touched on the basis of infrastructure as a service, and I said it's a sort of bottom layer. On top of that, there's layers of abstraction, and we build all sorts of interesting systems. So what enables us to do that? And it's this approach to abstraction that we've developed over the years, and a key technology. That key technology is called virtualization. We now know how to take computing resources, virtualize them, and build them into new resources, new facilities, new services. And those services indeed may be combined and used to build other services, again, perhaps even using virtualization. So we spend some time discussing how virtualization works, what sort of virtualizations we can get, and we talk about all of the things that we can virtualize. So let's just quickly review that. So we buy machines, we put machines into a cluster, and we build a cloud from the cluster. You can buy those hardware services, just the, if you like, the metal, the compute cycles. You can buy that as a service. I can sell to you, say, 5 machines running at 3 gigahertz each or 4 gigahertz each with so much memory, 2 or 3 terabytes perhaps, and lots of disk. I can sell you that as a service that you can use. When you're finished using them, they get returned to me, I use them for somebody else. While you're using them, they're yours. You just get to see just those machines, and you can build anything you like on top of them. You are the controller. You can decide what sort of systems you want to put on them, what sort of operating systems, what sort of software applications. If you want to do the hard work, you can construct your whole business right up from, if you like, the bits on the metal up to very abstract layers, like if you're wanting a taxi service, you can build all those layers up to providing the HTML and so on, enabling the taxi service all by yourself. But that would incur costs. That would be sort of really sort of extravagant in the terms of getting started. It's not the lightweight start that you think you would benefit most from for getting fast businesses organized and set up. So we have other virtualizations on top of that, and we will talk about platform and software as a service later. Moving horizontally, if you like, from virtualization of the CPU and giving you, well, hardware and then building virtual machines on top of that hardware, what I want to talk about is another direction that you can go, which is virtualizing the network. So you can think of, I've got this data center, but then I give you, say, 5 machines, but I want you to think that they're just 5 machines. And you can't see any of the other data structure, any of the other data center, and the other parts of the data center can't see you. You can get out to the web, and you can process. You can attach storage in another sort of virtualization. You may have your own storage attached that you can expand and contract. That is another asset that clouds can provide. So we have virtualizing the network, we have virtualizing storage as a separate chapter in what we're describing in our presentation. once you understand this sort of notion of building modules and building hierarchies and abstractions, then we're going to start discussing some of the ways that this can be done. We're going to discuss the virtual machines, how to build virtual machines on top of hardware or operating systems, how we can build lightweight virtual machines using container technology, very exciting, lightweight threads that give you a protected environment that allow you to build very, very fast switching, very, very fast systems to assist your web or database. We're going to look at software protocols that allow you to build such containers very quickly. So Docker is a sort of software engineering technique that has allowed people to build containers for the cloud very simply, very fast. And Docker itself has its own scheduling, its own decision-making apparatus. If you want to run 1,000 threads over your 5 or 10 machines, Kubernetes allows you to do that. So we have levels of this abstraction. You can have a whole machine, you could have a core on a machine, you can have a process on a core on a machine, or you could have a thread. And this thread can exist on multiple different cores, whichever one's free, and it can move around, and we can have a scheduler for those. So lots of different variety, and we'll cover that. We're going to look at some more sophisticated containerization, abstract virtualization, you might say. I want to mention Java virtual machines, and there what you're going to do is choose, say, a particular favorite language, Java in this case. What we will do is to provide you an environment that's just Java. And no matter how many processes and threads and storage and whatever you want for your Java, we can provide that by duplicating the JVMs and getting them to connect together through distributed computing and running to support what you want on the cloud. The whole economics of cloud, the raison d'etre or whatever, for clouds requires you to share. So lots of users, they see their own piece of the cloud. They don't see other people's pieces of the cloud. They don't understand that they're sharing hardware. That's all sort of abstracted from them. The answer to how we do this, well, it's layers of abstraction introduced through virtualization that provide that. So we're going to introduce an abstract model of what a generic computing resource should look like. And we have a background knowledge of what physical computer resources are like. Well, what we have to do is to build that abstract model from this physical computing resources, and we do it with virtualization. So let's have a look at layers of abstraction. I go out, I purchase a cloud center, I get lots of hardware, I get some processors, some network in the center there, I get some CPUs, and I get some storage. That physical model then is going to be multiplexed to many different users. Virtualization keeps them all independent from tripping on each other and allows us to build our software-defined architecture. So if we put all these things in a box, what we're going to do is to model what those systems provide, but in an abstract way. Compute, storage, networking. So those abstractions will get mapped down onto the actual particular physical entities. But we're building layers of abstraction that simplify the matter of running your tasks on these systems. Virtualization is a mechanism to actually create the dependencies, to map those dependencies onto the real hardware and provide the layer of abstraction that we want. So here we build using those machine components, which we've abstracted, a complicated data center. And it's going to have abstract storage. It's going to have an abstract computer. It's going to have an abstract network. We may have multiple computers. The networks can be hierarchies. They can be tiered, all sorts of different arrangements, but we don't have to care because what we're doing is hiding that under a layer of abstraction. The physical computer resource is provided to many users. Each user is going to see the system that's provided to them rather than the whole of the cloud. So moving up a level, what we're going to build on top of that is another layer of abstraction, and that is how we actually allow users to program and interact with the services of that cloud. So you need programming platforms, you need to have mechanisms to allocate those programming platforms, you need monitoring, you need billing, all these other things. They're all going to be built on another layer of abstraction that hides, if you like, the underlying complexity of all those virtual machines interacting. So, as we said, virtualization is the foundation of cloud computing, and we're going to step through this fairly rapidly, but we're going to step through it because it then answers a lot of the questions you will have about how we actually build such complex systems. So virtualization allows you to have distributed computing models mapped across networks onto individual machines. And what it does is it doesn't create dependencies between the physical resources and your application. Instead, what it does is to build an abstraction that allows you to program them, but not have to care about them. So each of the services are going to be based on virtual machines. They're going to be based on remote procedure calls because of distribution. And the client service model is going to be employed quite extensively in providing the services to the outside clients of the system. It will offer simplicity of use, ease of programming, and allow those client-server paradigms to be used to construct services, but now instead of just perhaps a single-threaded, simple model, sequential model of a client-server paradigm, it may end up that the client-server paradigm uses lots of resources and offers lots of parallelism through distribution. It will certainly offer lots of fault tolerance, lots of reliability because of the duplication. What sort of virtualization exists? Well, in this and the subsequent presentations, we're going to talk about different types of virtualization. In this one, I want to focus on a single one, which is that for compute. What we're going to take is if a simple model of a computer and virtualize that so that multiple instances, multiple applications, each think that they have that simple model of a computer underlying their computation. There are two ways to do that. One is we can do that with hardware assistance, building into the computer model mechanisms to give different images to the applications such that they think they have the whole machine all to themselves. Another approach is paravirtualization, and then what we do is to compile that view of virtualization into the actual software itself. So all of the software is run through special compilers that take care of giving you different instances of the hardware for each of the different applications. At the operating system level, we can also talk about virtualization. We can talk about different mechanisms for virtualization using the operating system existing approaches to virtualization. There you've got virtual memory, you have different threads and processes, you have interrupts and process switching. So at the operating system level, you can provide virtualization in the sense of containers. That's a process with an environment that you can easily duplicate. We have jails. These are processes contained in a virtual memory that's difficult to get out of. We can provide operations that enclose or increase the amount of the system you can see, and change root allows you to do that by having change root. What we can do is to move you up the file system hierarchy so you can only see a piece of the file system. We have zones. We have OpenVZ and Virtuoso, all sorts of different software systems running on operating system that can help provide virtualization. So, just to recap, we have, first of all, your native hardware. Then we have hardware-assisted virtualization, which gives you sort of copies of that hardware. We have para-virtualization with our compilation methods. Then we can move up a level into the operating system and provide virtualization at the operating system level. Well, native and full virtualization would clearly be an attractive opportunity to provide really powerful and effective virtualization scheme, so we'll deal with that one first. The virtual machine simulates enough hardware to allow an unmodified guest operating system, one designed for the same CPU, but to run it in isolation, that it doesn't know about any other of these guest operating systems. So in the diagram, what you see is we have multiple guest operating systems. We have some management software, and what we're doing is to multiplex those different guest operating systems onto a hypervisor, virtual machine monitor, on top of the actual hardware. The hardware is providing virtual machine instructions and virtualization instructions. The hypervisor takes advantage of those instructions to build the guest operating systems that operate in that sort of isolated environment. There's a number of examples of those: VirtualBox, VirtualPC, VMware, QEMU. All of those are examples of how you could build that full virtualization. The hardware, well, what it does is to allow each operating system to think it's independent from every other operating system. What you need is additional layer in the supervisor state of the computer to enable that. Intel uses Intel VT. AMD uses AMD-V. It's a virtualization scheme that's very similar. And software which takes advantage of that is VMware Fusion, Parallels Desktop for Mac, Parallels Workstation. All of these things provide you software to actually control the hardware instructions in the Intel chip or AMD chip to get you that virtualization. Para-virtualization, this is where you're using compilers or interpreters at runtime to give you that same virtual machine concept. It offers a special API that can only be used by modifying the guest operating system. So when you're running para-virtualized, what it's going to do is either compile the operating system in a special way, inserting special APIs where the existing APIs are, or what it's going to do is to require you to modify the operating system to call those APIs so that your operating system becomes virtualized. An example of that is Zen. Here's a diagram. What you see happen here is that we've produced stubs between the actual hypervisor and the modified operating system, the guest operating system, and those stubs link all of the systems together with a control piece of software called a hypervisor VMM, and then all of that virtualization is basically interpreted by the hypervisor, giving you independence for all the guest operating systems. So we've talked about the hardware, and doing it with software or hardware instructions, providing virtualization that way. You can also provide it at the operating system level. Operating systems for a long time have had virtual machines, and that allows you to create all sorts of structures. So in this part of our lecture, we're talking about virtualizing a physical server at the operating system level, enabling multiple isolated and secure virtualized servers to run on a single physical server. If you want to go out, look at software, Linux Vserver, Solaris containers, FreeBSD jails, changeroot, cgroups are all examples of software systems running in an operating system to virtualize a physical server at the above the operating system level to provide those separate virtualizations. And oftentimes we call those things private servers. They're not completely virtualized. You will find security and other sort of issues, interference between some of those things. Typically, when you step outside the requirements, the specifications given by the software that gives that sort of system-level virtualization. So we've moved from looking at software-defined systems to virtualization, as virtualization being a mechanism to offer the various layers within software-defined architectures to allow you to control and manage the systems and to give the applications, the user applications, independence from each other. And what we've seen here in the virtualization lecture is we can take compute and we can provide services to individual operating systems that can then run applications, or we can provide an operating system that offers services that have been virtualized and are independent and provides those to the user. So all of those mechanisms are available. We're going to next take a look at software-defined networks and then software-defined storage and show that there's similar approaches with networking, with storage facilities that mimic this. Then we're going to take all those and put them together back into our package to provide a cloud. Well, virtualization applies very specifically to processes in a CPU, but it has applications elsewhere, and it has gradually crept over the whole community that the realization that virtualization is a very, very powerful technique to organize large data centers. I'm going to tackle first software-defined networks, and then I show the same type of virtualization with storage, and then bring it all together when we talk about OpenStack. So with software-defined networks, the realization is that people are actually mapping virtual networks in all sorts of different formats, but they're mapping those onto networking hardware. And you can have a diagram here that shows this type of notion, that what you can build up is a set of virtual circuits, communications between different nodes in a system, irrespective of the actual hardware. Sometimes you would have to route through an extra router, other times you could route directly, but this notion of providing an overlay network on top of a physical network is very, very much like the virtual machine that we've been discussing, but it's just applying to operating systems. In this case, it's applying to network operating systems to networks. So the picture shows applications wanting a network, and they talk to a network operating system that controls the switching, the routing of the packets in the network, and that really defines how the packets are transferred. But what it doesn't do is to say how it will actually get mapped onto the physical network. that can be different. It could be top of rack, a star type of thing. It could be a mesh. So software-defined network has been one of the steps that's really crucial in developing OpenStack and in building big data centers, because what it allows you to do is to virtualize the network, to build a data center, build the computation you want without knowing what the physical network is, but you define it and then you map it onto that network. So you can preserve, if you like, the original concept and then choose lots of different implementations to make it run fast. So in this diagram, what I've got is a heart. It's a love affair, if you like, with virtualization. Virtualization was good for processors and CPUs. It's also good for networking, and examples of sort of networking operating systems that control the structure of the networks would be NOx, but there are a number of them, and what they do is to virtualize the operating system. So having established that thread, we can go one more step. What was good for the networks is also good for storage. You find all sorts of different requirements for storage. For example, whether it's attached storage, where it's mapped so that each node has its own individual storage, whether there's just one big storage center in the whole of the data center that everybody communicates with. It doesn't matter. You can build your software so it thinks it has storage and then map it onto whatever structure's underneath. And so we talk about virtualized storage as well, whether it's network attached storage, whether it's a big server with lots of storage, doesn't matter. So we have this version of our systems where we think, well, we would define what we want for storage, and then we will map it across onto whatever physical storage is actually available in the data center. We virtualize it effectively. So there's a continued love story, if you like. It's a triangle. We have virtualized storage as the third leg of this data center, this virtualization going on for data centers. So today we're going to look at virtualization in all its different forms. And what we're going to find is there's a range of virtualization mechanisms you can use. Some are much more efficient than others, some are much more secure than others, and which one you choose is really going to depend upon your application. What's exciting is that this is really a sort of evolving area, and that over time hardware and software have come together to improve both virtualization from a software point of view and virtualization from a hardware point of view. So it's a moving target. We're going to be giving you an update, if you like, and come back in a couple of years and it may well have changed. However, some of the principles will remain the same, and those principles I want to get over in this lecture, and in the subsequent lectures I'll give you some ideas about which directions people are moving to provide faster, more application-oriented, if you like, virtualization that matches what people are wanting for their clients. So in this, let's take a look now at the range of different virtualizations that occur. We've got native, which is really sort of full virtualization. The codes are running on instructions. The instructions themselves are virtualized. They're in a sort of envelope that does the virtualization. The hardware is providing that sort of separation from one user to another user as they execute their machine all on the same hardware. And when we say it's hardware assisted, meaning that when you virtualize, what you're going to do is to take the hardware and switch from user mode into operating system mode, from operating system into doing I/O and so on in this envelope, this encapsulation, this way of separating things. and the hardware itself will support doing that. So if we're in the client, we drop into the operating system, what will happen is that there'll be a special interrupt saying this particular VM wants to go from user space to an operating system space, and down below somewhere there'll be a hypervisor. The hypervisor is going to do some context switching for that to make it all happen seamlessly, and the operating system will be executing in its own security zone, supported by the hardware. It can do, say, update the page tables, do things like interrupts, and all of the hardware will be oriented so that that particular virtualization thinks it has all of the different devices, it sees all of those events, and so on. So that's hardware assisted, and to build those sort of systems you need to go into the hardware and add additional instructions, as you might find in the VT and so on. Going to distinguish that from providing sort of software virtualization. Sometimes the software is helped by hardware, but most of this encapsulation, this virtualization, is being performed by the software. Para-virtualization is the first one that came along. In terms of sequencing, what it was doing is provide hooks to replace the hardware assisted, to give you that sort of virtualization for the operating system and for the client. Then we'll start talking about more sophisticated approaches which combine much more software with the virtualization concept. And we're going to be doing this at the operating system level. What we're going to do is to build operating systems that accommodate virtualization, do all of the things of para-virtualization essentially, and give you a faster execution, and they are thinner, lighter than the para-virtualization, and therefore execute faster. They may not give you so much security, and we'll look at various ones of those. Containers, very popular at the moment, and actually sort of a leading contender nowadays when you're building a system and you want to decide what sort of virtualization to use. Containers really stick up their benefits and attract a lot of users. Jails are sort of old style Unix mechanisms which prevented you, when you were running on Unix, to actually access different parts of the file system. They would lock your root file system somewhere. Change root was the mechanism used to actually implement jails, and we were talking a bit about that. We're going to talk about zones, which are built out of these ideas. These were made popular by Solaris. We'll talk a bit about those because they're slightly different from containers, and we'll also talk about OpenVZ and Virtuoso and how that operates. So you end up, at the end of this set of lectures, or this lesson, you will end up with an understanding across the spectrum of possibilities of which ones match your best interests. So the virtual machine simulates enough hardware to allow unmodified guest operating systems, ones designed for the same CPU, to be run in isolation. There's a range of these, and examples would be VirtualBox, VirtualPC, VMware, QEMU, WinFallIn, and Zen. And I'll talk a bit more about Zen later on. But essentially, if you look at the diagram, what we've got is the hardware. We're going to put a hypervisor on top of it. We're going to have applications and a guest OS, and for each of those applications and guest OS, there's 2 there listed. We're going to have some management software that essentially takes the applications and guest OS and provides them, isolates them, provides them their own execution environment. So in this scheme, the obvious thing is to interpret pretty much all of the instructions. And this is really underlying, say, something like QEMU. it's clearly possible to take each of the machine instructions and interpret those machine instructions as to what it does. And we do one-on-one all the way through. We can do it for the applications, we can do it for the guest OS, and we can build a simulator for everything that happens on the system. But that would be inefficient. So a lot of these machines, what they do is only simulate the instructions that are relevant, that are difficult, that might break out of the virtualization. And they execute the other instructions, things like add, multiply, divide, directly on the machine using the machine architecture. And in this way, you can get orders of magnitude speed up on a machine's simulation such that these virtual machines almost behave as fast as the software running on the real hardware. So in this scheme, what we're going to do is to go through and replace instructions that are sensitive to security, are sensitive to multiple users being on the box, and you don't want people to know there's multiple users. So we take those instructions and we're going to simulate the effect of those instructions on the box. All right, if we delve down into a hardware solution for virtual machines, then you'll see all of the mechanism that the hardware would have to, or that a simulator would have to build in order to do what hardware is doing. And so that gives you a comparison. In this system, what we're going to look at is what would actually be required to run a virtual machine on hardware itself so you get a really fast execution. And we want to be able to have the client, the application, talk to a guest operating system, and we don't want it to be interfered with by other virtual machines. And the classic sort of solutions to these in the PC or in the cloud space are from Intel, the IVT instruction set that supports virtual machines, or the AMD virtualization, AMD-V virtualization hardware in the AMD space. And examples of systems that actually use this are VMware Fusion, Parallels Desktop for Mac, and the Parallel Workstation. What is happening in the diagram is that all of the difficult instructions that the applications and guest OS would execute will be executed with instructions on those machines. There are additional extra instructions in order to make all of this mechanism work. And there's additional software that makes it smooth so it will operate properly. Let's take an example. You're in the application and you want to do some I/O. Then what will happen is you will want the operating system to do some I/O operations for you. So you need to context switch into the operating system. In these hardware-assisted mechanisms, what you're going to have is a hardware context switch to go to an operating system level in the kernel, but it won't be the lowest level. It won't be in charge of all the I/O. What it'll do instead is it'll have enough privilege to effectively execute as your operating system, and when it wants to do I/O, it will execute instructions, but those will get interpreted by another layer lower down, which is it's again going to be a hypervisor, but those would take the requests, the I/O requests, and map those I/O requests into actual I/O operations on the machine. So at the lowest level, you are going to interpret essentially the difficult operating system instructions that would break the illusion of virtualization. And then moving up, when you go from an application into that operating system, you'll be doing an interrupt or a trap into the operating system. That trap is going to have the unique properties of taking you to the operating system code, not to the hypervisor underneath. It's going to redirect or make sure your interrupt actually goes to the operating system, not to the hypervisor. So all of this is built into the hardware, and what it would do is to completely separate out that guest OS and the applications from all the other applications and guest OSs on the machine. Now, in terms of just efficiency, it can be very efficient, but you now have the guest OSs really operating in their own virtual memory with their own caches, with their own data, and as you're accessing all of that material, you're basically sort of isolated from everything else. You can't share any of those values. So if there's an operating system piece of code or there's an operating system data structure in the guest OS, it's not going to be shared with anything else. And so there's some inefficiencies that occur. Similarly, when you transfer from the application into the operating system and then into the hypervisor to do I/O, each of those transfers is going to be a little bit of overhead. With partial virtualization as opposed to the hardware virtualization, what we're going to see in these machines, in these computer machines, is that we don't have a full instruction set to actually do the virtualization, to interpret jumping into an operating system or that the operating system wants to do I/O. Instead of what we're going to find is we replace some of those difficult instructions with software code. We may have in the virtual machine and in the underlying hardware support to do that, and we may find sort of support for maintaining the address spaces, but essentially a lot of the operations that were mechanized before aren't. The opportunities, however, for sharing and for priming caches and sharing caches are much higher because we now no longer have completely separate domains of execution of the applications and operating systems. So there are different ways to do this. One of the ways would be to simulate the hardware. Another way is that we go in and we modify the operating system, the guest operating system that we were there talking about, and we insert into the guest operating system APIs to do those difficult operations that might endanger the notion of virtualization. So, as we said, when the application, say, does I/O, it's going to make a request to the operating system, and the operating system is then going to go through and do the I/O. Well, you can change the way the operating system calls the I/O to make it a procedure call to a hypervisor to do that. As similarly, when you actually go from the application into the operating system, you might actually replace that transfer into a call to the hypervisor to change what's going on. So, for example, if you're worried about protection, you could change the protection of the application as you switch into the operating system. So we get some additional terminology coming along. We have inside this hypervisor, we have requests coming in to actually perform the operations of the sensitive operations of the operating system. And those are called hypercalls. So we have a hypervisor, we have hypercalls into the hypervisor, and then what we do is to adjust what's going on. Now, if you have exceptions, you have interrupts and other things, you have other issues going on that need mapping, and there will be extra code, anomalisms, to actually do the transfer to make sure your virtualization is a solid virtualization. Examples of this are Xen, KVM, Windows 4 LAN, 9X. They are all examples. If you look at that diagram, what you see is that you have an application, you have a modified guest OS, and now you have the hypervisors under it, the hypervisors supporting all of those. But obviously, if the operating systems are modified, you can obviously share some parts of the guest OSs between those applications, but other parts which have been modified you may not be able to. There is more room for sharing. There is a cost. There's the cost of these hypervisor hypercalls that goes on, and that will add to the overall time. So an alternative route, rather than have modified operating systems like Xen and so on, is to actually change the operating system to support different types of physical servers and provide an interface on the operating system that basically enables a virtualized set of servers to run. In this diagram, what you can see is how to create services on top of the operating system providing libraries to those servers which actually provide the virtualization for each of those servers. So the server now will be responsible for interpreting the sensitive requests of the private server. The operating system itself will try and avoid, it's programmed to try and avoid making conflicts or having conflicts between the different virtualizations. So this approach is used in Parallel Workstation, in Linux Vserver, OpenVZ, Solaris Containers, FreeBSD jails, and changeroot. It is less secure than the previous examples. Clearly, if there's a problem with the operating system or a problem with the interaction between the physical server and the operating system, there is nothing to stop intrusions and other problems occurring inside this system. However, if it's all coded correctly, what it can do, though, is to remove all of those levels of interpretation, all of the hypercalls, and what you end up with is a much more traditional operating system that we know how to optimize, we can execute very quickly. So there's some pluses to this and there's some difficulties with this. Now, what we'll find is that in lots of circumstances, these pluses actually outweigh all of the security issues. For example, let's suppose you are building a server and it has multiple different threads, multiple different pieces of the services, as in, say, a cloud. Because it's all operating in the same domain with the same security, essentially, they're all doing the same, working for the same organization, it's not clear you need the protection between all those different pieces of all those different servers, all the different containers for what's going on. So in that case, this might be a much, much better solution than going ahead and building a real virtual machine, either with hardware or with the interpretation. So that's another reason for looking at this whole spectrum, that there are different reasons for doing different things. Let's map these together. On the left-hand side, what we're going to do is list the hypervisors, what their overheads and so on are, and on the other side, I'm not sure which side, I guess I chose the left side for the hypervisor, the right side for the containers. As we compare that, first thing you come up is, well, you have hardware, and then you're building from that hardware many virtual hardwares, and on top of that, you're running many operating systems. Now, compare that with the containers, and this sort of building the interpretation into the operating system approach, there you've only got one real hardware, you've got no virtual hardware, you've got one kernel, you've got many user space instances, and what's giving you the effect of user space separation is really the kernel. Let's go back to the left-hand side, the hypervisor. It's very versatile. It can run lots of different operating systems. So you're going to have Windows running at the same time as Apple OS X, at the same time as Linux, all on the same box. This is not possible on your container side. The containers, they could be tuned to take applications written for specific operating systems. The libraries might be different, but on the whole, they're not going to be able to support effectively all the different operating systems you get, because there's some really radical differences sometimes between the operating systems. You do, however, get a difference between these two, hypervisor and containers, on how much density, what's the effectiveness of all the bytes you're using. In the terms of the hypervisor, you've got all this interpretation. You don't need extra code in the operating system to do things. You do have the hypercalls, though. You are going to get performance, you are going to get scalability. On the other side, on the container side, what's going to happen is that you don't need so much code, and the applications don't need so much code to do the sort of things they're doing. So you've got a higher density, if you like. You can get more apps into a set of container systems than you can on a hypervisor with its apps. And you get natural page sharing because of the normal caching and other operations inside the system. Your page sharing is going to work for you. It's not going to work for you with a hypervisor. Lower down, as we sort of look at the features of trying to support multiple machines, you are going to have hardware in hypervisors that will accelerate some of the difficult tasks that you've got to do. So if you're doing context switching, you are going to have hardware to support that. If you're going to play with the virtual memory mappings, you are going to have hardware to do that. On the other side, with the containers, you have less flexibility, less possibilities of changing things, and the result, because you're running effectively with just sort of a simple operating system stack, albeit modified, you get almost native performance, and there's not really much observable overhead. So containers, they're going to share host OSs and drivers. They can have small virtualization layers that make sure everything's distant. They naturally share pages. They're not completely secure, but on the other hand, they're getting very, very close to being a good protected environment. The hypervisors have separate OSs. They have virtualized hardware. Their hardware emulation requires additional state. They have trouble sharing OS pages, so they often don't do that. And they are much, much better at trying to separate, if you like, the worlds of applications and their applications from the other applications, because there is effectively a large wall between them. Containers are more elastic than hypervisors. So if you want to create containers, since they have such a small footprint in the way they're built, they're using less software, they don't have so much impact on the performance, you can get many more containers in a machine on a core than you can with hypervisors supporting operating systems in virtual memories. The container slicing of the operating system is ideally suited to the sort of things that we're going to find in clouds. So when you build, let's say, application support on the clouds for big data, then you may implement that with lots of threads on lots of different machines, lots of different cores, all in the same machine. But you can utilize all those cores much more easily because they can actually just sort of slice quickly from one task to another. They don't have to go through all that mechanism that we were describing with the virtual machines because of the nature of the application. So that sort of system is much more sort of mappable from a cloud point of view onto containers. The hypervisors, I won't say it's the only advantage, but the slide does. Only advantage in infrastructure as a support is supported by different, it allows you to have different operating system families on one server. So if you really do need Windows to be talking to Linux, you can do that all on one machine. That's a sort of interesting case, but it's not a really demanding case for, shall we say, not going down the container route. So mapping all this out, we could compare increasing efficiency with increasing isolation. Increasing isolation is along the bottom, efficiency is the height. So if we want things that are very efficient, then Linux and Windows are great. If we want to isolate application software, one from the other, we can go to something like a security kernel, and one of those is called SE Linux. And you can see it's slightly lower performance. What it does is to check everything that goes on communication-wise between the applications and the rest of the machine. In terms of SE Linux, it's using label systems to do that. I won't go into that here, but those labels, interpreting labels, has a little bit of overhead. Similarly, you can put BSD jails up, and when you put BSD jails up, what's happening with the jail is that it's checking your access to file systems to make sure that you don't exceed the authorization to access everything. You'll be constrained to a piece of the file system, and it's going to check that every time you make a file system access. Not just check it from the access tables, but it's actually going to check it from what's open, what's in your tables, what's in the cache, and so on. So BSD jails would also impose a little bit of overhead. Then you get to the container systems, Vserver, OpenVZ, Solaris 10. Those will be faster. What they're doing is sort of really threading between multiple instances. They're keeping their memories separate. And as I said, this is all done by having the library a little bit more sophisticated, a little bit more checking on what's going on, and the communications through the operating system also checking and keeping the identities separate. So the Vserver, OpenVZ, Solaris 10, they're all having more overhead than SE Linux. So we move across, we get to the Zen and VMware type of implementations, where what you're doing is partial virtualization. You're interpreting the sensitive operations that are being executed. So when, as I said before, when the client wants to do I/O, you're going to check it's dropping into its operating system. You're going to check again when the operating system wants actually to do the I/O operation. And all of that is going to add to your costs. It gives you more isolation, but again, it detracts from the performance. And then you can have the machine efficiency. You can put extra machine instructions in there, virtualize everything, and you can build systems that are really very, very difficult to break the isolation of, but you're going to pay a penalty. You're going to have more hardware. You're going to have extra instructions. You're going to have extra code to manipulate that, extra instructions to keep track of all that security. And so it's again, not as efficient as you would like, especially not from the point of view of how much hardware you're using to execute the instructions. So looking at it from a feature viewpoint, the hypervisor allows you to have multiple kernels, allows you to, the hypervisor was the partial or full virtualization, allows you those multiple kernels, allows you those to load arbitrary modules. They're still going to be protected because it's a sort of enforced protection, allows you to give administration to the operating systems that run to somebody, allows you live migration, and you do have actually there's going to be a difficulty anyway. When you want to update, when you have to change the system, modify it, put maybe fix a bug or fix a security problem, you have to worry how you're going to do that in an environment that has lots of threads and applications running. On the container side, you can't have multiple kernels. Loading arbitrary modules is not possible. You can have a local administrator, you can have live migration, and in some systems like Zap, you can actually do the system update. It's a lot easier because there's not so many systems to actually update. There's only the centralized system. The previous lecture gave you an introduction to all the different virtualizations that we're going to discuss, and now I'm going to take each one and just go through it a bit more in detail. We can come back to some of the points I made in lecture 1. I want to stress, though, some other aspects of this, like maintainability, ease of containment, and so on. So we'll present some new material here too. Let's look at Zen. This is a picture of the guest VM, and what we're expanding is just one of the VMs of a system and having a close look at what's inside. What you can see is that most of the application space is pretty much what you would expect from a Unix, and the processes, the organization, the ports that are available, all of that stuff is mapped so that pretty much anything that you would have written for Linux would be fine to run in Zen. It will all carry over and execute, so there's no real impact on the users whatsoever. We have processes. We're going to have a init process when the thing boots up, or when the application starts. We're going to have /bin bash, your favorite shells. We're going to have HTTP. All of that stuff is just typical usual, just standard code, and it's not going to be modified at all. The file system, you're going to have the same type of file systems. And now note, you're going to have lots of users having /home or /root. Each of those instances, those guest VMs, are going to have a root. And those roots aren't going to interfere with each other, which of course they would have done if you'd put them on a single box with Linux. So the guest VM is going to take care of that. It's going to give you that whole sort of Linux feel. This is the whole machine for you. Similarly, if you look at the ports, the port numbers like port 80, port 3125, they're all going to be your ports. And if you use them, you're going to think that you're the sole person actually accessing, sending I/O through those systems. You're not going to see any of the other users' applications on this system. So the magic doing this, as we described, was the guest OS and the way it has been modified to provide the virtualization. So the guest OS, much of it is going to be the same as your normal OS, but there are going to be pieces of the operating system, sensitive operations in that operating system, that have been modified in order to be able to give you the virtualization feel. And in particular, we can talk about some of those. Access to the I/O clearly needs to happen, but if you look at those pictures, well, /root, when you access the disk system, something's happening there because other people could be accessing their routes, and it's clearly not all the same route. Similarly with the ports, you're accessing port 80, somebody else might access port 80, and you would like those accesses to be separated and contained, if you like, well, isolated, so that everybody's happy. So the answer of how that all happens is in the sensitive operations executed by the guest. What they're going to do is actually call down into the hypervisor, which is why we've got so many teeth there, sort of showing up and down interactions, to interpret what's going on. When we get, say, a write to the file system and it goes through /root, we're going to interpret /root and the file hierarchy differently in this guest VM from in the other guest VMs. And what the hypervisor is going to do is to map this particular route to a different part of the disk so that there aren't collisions when the file system's changed. Similarly, when you write to port 80, what the hypervisor is going to effectively do is intercept those I/O requests to the ports from the guest OS, interpret those port IDs so that they don't map on to the same ID as all of the other processes, and then map it through the network interfaces in some manner. So this whole environment can be built, or is built, it can work very well, but it requires some fancy footwork, especially down in the driver domain. What you see happening is that the guest OS, when it's talking to the drivers, because it could talk to the disk, it could talk to the network, it could talk to other, well, RS-232 type of hardware, what you have to do is to get some interpretation of that I/O request that will work on a shared machine that doesn't interfere between all of the applications. Typically what happens is that driver domain has a special sort of isolation box, shown here as a driver domain, and what it's going to do is carefully assign pieces of the disk to the guest OS. It's going to carefully assign the I/O structures, the ports, and so on, so that when port 80 gets to it, it's going to map it to a different port for that box, and then do the actual I/O. Oftentimes what will be then occurring is when you get information coming backwards and forwards, that driver domain has to work in both directions. It has to take what's coming in and map it back. You've seen a lot of this already, probably. In many ways, well, the driver domain working with the networking, you've seen some of the ways that the networking devices can interoperate. If you think about NAT boxes and what they do, in a sense, the driver domain is doing sort of no difference. It's taking addresses and changing the addresses so that there aren't collisions. So if you look at all these components that we've got in Zen, what are they all doing? I've described how it works. Now let's focus on what it's doing. This box hypervisor is providing resource control. What it's going to talk to is the driver domain. It's going to map virtual devices across that driver domain. You're going to have some mechanism for organizing the CFQ call for disk inside a PC. You're also going to have to manage the HTTP for a network access. So those parts are in that driver domain issue. Then you're going to have an I/O path where the process is communicating to the guest OS, and then the guest OS communicates to the IDD. That's the I/O part of it. It's going to have to be isolated from all the other machines, all the other virtual machines running on Zen on that same platform. Then the hypervisor is going to be responsible for security. It's going to be providing access, physical level control. It's going to be looking at PCI addresses and make sure they don't collide. It's going to have to look at virtual machines, virtual memory, and make sure the virtual memory is mapped so that the physical addresses don't collide. Then we dig down and there will be a resource control, and somebody's got to decide how to schedule all of the different parts of this. So the hypervisor is going to do that. It's going to schedule the VMs. It's then got to talk about allocating resources, because the VMs will require memory space, real memory space, virtual memory space, and then disk space for the VM. All of that's got to be done by the hypervisor. And last, you've got scheduling that's occurring. You're going to have to schedule the VMs, but you need guest VM and IDD scheduling for the I/O. And of course, because this is Linux, you've got two levels of scheduling inside the guest. You've got that for the applications, and you've also got the I/O scheduling that goes on. So another complicated part of the hypervisor. So what you see here is an architecture that handles very nicely the separation of guests and their operating systems. The conflict oftentimes occurs down in the driver domain. It can be overcome by changing the addresses, changing where file systems are mapped. Now we're going to look at containers and how containers and jails and other things can operate. Our next presentation is about Vserver 2 and basically providing a guest VM in a sort of container-like situation. What we've been steadily moving towards is a lighter weight execution environment for the applications, but one that separates and isolates the applications in their use. And what we saw before was that even if you do this, you have to be careful when you're doing I/O and when you're actually accessing the file systems, because you could get collisions and you need to isolate those. You could, of course, just use libraries to do all of this. And in the Vserver 2, the implementation, early container type of implementation that it's got, what it does is just that. It's a guest environment that you run your VM, well, you run virtualized in, if you like, your application in there virtualized, but it's really using lots of different support systems to provide that isolation and separation. Although if you are a persistent hacker and want to attack this, then it's going to be easy to do. So if we move towards this system, looking at what are all the pieces doing? We have now an operating system that is doing resource control. It's going to do just your regular types of things. So it's going to do your CFQ. It's going to do all those sort of normal sorts of activities. What has to happen is the libraries are going to have to do the separation from one user to another user. Similarly, the isolation, you're going to be able to access logical objects. If you're going to separate out those, then again, you have to be able to determine what's being accessed and prevent one application from accessing something else. In this case, it's often used as what's used as the BSD jail mechanism to try and separate out the file system for one user from another user, so that the users would be mounted in different parts of the file system with change root, and then the jail will be put around it so that you can't get below and see the other file systems for the other virtualizations going on in the system. And of course, you can do that similar types of operations with I/O devices. They're all mapped into a tree structure, and you can isolate those tree structures and map those into the different guest virtualizations. Here you've got the I/O path, and one of the things that the operating systems do is make sure that the I/O paths are individualized to each of the different processes and threads in their containers so that you can't actually see from one container to another. And so that's got to be a modification in the operating system. When the processes do I/O and they're talking to physical hardware, you've got the possible of interaction between the different guest VMs. And so what you need to do is to schedule that I/O so that they all occur in different times and don't interfere with each other. And again, that gets back to putting mechanisms in the kernel to prevent that from happening. Inside the system, you're going to take you're going to have opportunities because it is just one system. It's not multiple virtual machines. It's not a hypervisor, not a complicated system. What you can do with the paging systems and so on is to provide optimizations in the way that the paths to access data are used. So in this case, one of the issues would be, well, you would like the virtualizations to be able to write to disk. You would like them to be able to read from disk. You can provide a copy on write type of access to a particular file. When it does write, it will write to a different place in the disk, preventing interference between the different virtualizations. So having a good file level copy on write is what's put into this Linux VM system, this Vserver Linux system, to prevent processes interfering with one another. So that particular piece of code is about 8,700 lines across 350 files. The emphasis being it's small. So what we've done is to get rid of some protection issues, some security issues. You're not going to get that completely done. It's going to give you the sense that you're working on a separate machine, isolated, but if you work hard enough at it, you can get around the abstractions and you can actually cause trouble. So it's a lightweight implementation, as you would expect. It's actually fairly efficient. It will work on all sorts of different architectures. This Vserver type of approach is really very efficient. It's written, when you look at the Vserver, it's written in terms of providing servers to different applications. So the terminology is slightly different from, say, the complete virtualization space. So you have to sort of mix and match the terminology a bit. So here we've got a comparison now between Zen and Vserver. And if I get some of the terminology wrong, I'll probably confuse everybody. But the terminology is a little bit different between the two, so it's easy to do. So Zen 3, Vserver 2, level of virtualization. Well, Zen is sort of physical, is giving you sort of complete identities of the codes. The Vserver 2, it's logical in the sense that if you start writing code that addresses real memory, you're going to go right the way through the abstractions and you can interfere with other processes on the system. I'll give you an example of that. If you do a fork bomb on this type of system, you can bring everybody down on the system. There's no protection for anybody because you're all running on the same hardware. It's all the logical separation. It's not really physical separation at all. Moving down a bit, resource control. You still got the same problems on both systems, that where you're doing the I/O is where you actually get complexity. You're having to share resources, and you need to have address names for all those resources. And so you've got to accommodate that in both systems. It's the same problem in either. The scheduler, with the hypervisor, you're going to have two levels of scheduling, one at the hypervisor level and one at the guest level. You've got the guest operating system and then your guest, so you can schedule there. You've got two levels of scheduling. But with a vServer, it collapses that. And again, to give you a sort of motive for thinking about this, if you think of in the Zen, if you have a guest that's sort of caught in a loop doing nothing, you're still going to spend cycles actually executing that guest. In the vServer, it's all sort of one level. If you're executing along, you're going to notice that sort of behavior, hopefully correct it with timeouts and other things, but it's a different way, where it's a different place to have to look for that type of bad behavior. What you would have clearly liked to do, of course, is to, if something gets caught in a loop, you would like to identify it, kill it off, and not have anyone suffer from that. In these two different systems, what you can see is you can really, well, you have to implement timers and other things, but it's really difficult to avoid the wastage that you get from that sort of problem. It's not exactly easy to solve, and in the Zen, you're going to have to look at both levels to see what's going on. In the vServer, you'd still only look at one. The I/O path, there is a slight difference here, and this is worth talking about at this point. When you're doing the Zen, what you're having to do to separate out the conversation going between the guest operating system and the hardware is to copy data into the kernel ready for use on the I/O device, and you can't schedule it until you actually get control of it. The resulting schemes involve 3 transfers, and it's very difficult to actually do an optimization. At the vServer, because everything's flattened, you don't have separate guest operating systems doing things. You only got one operating system. You can actually schedule the operating systems a little different, so that the I/O path only needs 2 transfers. So that's slightly better. It will obviously work on all sorts of things. This is just some performance comparisons, and what you are seeing is just sort of the advantages and disadvantages, Zen versus Linux versus the vServer. The key thing to note is that the vServer is actually, I mean, it's a very Linux system. Behaves very much the same. The green and the brown are almost the same performance, and so you're not losing very much that logical virtualization, but you're not really sort of, on the other hand, gaining much logical isolation, physical isolation. You're getting logical isolation, but you're not really getting any physical security, physical isolation benefits from it. And this is a sort of scaling things. But, well, overall what you see is as you increase the number of Zen virtual machines guests, the performance drops a lot faster than in the vServer, and that's simply because Zen is using a lot more resources on your computer than the vServer. The vServer has a very sort of shallow footprint, mainly because it's using all of the standard Linux threads and other mechanisms, and it's using very simple protection schemes like the jails and so on. So that's what you're getting with the vServer. Well, we talked about Linux. What about BSD and what about other Unix systems? Solaris was a leader in Unix. It took the BSD systems, made them very popular, and then improved upon them. So we should look at Solaris perhaps as a sort of example of how the Unix as opposed to Linux world dealt with virtualization. And Solaris Zones were a sort of early type of virtualization. They came in about the same time as Linux, but they were, this is all before current modern events and before the cloud. So what were Solaris Zones? Again, very similar concepts. You're trying to provide virtualization. In this case, you're using, yet again, virtualized operating systems. The operating systems are going to provide that virtualization. It's going to be a logical sort of separation of systems. You're going to be able to share files, processes, and network interfaces. And one of the nice things about these type of zones is that they actually accommodate sharing them, though sharing between zones as opposed to isolating completely between zones. So they'll actually do the mapping that's necessary with the namespace and so on to allow that sharing to occur. The scaling and sharing can be configured basically as you need it, and individual zones can gain files and configurations. To situate the whole thing, there's a global zone, and then you can create other zones from that to do different tasks. So if you were going to build, say, a very complicated web service type of operation, you could create that in a zone on a machine, and then you could subdivide the zone. You could have other zones that handle just specific things like executing the user scripts coming back from HTTP. So there's some benefits, a little bit more control perhaps than the Linux world, and the whole thing taken into a Unix world. So there's a global zone. All Solaris 10 had global zones attached to them, and this global zone is bootable from the system hardware. It's just part of the system, and contains all of Solaris, and can contain additional software, anything you want to install. The local zones are a subset of the complete operating system. If you like, what you're saying is, well, I've got everything, and now I'm going to provide particular environments for my services that I'm going to provide on Solaris. So I will subset what I've got in the big zone for that purpose. And so you just allocate in those local zones particular pieces of the whole zone, and you can actually add non-shared packages if you want. The local zones, if they don't have a sharing arrangement specifically, they have no awareness of the other zones. It's almost like a tree, and as you move down the tree, you inherit stuff, but the leaves can't talk to each other. So a local zone can't install, manage, or uninstall itself, and it can't do that to any other zone. It's got to be the higher up the hierarchy zone that does that. So you have a zone administrator that manages building these zones, shutting them down, allocating zones, and starting scheduling. You can see it's a very hierarchical approach to the problem, very reflective of the way that Unix thinks about the world. The zone administrator allows you to allocate devices and allows you to plumb the devices together, so you can actually create arbitrary structures and communications between zones if you want, but that's all sort of programmable, because it would interfere with the isolation notions. And then you also have managing the file systems. You can share files between zones. That's again on a zone administration, so it's a little bit more flexible than we were talking about before. The scheduler manages thread management per zone. The threads are little processes. They're not the Unix processes, they're the individual threads. can do context switching between the threads. Doesn't change your VM. They all operate within the same virtual memory. So the kernel threads are doing the work on behalf of the zone, and they're all owned by Zscaler. So you have a root, again, which leads to all the individual pieces. The zone file systems, you have two different models of how they build the file systems for the zones. One's a sparse root model. Minimum number of files from the global zone are provided to that zone, and shared files are mounted via read-only, and then they loop back. So that approach, you just get a very, very sort of limited view of what actually is in the whole system. The other approach is to give you a whole root model. There's no dependency or shared file systems. What you're getting is a root, and then you build things up from there. And I think that's pretty much what I want to say about that. Zones have visibility to each other via network interfaces. So if you want to talk between zones, you can communicate using sockets. You can obviously communicate through the Ethernet if you really want to write all that code. The global zone administrator can modify those interfaces and routes so they're reconfigurable. And then you have the communications being in the global zone, you can extend and so on if you really want to. And the same thing with the sort of failures, events, and so on. They're all configurable from the global zone into the local zones. So one of the key purposes of this system was actually to control resources. So there is a rather large amount of effort in constraining how much physical memory, how much time, how many threads, how many kernel pages are being used, how many are mapped into real memory. All of these things can be capped and resource managed from the global zone to the individual zones. So you can actually sort of place restrictions on one of these zones you've built so that it is constrained to operate within a set of limited resources, won't exceed it and won't place too much handicap on the rest of the system. So that's this Solaris zoning system. Now let's move on to containers. Okay, so let's look at some Linux container app. And now, I have to confess, there's multiple different implementations, and so we're going to look at different implementations of containers in Linux. It's a progression. Actually, what has happened is there's a sort of accommodation performance against all the things they would do, and the security that's involved, the protection that you get, and so it's a sliding scale. This OpenVZ is an early container system, and so we will talk about it. What you're getting is both the host and the guest as Linux. You're getting a minimal sort of performance parity for OpenVZ, 1 to 3%. So you really couldn't probably tell the difference that you were running OpenVZ as opposed to running a standalone server. And what it provides is a whole slew of different implementations, virtuoso containers and so on, as sold by Parallels. Their claim is that this system is so lightweight, so organized, and so sort of performance enhanced or non-preventing, that you get 300% more virtual servers than if you went with a hypervisor. And 300% more virtual servers turns into a lot of cache. So Virtuoso, this is obviously a big sale in cloud computing. So here's some hype. The claim is that OpenVZ performs a lot better, And to show that, what they do is to show the density, how many different instances of OpenVZ can operate, how many applications and virtualizations can operate at the same time. And you can see the graphs. Obviously, it looks very pretty. I'm not going to comment on it other than this is meant just as a placeholder for you to remember. The claim is with the container family in Virtuoso, not so much overhead, you can scale it, and this makes it a really good, effective cloud performer. You can look at all sorts of different issues like the store performance, and obviously you'll follow the hype, but what you see is that OpenVZ is doing a lot better. And again, you can look at store response time, how much effort is overhead getting things out. Naturally, it's better than Zen as a comparison with other types of systems, and you see the wonderful benefits of going with that particular system. But overall, I think there are sort of probably stronger issues about why you might choose containers or why you might choose virtual machines. And some of those might really be about what type of applications you're building. This is, I mean, it's great, good stuff. You can build really lightweight things, but on the other hand, you have to take into consideration how much protection are you getting, how much security, do you get all the management? And so as you look at these figures, yes, they're great, but just, in a particular context, they're going to be perfect. In other contexts, you've got to consider what your applications are doing. So here's a kernel. It manages the namespaces, virtualization, isolation, just like the other guys. It provides you C groups and resource management, and C groups become a particular sort of feature in containers and in Linux containers. And what we'll see is when we go to the next generation of Linux containers, C groups is also a really sort of fundamental building block, because it gives you ways to manage authentication, authorization for people when you actually want them to communicate between different virtualizations. You have in this system, because it's such a low footprint and there's little amount of state, you have the possibility of actually migrating applications from one container to another container, perhaps on a different system. So you can checkpoint the applications, restart them, because the emphasis has been on this sort of lightweight approach, this uniform approach, and making it all Linux. It becomes very easy to do. There are a variety of tools to control your containers so that you can move them and do various things. There are templates, pre-created images for fast container creation. And the reason for mentioning this is that we are going to get into a situation with our clouds where actually building things becomes a really critical issue. If you can build structures fast, you can build web servers or whatever it is fast, then you can make them elastic, you can make these systems elastic, you can have lots of users come along, just get temporary systems, put them up for just how long they want. So the templating approach is kind of a very interesting development in the notion of containers and how they're all managing the virtualization and providing easy ways to build things. That's going to, as you will see in the later parts of the course, that is a critical part. So each container, you might recognize some of this again. It's going to be built on change root, and it has system libraries, applications, and virtualized procedures and systems. The actual /proc/sys are virtualized, so you see your own from your thread. Has virtualized locks, clearly needing some software libraries and stuff to do that. The process tree is all sort of organized so that you don't see anybody except yourselves. It's fully virtualized. Your init PID is 1, which is very comforting. The network, the namespace, you get your own IP addresses. They don't interfere with other people's IP addresses on the same machine. And so the whole sort of part of it, which deals with the networking and with the cloud part of it, because most of these systems are networked, is handled by these libraries. The devices, if you want them, can be gated across to real devices like network interfaces, and that can be managed through software. There's IPC, that's inter-process communication objects, things like shared memory, semaphores, messages. They're all sort of virtualized as well, so that sort of enhances your abstraction, makes things a lot easier to program. The resource sharing has limiters on it, resource management. They have bean counters to actually count out how much you're doing different things for, and you can control those. You can set limits. You can run there's a fair CPU scheduler, which is kind of interesting, a fair scheduler. It allows you to set shares and hard limits. You have quotas and also disk I/O priorities, again, so that you can basically create your environment for your container and have it operate in pretty much isolation from, at least from your point of view, from all the other containers on the system. We talked about migrating processes. That really requires you to have systems that will allow you to save the state and then sort of start it again. So there are mechanisms in this to take running processes and passivate them, essentially take a copy of what their current state is and stick it in a file that you can use later on. That will record all the open files. It will record all the network connectors, all the buffers, backlogs, memory segments, making it very easy to sort of have a managed system where you move parts of your servers around over different systems. You know that the sort of notion of elasticity, though, is not there. You're going to have to program that. But you've got lots of primitives there to actually build such things. The CT state, well, once you save the state, you can restore it later, and you can restore it on a different server. Very nice for debugging and so on. Well, having introduced this virtualization and a spectrum, I think we should now look at what really is a promising way of organizing your cloud structures and still taking advantage of sort of lightweight operating system-based containerization. And for my preference, LXC Linux Containers is probably one of the easiest places to get started building things and experimenting. And it also leads into lots of other interesting pieces of software, which will be in my MAAS Metal as a Service lecture later on. So LXC, what are they? Where do they come from? What we've seen in other places, lots of different sorts of container and zone and well, solutions to trying to provide isolation, but LXC is really the dominant one for Linux. It gives you better isolation. It's a lot better than just trying to use change root and the jail. There are other features in there to give you that much better isolation. It does a lot of mapping of names and so on. It's low overhead, minimum resources in terms of RAM and hard disk space. You don't have to implement a guest OS to get the virtual machine, as opposed to VMware VirtualBox KVM. You can just download Ubuntu, and it has it all in there as part of the Ubuntu operating system. So it will run application services at the native speed of the the hardware, just as if you were running on the regular Linux. And that's a huge advantage in terms of knowing what you're getting by doing all of these aggregation, building servers, and so on. There's support for Linux containers in libvirt, which makes it really easy to get used to. Linux containers work well with BTRFs, and there's no special hardware required. It will run on 32, 64-bit processors. The Linux containers, these are all open source, so you can actually see how they work. And unlike Zen or OpenVZ, you don't need to modify the kernel to run these sort of containers. They're just sort of built from the libraries. So one way to sort of view this, and this is a sort of built on CentOS, this example is built on CentOS. Let's look at some Linux containers. We'll use Ubuntu to boot them, but then we'll have CentOS clients on top of the system. And what we're going to do is to map them so they have the right libraries that they'll execute on Ubuntu, even though they're CentOS built clients. What we're going to do is to step through some of the commands. I'll try and describe their basic essence. But what you'll see is that it's a sort of typical Unix, Linux command style construction. And once you've mastered the commands and you know what all the libraries are and so on, you can build pretty much all sorts of different interesting implementations. And the reason I mention that is that this really then leads to the notion of programmatically building your own environments and actually sort of managing very, very interesting designs in a programmatic manner. And we'll talk about that in MAAS and in Juju. So here what we're going to do is to create a control group, file system as the root user, and we first start out by making a directory with a particular C group. We mount that directory and add to FS tab, our file system table, so it'll be there after a reboot. So we can just go in and edit that file system table and add the item none C group default 00. Then we can go and get the applications that we might want to run. And here we're sort of taking advantage of going off to get from the library. We do an apt-get install libvirt bin with a DB bootstrap. We need to download and install this package. So that's the next step. LXC 0.721 AMD 64 deb is the description of it, and what we're going to do is to download that and install that as a package in our system. So having done all that, we can now create a container. We create a path to the container, and then we instantiate in that the initialization for CentOS. We're putting that in /etc. Create a root file system, copy files that we want from where we were working earlier. Okay, so we can then go and create a file for creating and setting up all the default devices for the containers, and we would do that by editing user local bin LXC config. Okay, we want to set up our containers so we can change directory into the root file system for the container we want to build. In this case, we're trying to build CentOS, so we can change directory to the CentOS in LXC, change directory to its root file system. Once we've done that, we can configure the LXC and also sort of fix the /dev for it. Once we've done that, then we can restrict what we can access by actually change routing into that self-same directory. So that's the next section. change root, CentOS root file system, and now we are protected. We've sort of isolated ourselves from the rest of the system. We can set up the root password for the container with password root, started removing some services from running, so we can sort of go through, edit what is actually in this sort of container. So we're going to check the configuration, make sure SSHD is on, HTTP is on, XINetD is off, and sendmail is off. And when you're sort of finished doing all of this, you can type exit, and now you've built this container with all of these properties, with some of the services that normally would be there turned off. This just shows that if you need to, you can destroy containers just as easily as you can create them. Once you've built the containers, you can start the container. That's the LXC start command. You can stop a container with an LXC stop. You can connect to the console, which is rather nice. So you have your own hardware, if you like, to actually talk to all these different containers that are running. And these containers are really sort of have their own terminals and can go asynchronously. You can check your configurations, you can list the containers. So there's a whole variety of LXC commands you can run to actually sort of manage the containers that you've built. But again, as you've built these things, you built it isolated, and you kind of went there and did it, and then you backed out, and you can still run and manage these things in this pretty much the same environment, which is very interesting. So containers are very useful in building applications, in building parallelism, and getting things to switch from process to spot, or processors to switch from process to process very fast. They're easy to write, relatively, and a great way of packaging ideas into threads that interact. They're not so good at security, not as good as the virtual machines, but nevertheless, they are actually sort of dominating a lot of the way that clouds get used. So today, what I want to emphasize is how do we turn that idea of containers into a production environment? How do you make sure that the software engineering is right? How do you reduce the effort to produce these container systems? How do you make it really possible to take the code that you write in those containers and move them from one operating system to another? What you would like to do is have it miraculously work on all the different operating systems that the user might bump into in the cloud, the same sort of organization for the same servers, and have it all operate. But we know, of course, that all of those machines are different. So I'm going to introduce you to this cool notion of Docker. So Docker, the best description of it is as a way of making all the containers actually sort of uniform, following an API effectively. What they do is to wrap up your container software in a whole complete, well, it's a container, whole complete container, but formalized in such a way that it has all of the parts that you need to run on all the different systems you're likely to meet. So what it does is to get a complete file system that contains everything to run your code, you run your runtime, the system tools, system libraries, anything you would want, and it packages it together in your container along with the code that you had written to do all this multi-threading. This guarantees that the software will always run the same regardless of which environment it's running on. So now your Docker is actually sort of operating in multiple different ways. It's not only allowing you to write that thread software, put it in a container, but it's building that container so it'll interoperate on all sorts of different architectures and all sorts of different hardware. So it's becoming really valuable. It not only does that, but it also makes your life easier, because now when you want to put your software on a machine, instead of having to write scripts and code to build the system there, it automates the deployment. It will actually take all those applications inside a container and put them inside the machine, link them to the right libraries for that machine, and boom, all of a sudden you've got your threads running on that system and you didn't have to do very much. It's an additional layer of abstraction. It abstracts the operating system and the libraries and makes them all look the same. And the way it does it is to introduce its own set of APIs that you write to as you write your Docker code, but it then interfaces those APIs down to all the different operating systems that you're likely to run your Docker system on. So it effectively does virtualization on top of Linux. Doesn't matter what the Linux is, what sort of drivers it is, or who actually is Red Hat or Ubuntu. What it's going to do is to allow your threads to run on those systems without having to do anything. And it automates it. It makes it really easy. You just press buttons, well, code, and away it goes. So let's have a look at that. So its origins are way back in the days of Hadoop and things like that. We were building platforms as a service. People wanted to build all sorts of unique projects. Solomon Hykes started off in Docker. He was looking at building something called DocCloud, a platform as a service company. So he wanted to sort of he had this vision. Okay, you want Hadoop, okay, install it, runs on any system. How does he do that? Well, he packaged it up and you invented Docker, or a sort of Docker to do this. The first real effective version of this was released in 13th March 2013, which is kind of a nice number when you think about it. It provided a lib container library that mapped the libraries so you didn't have to change your applications. It was written in the Go programming language. Now you probably know where Go comes from. That's a Google effort. And history was made. From then on, life got simpler and simpler. And what you see is that there are versions all the way through even to this May in 2016, improving that notion of providing an environment for your threads that's portable and automated. So the team putting it together, the Docker team, it had widespread industrial support. And so the Docker container system that you've got actually will map to a huge variety of different Linux systems, and it'll be very reliable, very flexible. So let's go on and see what Docker looks like. So it has, as I said, a packaging aspect. You've got your threads, what you want to build. What you're going to do is to build it inside this Docker container. And the way you build those Docker containers is exactly the way you saw for building ordinary containers. But now the Docker container also contains libraries, and the lib container is one of them. libvirt, which virtualizes the Linux kernel, so you don't have to know the details about the kernel. And it also separates you from other Dockers running on top of the kernel. It operates a bit like virtual machines, but nevertheless, be aware, security is not as good as on virtual machines. But if you want to build a large-scale server with lots and lots of pieces in it, threads interacting and so on, you don't care about the security because it's all yours. What you care about is being able to organize it the right way, and that's what Docker allows you to do. And then there's some other libraries. There's LXC, which is the container mechanism, which we talked about in the previous lecture. And then there's a system daemon spawn, which actually manages how the Docker is set up and what runs. So those are the components, and they all sit on top of your whichever Linux kernel and make everything work. And it doesn't really matter if you want to use SE Linux because you want security from the outside world, you can use it. If you want to use capabilities, if you want to use C groups, if you want to use Netlink, it all maps from your threads through the Docker to the Linux kernel. So, what can you build? Well, your applications would sit on top of the normal set of libraries, or what you would expect is the normal set of libraries. And here I've sort of shown, you've got app 1. Let's look at app 1 here. It's going to need certain libraries to execute the system code, and it's going to need certain libraries to map it down onto the system level. And there might be binaries that you need to run, like file systems and so on, that are specific to your particular set of threads. And so that will be contained in the bins. So that package is what you're interested in having run, and it's all sort of virtualized for Linux. The Google engine sits, or sorry, the Docker engine, Google engine, the Docker engine sits here and takes that code, maps it to whatever operating system you've got, and the infrastructure under that the operating system really supports. So if you want a particular file system and you've got some binaries up here for the file system, what it's going to happen is it's going to get mapped down to the file system here through the Docker engine, and all those read-writes and everything else are all going to be mapped so that what you expect to happen will actually happen. So this mechanism effectively isolates the way you have to write your application, and you can think really that what you've got is your Linux machine sitting under here running your app 1. And of course, your girlfriend or your boyfriend might be running the same application, or different application, same application. They'll think they've got a whole Linux system to themselves, but they could be running in this package, and they would just see what they're doing. Similarly with this might be somebody different. So this overall is a real sort of interesting lightweight mechanism to do things. It's lightweight both threads, and it's lightweight from the point of view of development. This particular picture delves into how Docker operates. What we described was we take our threads and so on, and we're going to turn them into a container. Then what's the story? How does it get automated and so on? Well, what happens is that we integrate everything together into a Docker file. So you've got you've got your threads. You're integrating that into a Docker file that contains the file system, the libraries, the interfaces, and so on. And there's a bunch of source code repositories that are used to help build that, and they will be on your sort of build system, your development environment. You build it and create, through the Docker engine, effectively container containing all those parts. So now you can transfer that to other machines. Now, typically, what you would do is to put that in yet a different container, a registry. And why is it a registry? So that people can actually look up that particular that particular component, and pull it down to whichever of the cluster nodes that they want it to run on, or maybe all of them. So this image registry is sort of operating like a server of Dockers, of whatever people have created and installed in that particular system. And here you can see there's a destination Linux host, and what it's doing is to pull down from the Docker container particular things that need to run. And of course you can do that under program control, or you can issue the commands to do that, but you pull this stuff down and run associate it with your Linux, and it's going to run on top of your Linux almost like another VM. But of course, it's all running at user level. It's all working, but you have your threads all operating asynchronously. They can use all of the packages down in Linux, so they get some concurrency and some parallelism. And this is all self-contained. From the last slide that we looked at, you put things together, you put them in a repository, and then you can pull them down to a particular client. One of the questions that comes up, and I hope you're all thinking about this, is just, okay, so I've got my server up and running. Now what happens when I want to make updates, changes to it, when there's revisions, when there's security updates? What do I do to make everything happen? Once again, this Docker system provides a mechanism to simplify the whole distribution of the Docker containers and completely automates the way that that operates. So you've got your application A, you've sweated lots to build it, and it's built around sort of bins and libraries. This is the original container that you've sweated so hard to create. What are you going to do when there's a security bug or there's another feature to add? You go in and you start editing it, and you add whatever it is that you would want to add to make it do that new function, or to be safer, be more secure. And here we've got a sort of example where we create some differences. Here's my old threads, here's my new threads. The code can be diffed. Those differences can be examined, they can be moved around. But in this system, we can put them in Dockers. The Docker container mechanism can actually handle it all. So we take that, and you will notice, because the bins and the libraries might change too, so we can actually have changes in bins and libraries in the Docker as well. So now we've got not only got the Docker with the original stuff, but if you want to change it, we can have a Docker container with all the bits that are being changed, but not everything else. So it can be very, very small, very tightly packaged. Those diffs, they're sent in what's called an update container, and once again, they're put into the registry. And the registry keeps track of the different versions of that particular Docker container A that you've got, so that you can actually ask for the old Docker container, or you can ask for the new one. If you ask for the new one, then what it will do, and this is really sort of cool, you have your Docker engine down here, and it's running an app, and it's running the old bins and libraries to support that app. Well, you want to update it. So what you do is to pull down the update, the apps, the difference in the apps, the difference in the libraries, and the Docker engine applies those changes to give you the new version of your system. So here you are. So let's suppose that you've got an app, really cool app, and you put it on 1,000 nodes. When you come to change it, what you do is to make your changes, you get an update container through the Docker system, you send it into the Docker container image registry, and when you're ready, you can deploy it on all those 1,000 nodes. You don't have to do a lot of walking. It will actually unpackage it, create the new versions of the Docker container that you want, and restart those Docker containers. So you have multiplied your efforts by 1,000. A real cool device. So if you think Docker is cool, you wait till you hear about the next lecture on Kubernetes. Well, let me tell you about Kubernetes next. This is a very cool development on top of Docker, on top of containers. You may have wondered, how do you organize very, very large collections of systems and get them all to run? Supposing you've got a very intricate stream processing system Or maybe you're doing Hadoop in containers, writing the code individually and passing all the data, with your thread, your own thread control. How do you build those sort of complicated systems? Well, Kubernetes will help you do that. So it's a platform, and what it does is to automate the deployment, scaling, operations of applications across clusters of hosts. So we talked about, well, if you wanted this one thing implemented on 1,000 hosts in the last presentation, but you could have many complications. Let's suppose you're doing stream processing and you have 5 streams and you want to allocate them to 1,000 hosts in some way. You want to do load balancing and all these other good things. That's where Kubernetes comes in, and it actually provides you a tremendous way of doing this without working too hard, really exploiting the programmability of building platforms, of building systems. The history of it is quite interesting. It's 2014, so it's sort of aged by now. It's Greek for helmsman or pilot, and I'm not going to try and pronounce the actual letters below, but it's something like Kubernetes. It's influenced by Google's Borg system, which was introduced to do their automation, and then Google partnered with Linux Foundation, and what they were trying to get to was a cloud-native computing foundation sort of system that could be used for all these different types of systems they wanted to build. And Google offered its work on Kubernetes as a seed technology in doing that, so that it became a foundation for quite a lot of work that was done by that Cloud Native Computing Foundation. It has several parts, and it's kind of interesting to think about how you develop from Docker and containers to these parts. So one of the issues when you're building these things is it's built on a distributed system, so they're all loosely coupled. So why not, as you're building systems, actually have building blocks that are loosely coupled too? So think about having inside each node loosely coupled building blocks, and then you push those building blocks to talk to other building blocks and other nodes in a loosely coupled way, effectively ignoring the fact that you're going from one system to another. How do you do it? So in this type of organization, you want to talk about more than one container at a time, more than one Docker element. They introduced the notion of pod. Pod is multiple of these Dockers, but pod restricts and constrains what you can do with all of those containers as a unit. And the reason it does that is because it wants to make it easy to actually construct these systems. So what it gives you is a unique IP address for a collection of containers all on the same machine, or all in the same Docker. And it prevents collisions from that node. It prevents collisions on the IP port address, so effectively sort of making each of those containers a separate entity that you can address with IP addresses and so on. So you don't have to worry about allocating the same IPs. You don't have to worry about the addressing, because all of that's taken care of with this pod notion. You will want some sort of backing store, file store, whatever. Doesn't matter whether it's a network disk, doesn't matter whether it's a local directory or some other sort of form, but you will want it in order to have the containers perhaps get at lots of data, or share data, or stream data, whichever. Well, it provides a volume to do this, and that volume is naturally shared by the containers in a pod. Now, it's not going to interfere with other pods and other network disks used for them, or other containers outside of all of this. What it's going to do is to provide you a way of thinking about this as just your own environment that can't be interacted with by other people, that you can actually know what's going on inside the system. So you've got unique IP port addresses, but naturally enough, what you would like to do is also have some sort of search capability, some sort of find me a pod, find me a particular thread inside the container and all this type of request. There is a nice, interesting abstraction here used, which is labels and then selectors on the labels. You can give a key value pair that resolves to a pod or a node component or a container. You can give it as a label and then use that label to find that particular element without having to know the IP address or knowing where it is. You can actually use that label in a selector to find it. The selector is a sort of like query element. It's searching through, looking for that particular entity. And so it's sort of really mapping whatever you want, whatever space of names you want as labels onto the actual implementation. There's a bunch of controllers in this system that manage the pods. And this is where you get lots of automation going on. So if you, for example, say, okay, I want this pod, but I'm in danger that perhaps I might flood this pod and it would die for some strange memory management reason, so I want to make multiple copies of it, then you can use something called a replication controller to actually create multiple of these. And you could either choose to say, well, I want 2 of these running together, or you can say, well, I want a replacement for the one which has died and slip that in, and it manages those pods. There's a daemon set controller. There's one of those on every machine, and what it does is keep the pods distributed in a nice way so that, say you want a replicated pod, you don't really want it on the same machine in case the machine dies, in case the node dies. So what you would do is to put the pod perhaps on every node. How would you do it? Well, you can tell the daemon set controller how it allocates those pods on machines to avoid that problem. There's also a very neat device called a job controller. A lot of jobs want to run batch. You want to sort of set up this job, start it running, go away, later on perhaps come back to collect the results. And you don't want to sort of supervise it or have to press buttons or anything else while it's running. Well, the job controller does that. What it would do is to batch pods and then run them to completion. So it effectively gives you that type of environment where you can sort of set it in motion, go away, have coffee. When it's finished, come back, collect the final finished product. You can, of course, batch pods one after the other so that one pod builds things that another pod uses and so on. So there's lots and lots of ways of building your system out of all of these pods. Then there's a set of services. This is when you have a set of pods working together and you have services inside the pods that the other pods want to talk to. So if you like, when you're trying to do inter-pod interaction, the services enable this. There's a mechanism for label selecting the actual pod that you want, of selecting within the pod what the container is, the Docker is that you need to talk to. You can do service discovery. That's one of the parts of the services. You can request routing. So you can say, well, I want a stable IP address. You can ask for a mapping from a DNS name to some address. You can program all of that within your service discovery so you can actually sort of use that as a way to construct complicated systems that you need to build. Then one of the issues is, well, all these systems, these pods are going to get used by outside folks. They're going to be network connections. People will want to interact with them. Those requests coming in need to be spread perhaps over a number of Docker instances in order to get the throughput that you want, because just one Docker won't be enough. There's a load balancer built into the services, and this load balance will do round robin. It will process all of the requests so that it gives you to a particular network address a sort of balanced load. If you want to request a service like a database lookup, and you issue lots and lots of requests, or lots of users issue lots of requests, they'll be load balanced over how many databases you've actually installed in your pods and distributed across on the cluster. So altogether, what you have is a very, very powerful way of constructing complex systems, lots of components on a compute cluster. This is how it works. Always understanding the architecture is sort of key. There's, on the one side, a need to control everything that's running, and that's done through something called a Kubernetes master. There's also a need for the individual nodes. How do you control the nodes? So you can see the architecture really is there's a master that controls all these slaves, and these slaves are where you put your containers, and the master is actually making sure they're all organized in the right way. So the master is controlled through an API, and what you can do is to ask for various different configurations and so on. Your application users are going to go to each individual node, perhaps through load balancing, to actually do whatever they're going to do. What you see in these packages are ways to, or are components built into Kubernetes to make this whole thing easier. So you have a Kube API server that takes the requests and then sort of decides what to do with all the requests in terms of organizing your Dockers. There's a Kube controller which controls where these places are instantiated. We discussed that before. There's this scheduler, and as we said, we can do batch, we can do other types of operations here. There's a replication controller that can duplicate, if necessary, your Kubernetes modules, your Dockers. It all runs on something called etcd, which is a daemon, but what it does is to implement this distributed architecture for control of Kubernetes, of the Docker elements across your cluster. So let's look on the flip side. If we go to the application users, they're going to come in, they're going to go through some sort of proxy element that finds the right sort of pod, and here you're going to have the select, looking up, finding the right place. So if you're looking into pod A, it would send your requests to pod A in order to implement them. And then what you will find is, of course, these components all interact with their Docker system on their particular node, but they also interact with Kubernetes. And Kubernetes, what that does is to provide the services of the Kubernetes master on the slave. So if you're going to do batch, or you're going to do some of these replications, then this element is going to be the responsible item on the nodes implementing that. So this architecture, it's a very sort of model view controller type of architecture for those who have looked at object-oriented programming. It's kind of an interesting architecture all by itself, and I'd suggest looking at this as a sort of good example of how to build systems. But what it does is to allow you to build arbitrary systems on clusters. Here's an example of what this means. Let's suppose what we want to do is to create a Redis database, and in that database we're going to have some data that front end will access and then return back to the user. How would you do it? This particular example, this guest book, and you can follow it through. If you want to download it, you can, and try it out on your own machines. It's all very easy to do. But what it will do is to create these these Redis master, Redis slaves in Dockers as containers on your machine, and it will allow them to interact, and you can actually send them requests through the front end. The key part to it is to use the APIs for Kubernetes, and here's one of the APIs, Kubet CTI, and I'm not sure how to pronounce that one, but I kind of think it's Kubekti. And what I'm doing is to create the examples in my book and in my guest book, and what I'm going to do is go off, take all of this, and actually start to build all of those examples on the machines. And you see coming back that the service Redis master is being created. What you see is that then it deploys that Redis master, then it goes off and creates the Redis slave, and then it deploys the Redis slave on the node that's being called the Redis slave, and then it takes the front end, it creates the Kubernetes node for that, and then it deploys the front end onto that node. So here you've got a lot of complexity, but it's all being done for you, sort of magic. And at the end, you can send requests, and here again I'm sending an API request into Kubernetes. It's another Kubeseti. This time I'm doing a get on services, and what I get back is a list of the IP addresses and the TCP connections, and it tells me how long it's taken to do that for the setup that I've built. Now, you know, Redis is a database. It's an in-memory database. The front end is probably some sort of Java webby type of thing. Here you see a very complicated system being deployed. Obviously, you're not in the location of that cluster. You're way away. You can control those constructions of those systems. It's all packaged. It's all automated, and this just revolutionizes the way that we're now building clouds. So if you want to read more about it, then I would suggest going off to read about Kubernetes. There's some good documents out there. Also, looking at GitHub, there's some examples of how you use Kubernetes for really sort of doing some very, very sophisticated work. And you know, we thank everyone in Kubernetes for giving such good explanation of it. Okay, thanks. One of the more interesting virtualization techniques is illustrated by JVM. There's lots of advantages of JVM for distributed computing, and it's well worthy of us just taking some moments to review what JVM means and what it means in a distributed environment. So if you go look at all the definitions, Oracle is the generator of all of the information about JVMs. It owns Java and virtual machines. But when you look there, you find a definition. Really what it is it's an interpreter running on top of machines that's providing a virtualized machine, one that's very, very customized to executing Java programs. So it has lots of attributes that allow you to check the Java language as well as execute. And that is what makes it really interesting for our purposes. Now, Java comes in a standardized format. There are actually 3 parts to Java. One is a specification. It's a document that describes exactly what the Java machine does. So for each machine instruction in Java, or Java instruction, Java bytecode instruction, there is a definition written out, and you can actually chain these together and you can prove properties about them. There's an implementation, And in fact, there's a variety of different implementations. The difficulty is getting the same specification implemented on multiple different machines. And they've done that by being very accurate about the specification and then providing generic implementations that you can then refine for a particular machine architecture like an ARM or a x86 or whatever. And then you have instances. They're implementations of the JVM that's running on a machine, usually runs on what we would call a process under an operating system, and it executes the program code that has been your Java code that's been compiled into a Java bytecode. So it interprets that bytecode and does what the bytecode says according to the specifications. Those three steps have become very popular, and as a consequence, the front end, the Java part, has also sort of been generalized, and now you find Java byte compilers for several different languages, some of which we are very interested in from a cloud perspective. Let's look at, as we're executing the JVM, we execute these bytecodes. There is a runtime environment, and that's well specified too. What it does is to give you all of the semantics that you need. So if you're going to have a file system or you're going to do some sort of inter-process communication, that's going to be provided by this runtime environment. The runtime environment is also checking to see that you're actually using the system in the right way. So there's multiple checks. Now what that runtime environment consists of is a library, and that's a sort of standard implementation on many machines, and then some particular pieces of implementation for it. And so you have a way of porting this JVM from machine to machine that's can be standardized and can be uniform across multiple different instances. So let's review what happens when you have a Java program. I'm not going to go into writing Java programs here, and we'll only do very simple ones that you can probably copy from our notes to run examples. But this is what's happening. You take the Java code, and it's .java as the suffix to that, as you store it in a file name, and you execute a JAVAC compiler, which is a Java compiler, and produce from it bytecode that goes into a .class file. So all of the files you see around in the Java environment with suffixes .class actually have bytecodes in them. Now you take that bytecode, if it's correctly compiled and it's correctly written, it will run on a JVM. And doesn't matter which JVM you choose. You can choose one on Windows, you can choose one on Linux, or you can choose one on Mac. It's going to run the same, it's going to produce the same results, it's going to synchronize the same way with other Java programs if it calls them. It's going to have the same I/O as other, no matter where it is. And so you have a uniform platform for executing code. And in a distributed world like we're dealing with cloud, this is a plus. Now remember, we're not just talking about the actual cloud itself and its cluster of machines, but we want something that allows users to program the cloud or program with the cloud. So it includes things like browsers and things like cell phones, laptops, and so on. All of these can use Java, and they can communicate in one paradigm, which makes it a very powerful mechanism for the cloud. What sort of languages do we have compilers for that produce bytecode, Java bytecode? Well, obviously Java, but there's Ruby, which is very, very popular now in building websites. There's Python, which is used a lot now for visualization besides websites. There's Clojure, which is used for some specialized software we will talk about in the second series of this cloud computing. There's Groovy, there's Scala. Scala is also used in the second half of our lectures, and we'll show where that's really sort of applicable. So all of these will produce JVM, and the class files that the compiler will produce for these languages all contain the Java virtual machine instructions, Java bytecode. They also include a symbol table. They'll also include some other declarations that are useful in understanding how to execute that code. The class file itself is hardware and operating system independent. You can take a class file to anywhere and execute it, so you don't have to worry about its target. When you're compiling, you just don't worry. It's all going to be taken care of no matter what the target is. So I can compile code for my cloud. I can compile it on my Mac OS X, and it's going to be perfect. I can simply take my cell phone and do exactly the same procedure. So this allows a tremendous lot of sort of take up by all of the clients and developers. It really adds momentum and velocity, if you like, to the whole cloud initiative. Bytecoding verifier. The secret of how these systems actually manage to convince people that same code would run on all the different machines is in a bytecode verifier. What happens is that we build a bytecode itself, what's compiled from Java. That bytecode is actually, you can look at it as ASCII, you can look at it in binary. There's different sort of transformations you can make, but they're equivalent. So there's a sort of direct correspondence between whatever representation the bytecode is and the standardized official specification for bytecode. What's key is that as you're executing, branches can go anywhere. We observed that if you're taking a virtualized virtual machine, we put a hypervisor under it so branches can't go to the kernel, for example, but they can go backwards and forwards within the virtual machine that you're executing. Well, in bytecode, in JVM, yeah, branches are always to locations, and they're restricted by the language. It's very difficult to get outside of functions and so on with branches because that's a security feature of the way that Java works. Data is always initialized, so you can't run into a 0000 type of piece of data. It's always initialized. There's always some value placed into it. And similarly, references are always initialized so that they have some sensible nil pointer in them. And everything is always type safe. So if you have a pointer and you try and assign it a blank or a space or a real number, it's going to cause an error at runtime, and you're going to be able to detect it. Oftentimes, you'll actually detect it in the Java compiler itself. Access to private or package private data and methods are rigidly controlled. So you can't just sort of take your Java code and access everything that's running on your JVM. You can only access the things that you have access rights to, which make it a lot easier to debug, and it also makes it very difficult to break into, and it makes it much easier to write software for in a modular way. And these are the advantages for a distributed environment. As a consequence, if you build the right Java interpreter, the right JVM interpreter, no user program can actually crash the host machine and interfere with the operations in the Java, or the Java JVM can't interfere with the operations on that host machine. So it's like a sandbox. It provides you, if you like, a perfect environment to execute your code where you're safe and the people who might be on that machine are also safe. They're protected from each other by the JVM. Now, this is not true when you just get to something like Zen using that sort of hypervisor with a sort of compiled code into a hypervisor, an operating system and application code, because there you can find ways that circumvent, if you like, what the hypervisor is trying to restrict. In Java, it's not going to be possible. So this is really good, solid separation of concerns, which is a big plus. Now, you might say that's going to be slow because there's got to be some mechanism to stop all of this interaction and check whether it's legal or not. And you're right, Java code runs a little bit slower normally than ordinary code running as machine code on a particular machine. But there are things called just-in-time compilers. And what they do as an optimization is they look at the code, and if the code has no way of, if you like, providing a problem to either crashing the machine or to interfering with another client, another execution of machine, program execution on the machine, then what it will do is to convert those instructions into actual machine instructions on that machine. So if you've got JVM and you're just doing some arithmetic, that arithmetic can get converted into Intel operations, x86 operations, add, plus, minus, divide, and so on. And you know that there is not going to be any impact on anybody else on that machine. So the just-in-time compilers can really do a good job. They still give the safety, but they can accelerate the code. So here's a pretty picture, difference between JVM and the classic virtual machine. The JVM code sits up in the application, and you can write it, you run it, it runs with some libraries to attune it to a particular machine, a particular sort of way of implementation, how much space and so on. And there's a JVM interpreter under it, and together that JVM interpreter and the libraries restrict the JVM code to being safe, doing what you expect it to do, or telling you that there's an error because you've made a mistake. So that JVM interpreter would interpret it. It's written on top of machine, so it'll be a machine code interpreting your byte codes in JVM. It can have a JIT attached to it, which would compile certain bits of the code as that interpreter thinks they're safe. Over on the other side, if you look, there's virtual machine and virtual machine architectures. We've talked about a whole suite, or we will be talking about a whole suite of different virtual machine architectures. We can have ones like Zen that are virtualized by basis of compiling and adding instructions into an operating system belonging to the client, sort of going through and annotating those instructions where you're calling down and to do hardware type of specifics, replacing those within instructions that would get executed, if you remember. We've got hardware specific instruction, like in the VX architecture and Intel, where if you execute something that could be sensitive to VMs and hypervisors, then it traps into the hypervisor, and the hypervisor does appropriate things. And then we have a whole host of operating system approaches where the operating system itself is sensitive to sort of virtual machines and tries to protect the client from accessing the wrong things on that machine. So things like containers that we will be talking about allow you to run threads, lots of different threads in a multi-tenanted environment. There's some protection, but not complete protection from one another. So complete different sort of approach, somewhat similar results, but if you want to be assured of actually having security, then the JVM is a real sort of plus. So let's summarize where we're at. What we've looked at is JVM as an example of, if you like, a sandboxed environment where you provide facilities to run on a cloud, and those are protected, those are secure from other people running on that cloud. They both prevent those people interfering with you and you interfering with them. So this is really cool. And when you think about in a cloud how you would like to use all those machines in a distributed way to provide all of the services you want to build, then remote execution sort of pops up as a real sort of necessity. and remote execution in these sandboxes is really very, very attractive because you can debug it, you can be protected, and so on. You can do your cache calculations for your banking algorithms and so on very, very securely in this JVM environment. Next, it allows you portability. It doesn't matter what the cloud's built of. You can use it. If you want to extend your computation, Java gives you a base, or the JVM gives you a basis for providing elasticity. It runs on most hardware. It doesn't really matter how many machines or what the size of memory is. It can accommodate all sorts of different factors. It supports secure browsing. So most applications using the cloud, you will find, use HTML, use REST architectures to talk from the front end, from your client to the cloud. Well, if you do all this in JVM, then you can have a secure platform that's on your laptop or in your cell phone talking to the remote cloud, and you're providing a level of assurance that actually you get the communication right, that nobody's interfering, and so on. Has huge impact as well on how fast you can deploy enterprise, new architectures, new applications, because Java will support all of the different software engineering, not just Java, but JVM will support really good software engineering practices, making sure that you've got the right software coded. It'll check your typing, the language will constrain you to safe constructs, and you can share that code. You can open source that code, know that when it's running, it's going to be protected no matter what's happened in that open source environment. So it provides a level of assurance for growing your enterprise on the cloud. So we've introduced JVM. I've described lots of aspects of JVM. You can see there's some big advantages. Needless to say, there's a little bit of cost, but it is one of the forces that has made cloud really important in the world. In this set of slides, what I want to do is to emphasize just what do you get with OpenStack and what are the mechanisms that allow you such great deal of control. Sort of, if you like, diving a little into OpenStack to give you a feeling of what it's capable of doing. So the OpenStack project's been around for a while. It has a very sort of ambitious goal of trying to be ubiquitous way of building cloud infrastructures for everyone. And Ken Pebble articulated that in his statements. Basically, he claims OpenStack is an open source software project enterprise services providers can use to set up and run their own cloud compute and storage infrastructure. So you've already seen this diagram before. I just want to now emphasize the elements in here. There's a dashboard. The dashboard talks to all of the various elements. I haven't put in the OpenStack controller there. I've assumed that it is in there. But what it's going to do, that controller and the dashboard, they're going to map to the compute, networking, and storage elements that you require for your OpenStack. And now you will have instantiated on multiple nodes these compute elements, and you probably have one networking node that controls the network. You probably have one storage node, or maybe multiple storage nodes that control the storage. When you ask for user applications to come in, you'll be allowing them to use those compute, network, and storage nodes to define what types of infrastructure they want. Typically, for a set of users, or for a particular user application, you'll be giving to that user application a specific compute node, well, perhaps multiple nodes, a specific network node and specific storage nodes, so that that's all sort of contained within the cloud. The beauty is that when that application is no longer needed, you can just give it to somebody else. You can give the hardware, the network, the storage to somebody else. And then if you want to bring it back later, you can do the same. If you want to scale it, you can release nodes. If you want to, or you can allocate nodes to make it bigger, release nodes to scale it down. So it gives you a great deal of flexibility. So that's the basic sort of idea behind OpenStack. Its compute server is called Nova. It orchestrates large networks for virtual machines and it's responsible for VM instance lifecycle, network management, and user access control. It has some storage, which is called Swift, provides a scalable, redundant, long-term storage for things like virtual machine images, data archives, and multimedia. So these are basically, if you like, sub-applications, they're sub-components of this whole OpenStack infrastructure that allow you to do different types of things. This last one is an image server, and this is when we were talking about boot images and so on, this is what we were referring to, what there is embedded into the OpenStack architecture, the ability to pick up virtual machines from previous previous times that OpenStack had been running, and load those virtual machines and run those. So you can, if you like, freeze the OpenStack, store it away on your Glance image server. Your files will be stored on the Swift. This would all have been under the control of Nova, and then when you want to recreate this whole virtual data center, what you can do is to talk to Nova. You can pull out that image from Glance. You can pull out the file system from Swift. They're all plugged together because of the descriptions in Nova, and so now you have a completely working data center. So you effectively can store and retrieve data centers in this whole sort of approach. So what we've seen is this development from a cloud, just hardware, to being able to manage the hardware with something like Mirantis, to bringing up virtual clouds effectively, that triple, the compute, the networking, and the storage, to being able to manipulate that cloud once it's actually running, and that was this section with Nova, Swift, and the network operating system. So next time we will be moving from there to some cloud services and talking about those cloud services. Thank you. So Amazon Web Services are probably the largest IaaS provider. They will provide a whole gamut of infrastructure as a service, from storage, S3, elastic block storage, computation, elastic cloud computing. They have databases, RDS, Dynamo, elastic cache coordination, and they provide a simple workflow framework for doing jobs, building jobs. All of their services are paid depending on use. There is an offshoot of their marketing and sales operations, and it's grown to be one of the more dominant, well, the dominant characteristic of Amazon, that it provides this IaaS solution, and there's a lot of different companies that build on top of IaaS to build their own services, cloud services. So if you look at the Amazon Web Services, there's perhaps 4 main places that they really sort of excel. One is the Amazon EC2 environment, which allows you to create virtual machines and populate the virtual machines, create networks between the virtual machines, and then use those virtual machines as a distributed system for whatever purpose you care to choose. Amazon DynamoDB is a database that's flexible. It's a NoSQL database, so it's very fast and has, as we will find out, it sort of uses eventual consistency. We'll discuss that later, but this allows it to have lots of customers, very fast response time, and still cope with a huge amount of information. There is a service that runs code in response to events called the Lambda, and what it will do is automatically manage how your systems respond to different activities, different requests, different responses when you have computer resource failures and so on. And then Amazon S3 is their very large storage, long-term storage. It's very scalable and provides a great deal of reliability and fault tolerance. It stores things in terms of objects, and you can retrieve those objects and use them. So, for example, when you're using Amazon EC2, you may want some storage, some data out of storage. You would go to the Amazon S3 to retrieve that storage, and then you would use it in the EC2 to provide whatever computing you actually want to do. Amazon's split up into multiple regions. These are just a list of them. There are 3 main facilities in the United States: East, West, and West again. One up in Oregon, one down in California. Of course, Amazon's located up in Oregon, so that makes it easy. There are, however, Amazon regions in the rest of the world. So there's one in Frankfurt, one in Ireland, one in Singapore, one in Tokyo, one in Sydney, one in Sao Paulo. So they have a set of distributed facilities that they can direct you to. And whenever you sign up for Amazon services, what you will be directed to is one of those regional areas, and they will be providing your compute for you so that you benefit from a low latency and high availability in your particular area. Different types of instances can be created inside the infrastructure as a service. We mentioned EC2. If you dig down into the EC2, what you can do is to create micro instances of virtual machines, which are sort of small, very lightweight virtual machines. They're still virtual machines. It's a free tier, meaning that students can actually get access to those and use those for their own personal projects. And there are multiple micro instances running at the same time. They do not put an awful lot of effort to for multi-tenancy to make sure that the clients don't interfere with each other, but they are free. So in general terms, you can actually get a lot of compute out of those micro instances, small virtual machines that fit together into their big actual hardware infrastructures. General purpose machines, those are larger instances they use for production, for companies wanting to provide services. They have memory optimization, storage optimization, compute optimization. And if you want to, you can actually get GPU instances in those general purpose machines. So if you want to run some floating point, there's ways to accelerate that and really take advantage of GPUs in the computations. Amazon has typically 4 billion to 5 billion range revenue. That was 2014, and it's sort of been doubling over a 2-year period despite continuous decrease in prices. So this is quite an achievement, and Amazon is the target to be. It's the company to be if you're trying to provide IaaS facilities. It provides the main source of competition for everybody else. Its capacity is about 10 times as large as its nearest 145 competitors. That's a Gartner figure, but that again is very impressive if you think about the scale of some of these machines and scale of operations. Even Google doesn't threaten Amazon's IaaS services. They really sort of dominate. What do they provide? Well, they're running on Zen hypervisors. Their proprietary version of Zen, so it's been modified internally in Amazon to be more efficient. The micro instances are often oversubscribed. The other systems, as I said earlier, weren't. So if you want to sort of get free computation, as long as you don't mind sort of a little bit of performance hit occasionally, those micro instances are very cool. Storage and local area networks are shared. They're multi-tenant, so you are sort of losing out if there's lots of customers wanting to use a particular Amazon service. You'll notice performance degradation, but on the other hand, they're trying to provide really effective designs where that impact of sharing is not felt too badly. You get billed by the hour, and there's provision for Amazon machine instances, licenses. You don't have to worry about so let's suppose you want to use Microsoft Word. They will provide you the images for Microsoft Word and you can use them. You do not have to go and get separate licenses, or if you want to use some other proprietary operating system. Typically Amazon will provide you those machine images and have it all licensed, ready to go for you. The operating system is typically on upwards is the customer problem, but Amazon provides you a lot of choices. They have an image store, for example, for their virtual machines, and you can choose from that image store which operating system that they provide that you would like to use. Now, if you want to use your own operating system, you can actually do so. You just require to upload that into the Amazon system, and then their imaging software would allow you to boot that particular image. It would be booted on top of the Zen hypervisor. We have consoles on the Amazon stuff. The consoles are there to provide management for what you're doing, whether it be virtual machines or whether it be some sort of platform as a service. They have different types of of consoles. Their main one, controlling the virtual machines, is provided by VMware. They do also provide one by Microsoft. The storage, well, there's transient instance-specific storage. So when you start up your virtual machines in EC2, you get access to storage as part of that, but it's transient because when your virtual machine is not running, that storage then disappears. So it's taken down and moved to the bigger store, the S3 store. There's persistent instance-dependent elastic block storage, and you also have SSD and encryption options. The block store can be used to build other types of database systems, as we will find out later on. The SSD is used because it really does accelerate your computations and make them faster. Encryption allows you to actually, say, provide a HIPAA environment on top of Amazon, or a storage at rest encrypted solution, and so it provides you safety and security, and you just need to build it on top of their infrastructure. The object-based simple storage service, S3, is there for all your long-term storage needs. It stores objects. You can put images into it, or data into it, all sorts of things. The major cost you'll get is uploading and downloading to that S3 from, so let's suppose you want to upload it from your business, then that will be the big costs in trying to get data there. The data itself is located per region, and so when you create data, you have to say which region. Well, usually it's assumed which region you're going to be in because that will be the closest one, and the data stays there. So if you build data that you want to keep in the United States, it's not going to actually be transferred abroad. It will be restricted to the regions you put it in, And so that's a safety mechanism. If you want to actually back it up across regions, you can actually do so, and they provide another service to do that. On the networking side, they provide a virtual private net cloud, private routing between the virtual private clouds. They provide you VPN tunnels that can connect your enterprise into Amazon. So you build your virtual cloud and then you connect your VPN tunnel into it. And there are sort of direct connects that allow customers to use carrier-based WANs, private WAN services. So if you, for example, negotiate with AT&T to have a high bandwidth connection, you can use that as your carrier and get into Amazon services and use that to connect to your cloud as well. And that's a big advantage if you're negotiating with these large companies for carrier access. When you log into Amazon, what you'll see is this splash screen. It's pretty self-explanatory. There's lots of documentation. As I say, as a student, you can do this for free. They will need a credit card from you, but then for free, you can have $300 worth of compute. And these are all the sort of ways you can use that compute. You can go in there and at any one of these points start operating and building up your service. The next main splash screen is this one. What it shows you is all the different services that Amazon actually can provide, and I've only touched on a small number of them. There are actually a huge number of them, and they all sort of range enterprise, mobile services, application services, analytics, just depending upon what you want. And Amazon will let you build the various systems. Some of these will be platform as a service, some of them will be infrastructure as a service, but you're starting off as infrastructure as a service, layering things up and then providing that for your customers. And Amazon's going to provide all the load balancing to get at your systems. So it's all sort of fairly straightforward and very well thought out, and Amazon is one of the lead companies in actually doing this type of interface and providing this type of service structure, which is why they're so successful. So this next diagram just shows you some of the other screens you can get to. This one is showing you the resources, it's showing you how many running instances, the volumes, that's up here. How many key pairs, that's security keys that you're using, what sort of groups you've got, whether you're using elastic IP, meaning you can have a range of IP addresses and increase them or decrease them. What sort of, let's see this one, load balancer you're using, what the options are on the load balancer. So when you see this, what you can do is to see the different health of the different systems. And you notice under here, it lists some of the different zones, the ones you're probably interested in, US West, US East, and gives some, well actually in this case just US West, but it gives you some details about their accessibility and availability. Here's another splash in. This is if you're going in to build a system, then you can choose your own machine image. Amazon provides AMIs, and you can choose from what those AMIs, which particular type of operating system you would like. So here's a Linux, and down here's a server, and down here's a Windows server. You can just opt to select one of these. You can say whether you want it 64-bit or 32-bit, and that all is provided for you in building your services. And so here is some yet another screen, step 2 of building your cloud. What you would like to do is to say whether you want big virtual machines or small virtual machines, where here's a list of all the virtual machines they provide. And you can see that they have micro instances, they have large instances, they have extra large general purpose sort of IaaS infrastructure. There's dots for selecting which one you want. Here's a number of virtual CPUs that you want per per instance, so you can choose a micro with 1, or you can choose an extra large with 4 if you, or up to 8 if you want. You can choose how much memory. Now you notice these are all in categories. They're basically whether you want to do a lot of computing or whether you want to do a small amount of computing, whether you want to pay a lot of money or whether you don't. So there's various options for the memory, and they fit to the size of the number of CPUs. There's optimized availability for some of the optimization packages, and then you can also specify how much network traffic you want. If you want to go to high networking, because you're using a lot of network transfers, then you have to go to a larger machine, and you have to pick one of these options down, lower down. You see that you can even pick a 10 gigabit dedicated, this one, 10 gigabit dedicated infrastructure if you so desire. So that's yet another screen. You go through, if you're building a system, you go through various steps. That would have been step 3. So you go into step 4, 5, 6. Here's step 7, cutting a lot of corners short, but what we're going to do is to launch the virtual machines we've built. What we've done is to build a network around them, and then we're going to sort of just say, well, create these things. So in step 7, we're reviewing what we're going to launch. It's going to be a micro, and we have a networking preference, and we have the security group. The security group would also indicate how you connect to it. Typically you're using SSH, and you're running over the protocol TCP, so you get a nice, good, constant, fixed connection into your machine, and it's encrypted so nobody can actually interfere with what's going on. And then after you've pressed launch, you will get a launch status, and it will tell you after a little bit of time that your systems are all running, and you can go to another monitor which you can actually sort of look at the health of those systems you've launched, see the overhead, the CPU being used, the amount of disk being used. So lots and lots of different things. Here you see a button to actually go off and see the instances. That's more of a summary, but you can drill down and see lots of details about them. If you do pick that summary, this is what you're getting. As you can see, the status is running, and you can see a little bit of detail about where we are. It's still initializing, although the machine's up. It's got a public DNS. It's got a public IP address, so you can reach it from outside. So you have there a sort of step-by-step set of slides, set of displays that will allow you to go and launch your own personal cloud. This quick overview, what we've seen is Amazon Web Services, and it provides a very comprehensive set of tools for building everything from IaaS up. You can launch your own PaaS if you want, and some people do that. Amazon is one of well, it is the top-rated, largest cloud provider for IaaS. Now we'll go and have a look at some others. So Microsoft is a challenger in this race for who's the biggest cloud vendor, and they certainly provide a huge cloud. Their view is to put cloud and mobile first before everything else. They've always aimed at businesses and providing support for businesses, and of course one of their benefits they can do is to bring Office and all of the Office software to a very large audience through Office 365 on their cloud. So let's look at their system, what they provide. They have emphasized trying to build a competitive service. They have even provided a competitive way of doing virtualization. That's provided by Hyper-V. And the intention, of course, is not to get locked into VMware's offering, and it distinguishes them from what Amazon's doing. Microsoft Azure is both infrastructure as a service and platform as a service. Their big selling marketing point is really the provision of Office 365 and Office for iPad on those services, so that everybody who's accustomed to actually using Microsoft for business can actually just move to a cloud solution using whatever devices are available. It also provides a shared file system called SharePoint, and that's another sort of sales point because they have a lot of customers built in using SharePoint. One of the claims that Microsoft makes is that if you have a local business and you've set up a computing environment without networking and your Office and all of the other different applications in your Microsoft environment, they will move that to the cloud for you as a way of you expanding your business or making your business cheaper. They will do that, and you'll retain all of the features and connectivity and sort of customized organization of that cloud, and so you don't have to really deal with very much. It's all taken care of you, moving to that different sort of support system. So they also provide some facilities as platform as a service, software as a service, rather. They provide Yammer, which is a social and collaboration network. They provide Exchange, which is Google's, well, like Google's Gmail, but it's a mail service, and their Exchange service is very large. Nowadays, they're also providing voice over IP in the way of a Skype version that Microsoft calls Link, but it's essentially Skype, and they've amalgamated these things. They also provide customer relationship management, and theirs is a very dynamic system, and again, that's been quite successful. So it was launched by Microsoft in 2010, and say it provides both sets of types of services. What it also accommodates is hybrid cloud computing, and that's a really sort of interesting feature that Microsoft has got itself into there. What it allows you to do is to take your local cloud and connect it to the bigger Microsoft cloud, and by doing that, it allows you to scale up with Microsoft products, of course. It allows you to scale up to a much bigger Office system. You can keep a core, which perhaps is more efficient on your local machines, but then if you need the extra capacity, you can scale up with hybrid cloud computing. So that's a really sort of interesting feature. What can you use Azure for? Well, pretty much you can use it for anything. All of the topics we've discussed before about bringing up virtual machines and different virtual machines you can use with the cloud. In fact, Azure will allow you to run Linux. It will allow you to run any other sort of Unix system or one that you build yourself. They're completely neutral with respect to that. They of course provide you very, very good Windows virtual machines. The PaaS service has been known to host websites that receive a lot of traffic. They have a reputation for being able to do that very well. They have a lot of web building tools, and so that seems, or that is a natural business area for them. They also provide very good .NET facilities, and if you want to extend your .NET or your .NET application to the cloud, then Azure is the way to go. Azure developed their own operating system called Windows Azure that's used for the data center clusters, and that does the glue to actually make all of the Azure do what it's using. Underneath Windows Azure, there's a Hyper-V. It's a Windows server hypervisor that can run virtual machines of any different sort, and your interface to that Hyper-V would be Windows Azure. The Windows Server is supported, so you can take your customized environment that you've built in-house, and you can move it out to the cloud very easily. You can provision and manage the virtual machines on it, and you can attach and manage disks on it just as if it was locally. So this is a great way of building a hybrid cloud solution that is flexible, and you can pay a base rate to keep it going because you're going to use that 100% of the time. And then when you get peak loads, like at Christmas, you can just get more of your system from Azure. So Azure, as I was saying, was the operating system in the data center. It treats the whole data center as a machine, handles resource management, provisioning, monitoring, manages application lifecycle, allows developers to concentrate on business logic and their own operating systems, their own systems that they're building. So for example, it provides a shared pool of compute, disk, and network. It provides that virtualized storage, that compute and networking, the illusion of boundless resources. That's all sort of mapped into the Windows Azure operating system, which is really sort of a distributed operating system that manages all the components through those hypervisors that we were talking about. It provides common building blocks for distributed applications, reliable queuing, simple sort of structured storage, SQL storage, and then access control and connectivity. And the Windows access control systems are quite sophisticated. They're like the ones that you get for your local clusters. So they provide a very, very sort of tight security system that you can use and deploy as long as you're familiar with how Windows does its security. So here's some of the components that we see in the Azure. You have your service model, then you have .NET, you have ASP, which is used for the web, you have PHP, then there's underneath that Windows 2008 services, you have your hypervisor, your blades, your SQL and storage, blob, queue, table. Blobs are like objects in Amazon. There is configuration for networking. And so what you see in this, although the names are different, exact sort of duplication of many of the things that Amazon is doing because all these big cloud systems need the same sort of management tools. So a cloud application is typically made up of lots of different components. It will have a front end, load balancing, stateless web service. It'll have a middle worker tier, which is sort of order processing and encoding, and you would get to that middle worker tier through the front end. It would have a back-end storage with SQL tables and files to actually drive this thing, multiple instances of each for scalability and availability. And what Azure does is to provide you a model of these cloud applications so you can pick one and then you can instantiate different pieces of it in ways that you want. So this modeling sort of allows you to get simple workflows, allows you to build simple systems, but using very, very sophisticated pieces of components and some quite sophisticated algorithms in terms of load balancing. So their terminology is slightly different. Their application is called a service. They provide a definition for that service, or a way to sort of classify or describe your service using XML, I think is XML, defined information. They allow you to describe the configuration information in a scripting way so that it can be stored and retrieved, and roles for what things are doing inside the system. Roles are like DLLs in the service process. They're collections of code with an entry point that runs its own virtual machine. So you see sort of different terminology, but very similar purposes backwards and forwards between Amazon and Microsoft. There's 3 role types that they offer. One's a sort of ASP.NET i57 sort of Windows Azure supplied operating system. They provide a worker role, arbitrary code in a Windows supplied operating system. They provide a VM role uploaded with VHD provided by the customer. So this will be your heavyweight, heavy duty, very customized, very special purpose type of system. So they provide different service models for what they're providing. Slightly different from the Amazon stuff, but still satisfying the need of providing those CPU classifications. This is what the role contents look like. There's a way for naming it. There's a description of the size of the VM, small, medium, large, so you can see different ways to organize things from Amazon to here. They have code, web worker role, hosted DLL, and so on, different types of code that you can embed, and different configurations, number of instances, number of threads, and so on, number of updates and fault domains, so that you can keep track of your systems. Again, very similar in sort of function to what Amazon is, very different organization according to a sort of Microsoft way of viewing everything, both accomplishing the same task, and of course both vying to get customers to actually use their system and trying to make their systems as simple as possible to use for the purpose of providing the services that customers want to provide to their clients. So Google provides an online, the best, if you like, or the leading, be careful what I say, online advertising system in the world. And it has far greater outreach than most of the other companies, big, small, whatever. That's because of its search capabilities and its obviously known popularity. Its competitors are mainly from different countries rather than within United States. So it provides service to small and mid-sized businesses. It doesn't change to meet customer needs because it's aiming at providing the best best advertising service that it can. It innovates very rapidly, which is if you're building your own system on top of Google, then you need to accommodate that rapid innovation. The value data for it, Google is very good at collecting real-time data because it sees what people's needs are through its advertising services, and it sort of really capitalizes on providing that in its services, and has many different service systems that try to give you the best updated data possible. It champions a cloud. It's not into hybrid clouds. It doesn't want you to have your own Google and then sort of upload them to a bigger Google. It's trying to provide a cloud that everybody will use, which will remove the necessity in the sense of having your own local compute systems. And it really works at the web scale, the World Wide Web. It is got an infrastructure that's global, and it emphasizes things that will work globally over the whole world. One way to sum it up, and this is not my quote, but I think I got this from Gartner, although I'm not sure Gartner's responsible. We're not like you, and you should want to be more like us, is sort of almost the way that Google is talking to the rest of the world. So what it provides as a platform, its main emphasis is a platform as a service, although it does offer now infrastructure as a service too. So if you like, it focused on platform as a service because of its search and so on. This was easy to do, and then it introduced information as a service as a sort of afterthought, and because Amazon was becoming so dominant and they needed to compete. So with Google, you have a Google App Engine, and the Google App Engine allows you to code for Python, Java, PHP, and Go. It provides automatic auto-scaling, and in some of the demos that Google shows, They show a genomics example that you can search for on the web, and what they do is to scale the size of the computations associated with that from mere sort of 1,000 nodes up to 600,000 nodes, all within Google App Engine. They have shared hardware, meaning that it's multi-tenancy, multiple users use their hardware at the same time. Your Google App Engine is actually sort of time shared over multiple different people. You don't get a single CPU to yourself. There is cloud storage, which is also shared. That's its object store. There's a NoSQL cloud data store, which is its eventual consistency data storage. There's a MySQL relational cloud that you can use if you want transactional-based systems. It offers Adobe Hadoop on top of its systems. It offers cloud pub/sub-based systems if you want to do event processing. So if you want events, then you publish your events to the Google Cloud, and people can subscribe and listen to those events. It provides cloud endpoints, allowing you to connect clouds together, and it allows business analytics in the form of PaaS, so business analytics platform as a service, allowing you to do things like big queries and predictions on data sets. So as you can see, it has a broad range. Its emphasis is much more on platform as a service, and its platform as a service isn't just sort of one offering. It has multiple different pieces. Of course, it's got Google Gmail as another platform that it offers, and it's really aiming at the customer, at the end user. It does have infrastructure as a service, as I said, and under that is Google Compute Engine, and the Google Compute Engine pretty much allows you to do many of the things that the Amazon services do, but they don't have so many ways to monitor and to view the system, and so many options, that terrific array that we saw with Amazon of different possibilities of the way you could construct your infrastructure as a service. Google has fewer of those. One of the more sort of impactful services that Google does provide as part of its cloud package are the following. It offers maps. Maps are used tremendously for navigation, for all sorts of things. Google Maps is really sort of one of the foremost, and it's taken to challenge things like Esri, which used to provide mapping services in the past. Is augmented maps with photographs and really sort of detailed routing, and so this has provided a real sort of leader for Google. It also provides Translate using some of the machine learning tools that it's built. It offers you to translate from one language to another, either written or oral. It allows you form filling, forms development. It allows you wiki sites to do all sorts of collaborations. It allows you shopping, which fits in with its marketing views. And it also has Keep, which is its way of providing services to clients which want to remember details about their current state of their mobile. So here's a sort of splash screen of Google, the Google Compute Engines, kind of nicely highlighted here. This is a very competitive market, and everybody is currently after trying to get as much of that market as possible. Google, even with all of the platform as a service offerings, it is still being very, very competitive in the information as a service area, and cutting its rates and making them match, or if not better than, the other competitors from Microsoft and of course from Amazon. This is a description of what one of their projects would look like if you go into an information as a service. And you can see here that you can go and build your particular services. You can drill down to those and elaborate them, define them. This is the project dashboard for the Google services, information as a infrastructure service. You can build a simple Hello World app. You can try starting up virtual machines. You can create APIs for your applications, so you can build on the Google API schemes to build your own APIs. You can create cloud storage for your systems. You can go use their big data collections, and you have a bunch of options just like Microsoft and like Amazon. You can go choose from a pre-built solution with virtual machines and various databases associated with it to actually try and put together your own type of cloud. Here's a description. Yes, we've got a populated instance here where I've created a virtual machine. It's on the US Central of Google environment, and I'm talking to it with SSH, and it has this IP address. So I've skipped a few frames here, but this is one of the displays that it will offer you, showing you just how Compute Engine can actually build cloud systems for customers.
So in this video, I'm going to talk about a new trend in cloud computing. This is pretty new, but it has significant importance in today's industry. Of course, we're talking about serverless architecture, cloud serverless architecture in this video. Now, you might think, what does serverless architecture mean? Pretty much any application that you have has to run on a server, right? Here, what we really mean by serverless architecture is that pretty much an extension of the platform as a service sort of model that we've talked about in previous videos, right? So remember, in previous videos, we say for platform as a service, the cloud provider would provide you with a certain platform. It has certain APIs that you can do, and you just submit your program, right? So serverless architecture definitely is more of a hybrid term. It kind of encompasses infrastructure, not infrastructure, platform as a service, but it also kind of takes it one step further, right? So the idea here is that your application is written in terms of very small chunks, just one function, right? And then the infrastructure would run your function in response to a certain event, right? So the event could be a multitude of many things, like a file was added to a cloud-based storage, or a user came to a website and sent a REST API request to my service, or a whole bunch of other things. So in this case, the cloud infrastructure would see that, OK, there is an event. I need to respond to that event within a couple milliseconds. Let me quickly bring up an container-based ephemeral set of resources so that I can quickly run this function, right? So remember that we've talked about virtualization and virtual machines, and of course, virtualization is the foundation of all things cloud. That's how infrastructure as a service works. Containers, which we had a video about in our course, containers are the foundational technology behind the serverless architecture. So the idea is that if you can have a set of computational resources in a container that you can very quickly bring up and very quickly get rid of, and by very quickly, I literally mean within milliseconds, you can bring up a container and then do something and take it down. Then you can actually try to do function as a service, right? Which again, I want to emphasize that this whole serverless architecture, function as a service, is really an extension of platform as a service model. But it's kind of like the new-ish approach that cloud providers are going to that model. Now, in this video, I will mostly talk about Amazon's implementation of serverless architecture, only because they were the first, the first cloud provider that went through this approach, and at the moment they're like they have the most comprehensive offering. There are others as well. In this video, we will focus on Amazon's version. Now it's called Amazon Lambda. I'll talk about Amazon Elastic Beanstalk as well. But before we get too much deep into that, I want to talk a little bit more background. I want to say, take a look at the journey of computational resources throughout the past decade. So, the whole computing started as you have like a desktop platform, right? So you have hardware you could buy from, any hardware vendor, Dell, HP, whatever. There's some sort of a hardware abstraction layer, and on top of it sits an operating system. Could come from Microsoft, could be Linux, could be whatever, Unix. So that was like the model 15 years ago, 20 years ago, right? Now, in this model, you have applications running on top of a middleware. The middleware could try to provide quality of service guarantees. It can handle events. Other third-party vendors could provide you with software development kits, SDKs, that are shown in this picture. And the software developer would basically sit on top of all of that, would write an application that would use that middleware layer on top of an operating system. Operating system will talk to the hardware. That was what was happening 20 years ago. That was before we had big data and we had clouds and we needed to do this sort of stuff. So basically, clouds came alive, right? So now, instead of having a physical hardware, you have virtualized hardware, right? So you have virtualized storage. In case of Amazon, could be, for example, Amazon S3, which we have talked about before. You have virtualized compute platforms and resources. Could be EC2 compute instances, for example, elastic compute units. You could have elastic load balancers and whatnot. And then you have a cloud abstraction layer in between what the infrastructure as a service provides you. And then you have some sort of a middleware running on top of it that tries to provide elasticity, virtual private networks, network DNS, so on and so forth. So the application developer, what would do, and this is now a little bit coming forward to the future as a couple years ago now, the application developer, the software developer, would write their application on top of now cloud middleware that we just saw in the previous slide, right? So you had elasticity and VPN. Now you try to run your application as a platform as a service. The platform as a service in this case, for example, could be Elastic Beanstalk, which I'll talk about in a slide in a minute. But that was kind of the model before. Now, as of a couple years ago, 2014, for example, there is this new term coming into life. They, the industry people call it DevOps, which 10 years ago, people used to call system administrations for the clusters. Now, the same sort of problem still exists. Now they're in the cloud. It requires an additional layer of knowledge, which I'm hoping that some of that knowledge we teach you in this class. And now people call that DevOps, and market is very hot for that sort of people and expertise. So this is still kind of like old-ish model if we're talking about function as a service or serverless architecture. Now, right now, with the serverless architecture, you have this layer implemented on top of all the cloud services that are implemented before, right? So we have something called Lambda, which I'll talk about, right? But now you don't need to interact with infrastructure as a service, which was what? EC2 and Elastic Load Balancer and whatnot, which you can still use, but you don't need to anymore. And now you don't quite even need to use platform as a service like Elastic Beanstalk and whatnot. Now you just write a function and you let the cloud platform figure out everything about the function, how to scale it, when to scale it, where the input data comes from, how the user's requests get routed to your function. Everything is pretty much now handled by the cloud infrastructure. So now you have Lambda in there. It can feed data off of Kinesis, which is another Amazon service which goes hand in hand with Lambda. It's for streaming. Lambda can work with EMR, Elastic MapReduce, which in another module we'll talk about MapReduce actually in the next course. And then you can talk to databases, cloud-based databases like Redshift that work hand in hand with Lambda. So Lambda is quite a game changer now in 2016, because not only you don't need to have your resources, you go to the cloud, you don't need to even get an EC2 instance and pay per hour. You write your function and pay per instance call of your function, which is a very interesting model. So before jumping into Lambda, I want to talk about Elastic Beanstalk, which you could say was and still is. It's still a service available. It's a stepping stone between platform as a service and function as a service, right? So in Elastic Beanstalk is what you would consider as a platform as a service. You write a program, complete program. The program can be written in Java, could be Python, Ruby, Node.js, PHP, Docker, whatever. And then basically the environment that the cloud provider provides you is a set of servers. Servers could, for example, the cloud provider can tell you that the server I'm providing you is Apache. And you write your program in terms of a program that runs on top of Apache. And then you allow the system to get to deploy, provide capacity provisioning, auto scaling, load balancing, health monitoring. But again, it's a whole program that you upload to Elastic Beanstalk. And then if it sees that, okay, I need more resources, it will go and grab one more EC2 instance and run more of your programs, Java programs, in another EC2 instance. And then it works with Elastic Load Balancer, another service from Amazon, which figures out how much load is coming to your application. And if the load passes a certain threshold, it goes and grabs another EC2 instance and run a server running your Java program. So now contrast this to the next slide, where I'm talking about Lambda. So Lambda is a complete event-driven compute. So when you're thinking about Beanstalk, you're still thinking about, OK, right now I have 26, for example, EC2 instances running my thing without me going and setting up, but there's EC2 instances. And if there's more load, the infrastructure will now launch another EC2 instance. Here in Lambda, you don't do that. You basically just give the whole Lambda infrastructure just a function that's like 5 lines of code or something, right? This function should be stateless. So basically, the function shouldn't keep track of what it has done before. It is request driven. So an event comes in. Event is a request for something. And your Lambda function can be written in a couple lines of code in Java at the moment, Node.js, or Python, which is the new thing that they've added on top, and it's very nice. Now, the event, now in case of Amazon, can come from another AWS service. I have a slide coming up showing you where other events can come from. But now in this case, you never think about how many EC2 instances are running my Elastic Beanstalk again, ever, right? So you only pay for the request served and compute time. So you can say that the infrastructure will keep track. It'll say, OK, so far I have run this service or this function, I don't know, 50,000 times. And the total compute time for these 50,000 invocations of the function was 3.8 seconds. And then you pay only for that. This is a very powerful way of thinking about implementing your your cloud applications. So now you can focus on business logic, not infrastructure anymore. You just upload the code. The framework handles everything else: capacity, scaling, you name it, monitoring, logging, fault tolerance, web service front end, deployment. You never need to think about patching security holes like zero-day attacks anymore, because you don't care about the environment running. In this case, the cloud provider, Amazon engineers, will always make sure that your function is running on an infrastructure that has all the security patches for zero-day attacks, everything already implemented. So that's a very interesting, very powerful way of thinking about business logic. Now, where do these events come from? Now, in case of Amazon, they can come from a multitude of different cloud services that the infrastructure provides. So, for instance, it can come from S3 as a response to a new file being uploaded to S3. You can set it to launch a certain Lambda function that you've written, or a file changes. It can come from DynamoDB. Now, DynamoDB is it's basically a key value store provided by Amazon, right? So if something you can put a watch on a certain column or something in DynamoDB, and if that changes, that becomes an event, and a certain function that you've written can run. Actually, this is a good time to mention that your Lambda functions have to be stateless. You cannot have state in your Lambda functions. Now, your business logic might require to have state. I mean, pretty much any useful program has to deal with states. This is achieved in this sort of architecture by storing your state in DynamoDB. Now, DynamoDB, you can think of it as memory-based, more or less memory-based. So you can think of DynamoDB as memory-based key value, distributed key value store. In the second part of this course, we talk about Cassandra a little bit. So DynamoDB is kind of like Cassandra. Very fast, very scalable. You can store key values and retrieve them, and since it's all stored in memory, it's very fast. So the idea behind this sort of architecture is that your Lambda functions could actually scale up, could scale down. Sometimes they could fail, and the infrastructure might decide to run something again. That's why they should not handle anything regarding state. All the state has to happen outside your Lambda function. Other events can come from Kinesis streams, which is kind of the streaming platform that Amazon is actually trying to provide. It's also a very new offering, and it kind of works with Lambda. It's very cool. From many other parts of Amazon, you can have that, right? So you can have from simple notification service, looking down the list, CloudFormation. You can have like deployment, and then you can actually get events from that. CloudWatch, of course. Amazon CloudWatch events that you can get, like scaling notifications. You can get load notifications. Everything you can actually all of those events you can use in triggering Lambda functions, and a whole bunch of other things. So I'm not going to go over all of them. Now, the execution environment for your function, as I emphasized before, the functions have to be stateless. You are still allowed to use pretty much any sort of resource usage that the program environment gives you. So for example, if you're writing your program in Java, Java allows you to do multi-threading. So you are allowed to use multi-threading if you wanted to. Right, it gives you a /TMP temporary storage space of 500 megabytes per function. So if your computation needs some sort of a temporary storage, you can use that. Again, remember that you shouldn't use this as sort of a consistent state storage. It's more of an ephemeral little bit of space that if you really need to write something and quickly do something about your computation, and then get rid of it. But you should again remember that this is just per function invocation. I mean, that's the guaranteed stuff. Once your function is done, that /temp could go away. So the other very important execution environment setting that you pretty much need to think about is how much memory you need for your function to run. RAM, of course, I'm talking about. So this can be set by the developer, by you. You can set it to be anything from 128 megabytes to 1.5 gigabytes. You can set it in 64 megabyte increments. So 128 megabyte, 192, 256, so on and so forth. Logical question here is that, okay, what about CPU? CPU is also a very important resource, right? So your function could need, lots of CPU, little bit of CPU. So in Lambda model, at least currently, CPU scales with the memory requirement that you've set. So for example, if you say, 128 megabyte, and then for another function you say 256, the one that you've set to have 256 roughly gets twice as much CPU time, CPU resources, compared to one that you've set to 128. Finally, the function should finish in a certain time. So, and if it doesn't finish after that certain time, the infrastructure would just assume that something failed and kill it. The default timeout for each function is 3 seconds. Although you can set it up from anywhere from, if I'm not wrong, 1 second up to 300 seconds. And the infrastructure will just wait for that much. Finally, I want to just quickly talk a little bit about how the pricing works. I think this is very important. This is why this model, this cloud computing model, is getting so much traction in right now. And I guess I should again emphasize that this serverless architecture is a very new trend. We're talking about 2015, 2016. Here you pay per use of your function, right? You don't again. So when the first time we were offering this course back in 2014, we didn't have this, right? So you had to grab an EC2 machine, and whether you were using it for like 10 seconds or half an hour, you would pay for a whole hour. Now here, you are basically just paying for the use of your function. And it's actually pretty cheap. It's 20 cents per 1 million function call, plus that very small amount that you see, $0.00001667 for every gigabyte seconds used. So if you set your function to have, 1 gigabyte of memory available to it, and if your function runs for 1 second, this much time is added. This much money is added. So as you can see, it's a very powerful model. Scaling is automatically built into it. You as a developer don't need to think about, okay, now I need to elastically go up and down, get more EC2 resources, get less EC2. Now I don't have enough load anymore. I don't want to pay too much. Now I have to release my EC2 instances. This is just great. So to wrap up, this serverless architecture is becoming very important these days, and in reality it's implemented on top of the other sort of cloud services that we've talked about, EC2, S3, and whatnot, and really the foundational technology that allows a cloud provider like Amazon or other cloud providers to provide such service are containers that we've talked about in a previous video.
So we've talked about companies. Now let's talk about what is the actual software they're using and how do they construct all of their clouds. The first lowest level I want to talk about is MAAS, which is metal as a service, and that's providing bare metal machines, CPU, memory, disks, networks to particular people so that they don't interfere with each other, so they have the ability to build whatever systems they want. Now, on top of that, you can build platform as a service. And this sort of software is like the operating system, OS X, Windows, Linux. You can build a particular platform to serve a particular purpose. One of the most famous ones would be, to put up a Java environment and let you then build on top of that Java environment some set of services you like. On top of that, there's software as a service that deals with providing software systems and allows you to go ahead, say, build a web service with the web front end, load balancer, with some databases and some file storage. If you wanted to get really sophisticated and sort of cutting edge, you would also think about building mobile as a back end, MBAAS, and there what you're considering is mobile phones using the cloud to provide services, voice recognition, looking up maps, destinations, routes, really accelerating what a mobile phone can do. We will go into how MAAS works in some detail, just sort of showing how the hardware all fits together and how the whole system operates to bring up a core set of machines for you. We'll talk about Juju, which is a really neat sysops, sysdev way of managing the system that you've got. So you can say choose Hadoop, put up Hadoop on these 20 nodes, and it will go ahead and do it for you automatically. So we discuss that. We'll look at different sorts of platform as a service providers next, like Google App Engine, Salesforce, web services. We'll look at sort of different semantics, RPC semantics for the cloud. We'll look at how the cloud is structured using REST and SOAP and employs JSON. Then switch over to just how load balancers operate and spread the load so that if you're accessing a web, you could be accessing, say, tens of servers providing you that service so that no one server gets overloaded from all of the communications. We look at protocol buffers and Thrift and how data is actually transferred and smooth so its access is uniform and you get predictable behaviors. I want to introduce you to Metal as a Service today, and we're going to look at an interesting innovation trying to make Metal as a Service operate just in the same way that CloudStack or other cloud resources work, that you can allocate resources and remove them at sort of the user's request. And the notion is to very much replicate that whole feeling of the cloud, that you get to use the resources when you need them, or when you don't, you can stop paying for them. We want to replicate the sort of feeling that the users can actually go and build their own types of cloud computers and customize it to the applications, to the needs that they have. So today, let's look at Metal as a Service. It's actually abbreviated as MAAS, and we'll define it. That what we're trying to do is to combine scalability and flexibility of the cloud with the ability to harness the power of physical servers instead of just having virtual machines or virtual processors or containers. We're actually going to give people real machines for the duration of what they want. Now, on top of that, they can run their own whatever. They can run VMs, they can run containers, they can do Kubernates, whatever. But the essence here is that we're actually giving those users physical machines to access. They can do whatever they want, they can organize it however they want, and then relieve them of the cost. Of course, DevOps, operating the whole thing, becomes an interesting question, because now what you would like to do is to make it as efficient as possible for users to configure the machines they're given appropriately for their task as easily as possible. And we'll get around to that later with Juju. But first, let's concentrate on MAAS and see how MAAS operates. So the use case is that you want another server machine or multiple server machines to actually conduct a service that you giving to third-party people. You're a user perhaps. You want to find a provider that will give you this. You don't want to buy a set of machines and have all the costs of installing it, installing a network, provisioning it, paying for the connectivity. All of that you want to just sort of pass off to the server company. And you want to still retain that flexibility. If you want to put in Ubuntu, or you want to put in Red Hat, or you want to switch and use Windows, you shouldn't be limited by this whole system. And similarly with your disk drives, you want to be able to configure those disk drives. You want to be able to say how you want to organize them, how much space, whether you organize them in some sort of RAID or whether you separate them out. And you want to take the network and partition the network, use the network in whatever way is best. So if you're going to stream data from a database into some web apps and then take the web apps and stream those out to a bunch of remote folks, you should be able to organize that network so it provides a path. You may have firewalls, you may have network address translation schemes and hide the database, but you should be able to organize it, and you're going to do it on somebody else's hardware. When you've set this up, you want to protect it securely from the outside world. And of course, if you're building something which is organized around the web, you have the whole internet there to try and interfere with what you're trying to do. So we provide service credentials. They're built into the mechanism. They're well, in this case, they're SSH, based off a user ID and then a public key. And we use that to secure the communication. It'll be encrypted with a private key, talking to the actual hardware that you instantiate, so that nobody else can break in and interfere with your operations. When you've reached the conclusion to this, you've actually provided your service. Maybe it's just for a weekend, maybe it's just for a football site, and everybody's watched the football and now you can just take it down. Well, you don't need the server anymore. You don't need to pay for it anymore. You can just return it back to the server organization for them to use for somebody else. So there is a mechanism to do this. And in decommissioning that particular server, you can also wipe its disk. You can do that remotely from your client point of view, and the server will guarantee that it goes through and does cleanup. So this is the sort of organization we're talking about. MAAS is actually a company. It's spun off from other companies. What it provides is a set of components. The software for those components are actually part of an open source release that you can download. If you go to maas.org, you will find all of these. You will find descriptions of this, and you can actually set up your own MAAS server and play with the whole system, either doing it on something like VirtualBox, or doing it on real hardware, or just doing a single installation. Or you could even put, believe it or not, MAAS on as a componentized system in Linux and run it that way. So it is a very flexible system. The key thing that underlines it is that they have modularized all the components so that they don't interfere with each other, and so that they pick up all the necessary libraries and so on to run those components in whatever environment they're actually operating. So we'll look at the bare machine for the moment, and we'll discuss this diagram that I've got here in terms of that. What you'll see is that there's communication with something called a region controller. Whenever you talk to MAAS, actually you're going to be talking to this region controller. And this region controller will, say, operate on the East Coast or the West Coast, or maybe it's the Midwest. It's going to provide you all of the web interfaces and the APIs to access your machine as it's brought up and put down. Within that, there's going to be different clusters within the cloud, within the machine room. There's going to be different clusters, and those clusters will be supporting multiple different CPUs, and you can see them listed there as nodes. They all have their own disks, they have their own networks, they're connected into a global network. There's a cluster controller that will talk to these individual nodes. The cluster controller is actually where the business occurs. The cluster controller is going to reboot these nodes, and it's going to supply operating systems for these nodes. It's going to respond to your requests at the web level by doing appropriate things to set up each of the nodes just exactly how you specify, and then it will turn those nodes over to you to do your cloud. I'd like to sort of just point out a couple of details about the diagram. One is that this whole thing relies very heavily on remote boot. All of those nodes are going to get their boot images from a boot server, which is probably part of the cluster controller. It could be off on a side, but more economically, it's just sort of in the cluster controller. It's going to be using protocols, PXC, to actually do the boot. There are going to be some sort of slight issues about how you control the power for each of these nodes. So you want to be able to switch them on, you want to be able to switch them off, you want to be able to recall them if they get attacked or if they have got into a loop. And so there is an IMPI server, IPMI server, I've got to get the right way around, on this cluster controller, and IPMI can recycle each of these nodes through the Ethernet, so giving the controller absolute sort of operational oversight on all of the different boxes. Because this is its own environment and you're bringing nodes up and nodes down and you're serving all sorts of different requests, there's actually a DHCP server associated with the controller, and that supplies the names for all of the different nodes. And as you're building your infrastructure, your hardware, it will actually, following your instructions, devise networks that are appropriate, the ones that you want to actually manage your systems within that sort of IP address space and that sort of network space. So that's the overall hardware. You can have multiple clusters, and typically you might have racks. I haven't shown them here too much, but the clusters actually may have racks, individual racks within them, and the clusters might be spread a bit geographically, or they might be in different locations within a city. There might be some proximity, but overall you have a mechanism to geographically manage a lot of different machines so that you can actually allocate machines close to the users if that's needed. So MAAS is a system that brings up these physical nodes. It goes through a process of finding the nodes, which is in this list it's called discovery, or enlisting the nodes. We'll discuss that a bit. How it does it is when you bring up one of the nodes, you configure the nodes to actually do a PXE boot, and MAAS listens to the PXE boots, and when it hears a PXE boot, what it does is to step in and provide a response and allows that PXE boot to download an operating system just exclusively for MAAS. We'll discuss that in a second. After you've gone through that, we're going to have an enrolling phase where we record all the details about the machine that's been discovered, and we set up data structures and so on so that we have a record of exactly what's on the machine, so that as we sort of craft our software for the user to run on that machine, we have all the data that's needed. Then we go through a commissioning phase. This is where a user requests a machine, or can request multiple machines at the same time, and then you get parallel commissioning. What will happen is that the machines themselves will receive requests about how to set themselves up, how to configure themselves for their file systems and so on. And then specific to the user, you're going to get a user password and the key, the public key, so that the user can actually access that node directly without going through anything else. And then it's up to the user to configure the rest of the machine, or however the applications want to be used. Once that's all happened, then you can actually deploy onto the architecture your favorite operating system, your favorite file system organization, and so on. So that's the deployment. So we'll see those 4 phases in another diagram I've got later on. Let me just show you what the overall impact is. This is taken from our SRG site, and you might not be able to reach it. So here's a screen of our local systems, and we put up MAAS on a server there. MAAS is serving 4 different clusters, in fact. what you can see there is the first term's LAN port. That's one cluster. As we move down here, we've also got some machines, Phoenix and Mustang. That's a different, two different other clusters, and the fourth cluster I'm trying to build at the moment. So this is all happening. The LAN port, you notice we've numbered them according to where they are in the racks, and they're in various different states. They all have their power on. There's a green symbol here. Some of them are deployed and actually being used by users. Some of them have broken or their software is upset, so they need recommissioning. You can see a lot of the machines here are actually deployed. Some are broken. Here's a broken machine. There was an allocated machine. It's been allocated to somebody, but they haven't actually started using it for any purposes at the moment. Down here you can see failed deployment, meaning there's something wrong with the machine that didn't allow it to deploy. So you get lots and lots of statistics and information about it. This is the list of owners that own those machines for the purposes of using them, building their own systems, doing experiments. And then we have their organization, how many cores they've got. That's processing units, CPUs inside each node, how much RAM each machine has, how many disks they have, what the storage capabilities of that particular node are. Well, we have a summary here, allocated. We got three nodes which are in state allocated, 5 which are broken, need me to go and fix, 52 which have been deployed and are being used by students for research, 6 that are stuck somewhere, 21 which are stuck in, they've been deployed but they didn't work that well. I should say, I've got some work to do. And then 6 that when we released them, the software didn't actually release them and I need to go and fix those. You will see that I've got owners and I can look at all the owners in the system. I can also then browse. Let's see if I can get rid of that. Well, should have gone away. All right, well, I'm just going to, I have some tags to say what these machines are doing. So there's different fabrics, different spaces. Oh, here you are, here's the tags. Some of these have GPUs. So if I just want to look at the machines with GPUs, I can. If I want to look at the machines running Juju, and one of these machines is actually running Juju, I can click that one. So that's this machine. I can look at subnets that the machines are running on. I can look at what sort of networks they are. I can look at, an SRG space as a whole. Each of these would select machines to actually look at. So let's go back and we'll select nodes again. And wherever that was. I will look at the status of each of these. How am I going to do that? Oh, I see. Get rid of that thing. There you are. Look at the status of each of these, and what you notice is that I can do various operations on each of these machines. I can talk about a particular machine, a particular chassis. I can go here, for example, look at a particular machine and see what it's doing. I can look at how it's being controlled. The power is controlled, turned on and off. This is using IPMI. It's under administrative control, it says there. The password is hidden. I get to see the network it's on. It's got 2 networking devices and it's using Ethernet 0. And I can look at the storage. And in fact, I can look at a lot of the detail about the storage. And if I went over here, and I've got to be careful because I could do something drastic, I could turn the power on or turn the power off, or release that software, or mark it broken, or delete it from my MAAS infrastructure. So this interface is pretty powerful. If I go through, well, I'm not going to do it, but what I can do is to go through and just sort of cycle a machine, turn it on, turn it off, all from this console, without ever having to go into a cold environment and play with the machines directly. So that's the console for MAAS. So let's now get into the detail of what actually happens when I click those commands to commission and deploy the networks. So here's a diagram of the cluster controller, a node. We'll choose node 3 just for the sake of it. And we'll have a node 5 that's already running somebody's operating system, let's say Ubuntu, as part of the example. And what I want to talk about is just how the cluster controller allocates and deallocates nodes. So let's suppose we turn node 3 on, then what it will do is to want a PXE boot. We've set it up with its BIOS to do this. It will send a message out across the network. The cluster controller will intercept it, and what the cluster will do is to actually boot an ephemeral operating system. It's a lightweight operating system that will allow us to control node 3. So now we collect from that ephemeral operating system what it observes is actually on the machine, all of the hardware configuration and so on, and we bring it up to the cluster controller. So the cluster controller now has a record of everything that's on that machine, and that's how you find out what the disks are, that finds out what CPU, what the speed of the CPU, and so on. So now we've got that configuration, and what we can do is to build scripts that will be useful for node 3. For example, if we want to do a custom boot, we can provide the parameters to that custom boot so that it knows what disks and so on to be used. We are going to be sending tarballs to node 3, tarballs being software and binaries that have been compressed into an archive. We will send the archive across to node 3, unpack it and install it in node 3 so that node 3 gets all of the software it needs to do particular task for the user. So when we know what the user, when we have a user request, the user will be requesting certain issues, setups for that node 3. We'll be able to extract the right tarball, match it against the configuration, perhaps add some parameters, limitations on how much fast storage to use and so on, and then that tarball could get downloaded to node 3. So this is all very automated. Let's suppose we have a request coming into our RAID controller coming into MAAS effectively, saying, oh, well, let me add a piece of equipment to my cloud that I've got. Well, what's going to happen is I'm going to get an IPMI request saying, please turn the power on node 3. And you see the diagram labeled 5. Node 3 will boot, and as it boots, it will do a PXE boot. That PXE boot, we know that it's got all sorts of things on top of it already installed, and it's being configured. But that PXE boot, what it's going to do is to download the next boot that we want to accomplish on node 3. Let's suppose we, switching to Windows or something, we would download that from the cluster controller. That request, the boot image coming back, would have some scripts associated with it, Kickstart-like scripts that tell it how to configure itself, how to configure the boot for all of the entries, all of the hardware on node 3. And so now you've got a customized system being built, and then we would download the rest of the boot software and so on as a tarball using Curtain, install it all, and then reboot into that untarred image, so that now we have a system with exactly what the customer wanted loaded into Node 3. And then we're going to turn over the access to Node 3. Part of what will be passed over as well in this sort of customization will be the user username plus the key for talking to it, the public key for the user to talk to that Node 3. And of course, the user will have to have a private key to match the public key. Now, later on, after the customer is really happy with everything that's happened, he might want to say, well, I want to cut my costs. I've finished everything, so I'm going to turn this machine off. So the next thing that happens is that we would get a region controller, remove the machine, delete, whatever. And I haven't quite quoted the actual official entry there because I just wanted it to fit on the slide. But you get a region controller request to remove that machine, and in this case it's machine 5. And what will happen is it will just do an IPMI request to that Ubuntu Node 5 machine, turn the power off. Now you notice that this control is completely separate from what the user might be doing on Ubuntu. He might have logged into Ubuntu with his user ID and his public key, but this thing, if it turns it off, it's going to turn it off irrespective. So the power, the whole control of the system remains with the controller. It doesn't remain with the user, and the administrator for that controller can always step in and take control of a node, bring it back into the fold, and get rid of whatever software is in there. So it's a very, very powerful allocation mechanism, and now we're going to see what you can do with it. So the notion is you've got a pool of nodes. Those nodes can be allocated to users. Each of the users can have user authentication credentials for remote access to the nodes they've got. And if they want to set up some other sort of domain of authorization, they want to use AD on those nodes, well, they can set that up with their user authentication and their credentials. They would set up the AD domain and everything else, and away it would go. So it's a sort of bootstrapping process, but it's all provided with this mechanism. They can tailor what they're doing to the memory size, the number of cores, and they can choose their operating system, the application to run on a node, and yes, when they finish, or if they don't pay the installments, the nodes can be returned back to root. What you get is really a sort of autonomous computer subsystem, a set of computer interface specifications and a way of accessing these that's sort of under control of the controller, but the user thinks that he's got control of it completely. There are managing and monitoring capabilities that are provided to this system, and there's a host of independent host systems, CPU, firmware, and so on. All of that is the responsibility of the cluster manager, the cluster owner. It doesn't have to impact the users at all. We've abstracted from it at all, completely. Now, we talked about power management, and just briefly, that's done by IPMI. This is a diagram of the IPMI system, and it's been in systems since about 2004, especially those built for clusters. What it provides you is two parts. One is the IPMI protocol, and the other is a BMC, which is a controller allowing you to control how a machine is booted, what its power states are. It allows you to communicate with the South Bridge, the IPMB, and all sorts of things. So it's got lots of different accesses. I'm not going to go into all of them. You can actually run this whole thing through serial ports if you want, but typically the way it's deployed with MAAS is to use the NIC, the network. And the NIC, you would send commands over to the IPMI commands essentially, and they would get interpreted by BMC to do the sort of things that we've been just talking about. Here's a broader view of how all that's put together inside a server. I don't want to dwell on all of it, but what you'll see is that on the motherboard, there is a baseboard management control of this BMC. There's LAN interfaces in that connect the IPMI protocols to the baseboard management systems, and that baseboard management system sort of can really operate independently of the CPUs and everything else in the system to actually manage the system. You notice that it's connected to the fan, temperature, power control, and reset control, just the sort of things that you need to know about and to be able to manage if you own the hardware itself. So IPMI usage is pretty simple. You can use it when the operating system is booted or when it's powered down. That particular device, the BMC and so on, are still live. As long as the system is plugged in, they're still running. And so if you have a system failure or any other problems, then you can use IPMI to go in, try and power cycle it, try and find out what's wrong, try and get an SSH to work with the system. So it's a very, very handy way of managing those systems and preventing the customer from having to know about any of the actual contents. Just think of the advantages. We can take somebody's web deployment, and if their hardware goes bad, you can switch their software to another system and have it running, and you don't actually really have to have the customer interfered with at all. He can keep up his service, and you're managing the hardware replacement. PXE, I mentioned that's just a boot process. It's what happens when you turn the power on. The BIOS will boot off the network. It will go to a PXE stack and do a network boot. It basically downloads the bootstrap from using TFTP from a server and then runs that. And you can implement multiple stages of bootstrap as we demonstrated, because that first bootstrap might actually then go and download something else, install it, and then reboot the system. So PXE is a very flexible way of getting hardware to the right sort of configuration, and it's another protocol over the internet. What we've done is to show you how you could control physical machines just like a cloud, but actual physical devices. We've turned those devices over to the users, and the users are now left with actually doing the DevOps, managing what's running on those systems, and they can put up whatever they want, and it's not really a cloud provider's problem to do so. But there is a tremendous advantage if you're selling services on the cloud. There's tremendous advantages to providing help to the user to configure those machines the right way. And that's one of these is Juju. Now there's other systems, other schemes. I chose Juju because it's open source again. What you can do is to provide services, lots of different services, and you can think of them pretty much as atoms. They're not really divisible. What you can do is to download them and run them. And if you want to glue them together, that's fine, but sort of trying to split them apart is not what you would be doing. Each of these services have dependencies, and they provide services, and that's recorded in scripting and in declarations and configuration files. And there is some software that Juju provides that will run through all this and organize those systems for you. And what it will do is to maintain elasticity. So if you have a web server and you want to move it from, say, two machines to 3 machines or 4 machines, Juju will actually allow you to do that. It couples services together in a distributed way using basically networking, but they usually highly cohesive, meaning that they're forming part of some system. Say if you're building a web service, you're going to have a database as well, and they're going to be tightly coupled together. It works at the user level. Once you get that user ID and you have your public key installed, then you can use your private key to come to this system and install whatever you want using Juju on the machines you've got. So let's suppose you want to do a Hadoop and you acquire 100 machines. Then what you can do is to download, using Juju, Hadoop onto those 100 machines with the controller for Hadoop and with all of the node instances for Hadoop and all the other bits and pieces, and install it and start to use it. If you want to use HDFS, that will be another Juju element that you can download, and it'll be integrated with Hadoop. It'll know about the tables, and so it'll boot itself or get itself started under your control and interface there. So what it does effectively is give you fast DevOps, and it allows users to use MAAS very effectively. Now, should you actually want to go the route of OpenStack, and we've talked about some of the advantages of OpenStack, some of the issues, you can put OpenStack in MAAS and Juju will actually do that for you. So you can choose even to have very flexible environments on the machines that you're provisioning there. So supports OpenStack as well, really sort of interesting. The way it all works, it has charms that are written as shareable, reusable, repeatable expressions. Typically, the way that people like to think of them is, if you're in DevOps, you record the best practice way of bringing up Hadoop, or the best practice way of bringing up a web server, or the best practice way of starting a distributed file system. Those will be well known, so why not just record them as scripts, parameterize them by the hardware, and then basically install those as a charm in this system, and then when people want to use them, they invoke the charm gets distributed to their machine and gets invoked and does the right installation, again using that sort of tarball idea. So you can use them unmodified, or if you want to change them, you can. They're like a package if you like. You can remove it if you want, and it really does. Well, Juju actually will work across most of the stacks for clouds that you can find in the world. So if you want to run it just natively on OpenStack, you can. If you want to run it on Amazon EC2, you can actually run Juju there too. So here's sort of examples of some charms. There's over 300 charms that are provided. Ceph is a file system, distributed file system. So you can add lots of elements, lots of nodes in that file system with their own disk stores that are all integrated into the distributed file system. You can have Hadoop, as I mentioned. You can do DB2. If you're into containers, then you can run containers using Kubernates, and that's a charm. If you want to use databases, text-oriented databases, you can use MongoDB. You want to use relational databases, there's MySQL. If you want to play with in-memory databases, there's Redis. If you want to do streaming, you've got Spark. And if you just want to play web services, you can use WordPress as a complete package. Often enough, what you find is that a number of services are bundled together, and guess what? They're called bundles. So Apache MapReduce is put together as a bundle. You can install a bundle of services to make things a lot faster. Similarly with Spark, you have lots of different, you've got some dispatches and other elements to it. You can put that into your system as a bundle from Juju. Here's an OpenStack. This is the OpenStack charms, and then just a communal garden web server on the right-hand side. So lots and lots of different ideas. If you want to play with us, you can actually do that at little risk. There is a demo package up on the web by Canonical. Canonical is responsible for many of these systems in the way that they've promoted them and provided software support to build them. You can go to demo.jujucharms.com, and if you run that, you will actually see Juju in action. So this is Juju running off those Canonical services, and what I can do is just click and point and build the system I want to install on my MAAS node or nodes. So if I want to choose, well, let's say I want to choose WordPress, then I can add that, and this is called a canvas. I can say add a database to this so that my WordPress can refer to a database. Let's say, what should we have? Well, let's just choose MongoDB because it's there. So I can add that. And then if I want to say that these services are linked together, so I can actually, I'm not sure if I can do this. There you go. What I can do is to link them together. Link them together. How do I link them together? Let's try again. I don't know why that's disappearing. There you go. Then they're linked together, so the WordPress will know where to get database entries if you starts making requests for SQL. So you have a sort of mechanism to build very complicated systems, and essentially you can configure. You don't have to do all the DevOps yourself. All right, well, that's coming up to near the conclusion of this lecture. Just to summarize then, we have interactive construction on top of dynamic allocation of nodes. You can configure this however you want. This is, in a sense, a coming direction of a lot of clouds provisioning, and gives the customer total control over what happens on the nodes. Thank you. So the Google App Engine is one of the leading platform as a service, so it's a good idea perhaps to just sort of look at some of the features that it offers and why that platform as a service operates the way it does, and compare it with the infrastructure as a service. So the Google App Engine, developed in 2008, it's multi-tenancy, therefore it's fairly cheap, offers automatic scaling, so it's flexible, and you can charge and you can change your costs very dynamically, supports very common programming languages. They're all high-level languages, they're all interpretive, they're all scriptable as well, so that makes it very flexible. The framework that Google supports for building webs is Django. It has a Grails web app framework if you want to write an app for the web. This allows it to be used for many, many different services, and people find that very popular. Its infrastructure tools allow you to deploy code without worrying about infrastructure challenges such as deployment, failover, scalability. They're all taken care of by GAE. However, the infrastructure limits the type of applications that can be run. As you can see, there will be lots of constraints between what you can build and doing reliability, failover, and so on. And so GAE keeps you in that safe territory where you can only build things that they can support. So applications run in a secure environment. Typically, when you communicate, the network will be encrypted, and when you're running on your your environment on the cloud, it will be running in a secure environment provided by whatever is actually doing the hosting, Java or whatever. Essentially, the sandbox is built around those interpreters so that one client can't interfere with another. It isolates applications from hardware, isolates the applications from the operating system, and they all impose security limitations on what can actually be done in those compute engines. The application code only runs in response to requests, and a request handler cannot spawn potentially malicious sub-processes after a response has been sent because of the interpretive nature and the checking that goes on in these systems. The GAE data coming from this is stored in the App Engine Data Store or the Cloud SQL or the Cloud Storage to be later used in the Google App Engine. You can actually use the database technologies that Google's developed, like Bigtable, but again, you're providing it is a very safe environment from the security side in providing or making all these provisions. So you can take advantage of Google's single sign-on when you sign up for a Google ID. You can use that to do all of your computation with the platform. You can build Chrome and Android games on GAE using again the sign-on. You can also do cloud endpoints to allow mobile services to get into your cloud and update or download information, and again that all uses the same authentication. Other services provided, there are MapReduce engines that you can call from this system. You can search APIs, you can SSL support for security, you can run Memcache if you want to. There are lots of different APIs. So you might say this platform is very flexible. There's some examples here of how flexible it is. There's BugSense. It's an application error reporting service, and it's used by GA to maintain logs of bugs in software and analyze them, but it's actually also provided to customers for their applications themselves. Ubisoft is used to build web-based games, and so you can build your own web-based game very easily. Claretics is a small social analytics company, and it's used a lots of this platform to do that. And again, some of that facilities are around available in GA to do your own types of building. So in general, because it's of the languages being used, the languages are very concise. They don't take many bytes to say very powerful things. Lots of cell phone apps have been built to use GAE. They have a backend like Ruzzle and Tapzoo to actually sort of make that simpler. And what it does is allow you to scale very well. It fits the GAE's purpose of providing this platform that's very scalable and modifiable, and you can do that very easily with small teams of developers. So it's a great way of introducing new business to the cloud, and has been very productive for Google. Salesforce is one of the main providers of platform as a service, or should I say software as a service. It runs a complete sort of solution for clients. It also allows them to build their own solution. So there's a little bit of discussion, platform as a service, software as a service, but nevertheless, what they have is made this cloud computing their own from the point of view of providing CRM services, that's customer relationship management services, to customers. and in the past they actually managed to displace major CRM businesses with this style of approach of providing a cloud that does that. So they are now sort of moving into other areas of cloud computing from that sort of basis. So although it's not as well known and sort of dominant as Amazon or Google, nevertheless, this particular Salesforce company is an example of how you can make clouds really sort of a platform for a whole new generation of innovation and services. So what they offer: sales, service, marketing, analytics, communities, and lightning deployments of systems. They offer this sort of very, very flexible, very fast system for basically companies providing facilities that Microsoft didn't actually fulfill. Microsoft's much more in the Office style support. These guys are much more in the, if you like, how does a business network, how do you put a business network together to make the business successful? Whereas Office and Microsoft are working on the back end inside the Office. How does that all work together for the accounting and so on? So you could think of this as social software for the workplace. Their competitors are Microsoft, IBM, JIVE, Salesforce obviously is prime contender in that. So the idea is each business wants to find out about each other and to build networking, build professional connections. They want to mine their networks for contacts, acquaintances, get advice, references, referrals. They're forming teams, business teams, different businesses together in a team as well, communities, informal groups, and collaborate on particular work projects. So CRM services allow you to discuss and comment on work, organize work from an individual group perspective, identify relevant information, discover other people with common interests, alert users to information, learn from other users' expertise. Salesforce uses Wave to build all this, and they have a Salesforce Analytics Cloud. So from when Salesforce started, what they provided was this platform where you could piece together various pieces of this service to provide you with customer relationship management, and they did it at a rate that was very reasonable for companies, and you could scale it as your company grew. You could build a bigger customer relationship management service, which allowed lots of small businesses to start up actually using CRM and taking advantage of that networking to start finding their own way in business. And it was so successful that Salesforce became, if you like, one of the leading flagships for promoting cloud computing. We described how to build clouds and how you can create scalable cloud services. The question is, what sort of services would you provide? And if you like, 101 is web services, providing just the feasibility of a scalable web server that can cope with multiple requests and an increasing number of requests that would require more servers, and perhaps that fluctuates from being enormous to a small amount. You can imagine, for example, the Olympics. The Olympic servers you might just have one server serving everybody, but as we get close to the Olympics, you're going to want a large number of servers providing Olympic information, and That's going to scale up over the period. If there's excitement about a particular event, you may have to duplicate servers for that particular event, serving out the web requests. And then eventually it'll be history, and you can shrink that whole operation down. You will have seen from the previous descriptions with, say, OpenStack, that what you can provide is an infrastructure to do this. But what we didn't describe is just how would you make a web service that's scalable and can operate that way. And in this lecture and in the MP you're going to be doing, what we're going to be exercising is web services and the ability to be able to scale. So overview today will be, well, how do you provide web services? And that might seem simple to a lot of you, but hold on, as we go through it, there will be ramifications of what we're describing that might get a little bit more complicated. We're going to talk about how web services can migrate into providing remote procedure calls using SOAP and RMI. And this forms the basis for doing many of the operations that you saw we needed in order to be able to run OpenStack or even Mirantis. That they communicate from the front end, a dashboard, to various servers, and they use protocols to do it. And those protocols are based on HTTP and actually SOAP underneath. Well, later we'll find out they use JSON and XML and all sorts of other things. What we will then go and talk about is a prescribed way of using HTTP that records state associated with HTTP, so individual HTTP requests can move you through the state. Effectively, the server behaves like a state machine, and the requests come in and move you through that state machine, and that description is called REST. We'll describe that. And then we'll go for richer descriptions of HTTP, JSON and XML, which add information on or above just straight HTTP requests so that you can have a richer communication environment. The reason for all of that will be we'll get to load balancing, and what we want to describe is a situation where you provide a web service for lots of people, and as those people increase, what you would like to do is to take their requests and move them to different servers. You're going to use load balancing to do that, and you're going to exploit some of the features that were in those earlier protocols to allow you to do that easily. So that's the name of the game. And what we're going to start off with just talking about web services. We're going to ease into it, and then by the time you get to load balancing, you'll see why we're being careful about defining our terms. So this is the notion. We're going to introduce you to web services and load balancing. And typically you're out there in the cloud, in the internet, you're accessing through whatever mechanisms, but it'll involve routers, into your data center. There will be a server in the data center, and that will be running on its own machine. All those requests coming off the router will go into that load balancer. Typically, the load balancer doesn't do very much. What it does is to farm out those web requests to different servers. It makes sure that if you're a client A, say, you're going to go for web service to a particular server A in a consistent manner throughout your session with the cloud. The next time you come back, you might go to a different node, but this time you will be going to that particular node to provide the service. So the load balancer is going to look at the overall incoming requests, and it's going to say, well, I've got a lot of load on these machines. I need perhaps to create a node with a new web server for you. It puts it up and then lets you talk to it. So what it's in charge of is fair sharing, if you like, or sharing out all those requests for service amongst the available servers. And if it doesn't have enough servers, it will go and create extra ones as necessary, depending upon how sophisticated the load balancer is. So once you actually farm out the request, and you notice the flow goes down we've got the internet here. It's going to go down through the router, but the load balancer is going to send the request to the individual web servers. They're all going to be sort of identical, duplicates of each other. They're going to provide the same information, but they're going to respond particularly to one particular person. That web server is going to reply to you with the results of your web request. And so that will follow the network back to you. So there has to be a linkage between your request and the reply. Well, the techniques for doing all this are commonly lumped together in one definition of software. It's a sort of middleware layer for the web. Basically middleware that provides services to applications beyond those available from the operating system point of view. The middleware allows you to have libraries, all sorts of different services. So typically the web services will be classed as middleware, and what we're going to describe is how all those components that are needed to make this happen. So why middleware? Well, what we're trying to do is to provide those functionalities across different applications, across different types of implementation, trying not to try not to duplicate software that we don't need to, and also making sure that people don't reinvent the wheel, don't have all sorts of different ways to do the very similar things. So what you're going to find is that there's middleware for HTTP, there's middleware for the web services, there's middleware for JSON. All that stuff is implemented in that sort of layer. And what we're going to be doing is building distributed systems. They're going to be very, very identical to each other for maintenance purposes. They're not going to be that different from a single node. They're just going to be tweaked, if you like, so that they work in a distributed fashion. So here we've got the applications. They're going to want to communicate down to your cloud systems. Those cloud systems are running operating system services. The middleware is in the middle, and it implements all different functionalities. It's going to get data for the HTTP requests. It may implement remote procedure calls, meaning what it will do is to simulate the effect of a procedure, but that procedure will cross the boundaries from your application on your browser to the remote site, where it will look like a procedure there on the actual cloud, and then you will get return values coming back to your browser, just as if you called a procedure locally. And that's implemented with SOAP. There's going to be support for applications beneath that. So that support needs metadata about what you're doing, and that metadata is provided in different data representations like JSON and so on. And so there's another middleware layer that's responsible for that. And then the operating system will be actually running the servers and interacting. The middleware will be communicating with those servers, and so it will all fit together. So let's first look at SOAP as an example. We understand HTTP. What HTTP does is to put and get data to and from a server. You put a request, you get back the web page, and that's a GET. And that gets then displayed. Well, let's suppose you want to do something more sophisticated than that. Let's suppose that what you want to do is to make a request to create a OpenStack server, say. How would you do it? Well, the mechanism that's used is to transmit an HTTP request with a put to the OpenStack interface, and it will be coded in XML with all sorts of special metadata in it. And what you're going to get back is a handle, in the form of a XML document, if you like, that would describe the instance that the OpenStack has created for you. So that sort of return and reply, what it's done is to change the state of the cloud in in response to a request from you. And so it really acts like a procedure call in a sense. And there's lots and lots of different circumstances where you can actually make those type of procedures out of the web requests. But SOAP is a protocol that allows you to do it simply. It's well defined so that you can read those SOAP requests and see what's going on. And there are tools actually to build SOAP systems. It really underlies the web service description language, WSDL, that you can find on the World Wide Web or in other places. It describes a sort of protocol for establishing more complex relationships other than just a plain web service. So that type of description, that SOAP, is an example of providing procedure calls, as we said. In general, procedure calls can be to objects, meaning it's not just a procedure call, there's a special argument in the procedure that denotes a specific entity on the cloud service that you want to talk to. So in this way, you can talk about lots of different objects within the cloud by using that object parameter in your request. So you have procedure calls, you can have a special parameter, which is the objects. Typically, if you do that, then the procedure call will be routed to that object to actually invoke the procedure on that object, and you have a sort of remote object call effectively. You also find that there's notions of shared memory which don't really work across a distributed system. So as a consequence, what you do is to have representatives of objects. You have identifiers for the objects, and you pass these backwards and forwards because you don't really have a shared memory environment. You can't just name an address. You have to use some sort of handle, some sort of identifier. And what we're going to find is in things like SOAP and so on, you're going to be using web addresses actually, those strange / path names to actually identify the objects that you want to talk about and which are shared. So the middleware is going to provide all the software to allow this to happen in a distributed application. It's all going to be transparent to you as a client what is occurring. The middleware will provide that level of functionality. We're going to start by backing off, if you like, going to square one. What are objects? What are procedure calls? And let's just see how then that gets mapped into HTTP. So within a process of address space, you typically have an object. It's got a set of data, a set of methods. You probably met it as a C++ object. You probably met it as a chord object. There could be all sorts of ways you might see this. The object reference is usually some sort of identifier which uniquely designates that particular object. And typically in C++, it will be a pointer. Now, nothing like that will work in a distributed system. And so we need to find substitutes. We need to find distributed substitutes for these in our middleware. And at the interface, what you're going to be doing is passing requests, which will be basically calls to different procedures. And one way of talking about that is you'll have a set of methods on an object. Each of those methods will be a procedure. There will be a unique object in the procedure parameters that's the object method, or designates the object to which the method's being applied. You're going to want to describe what that formal mechanism is, and that will be a signature. These requests will return arguments, and so you will have this two-way protocol. So put object name, get object name. Those are the types of things that you will have for talking to objects. you will provide, or the middleware will provide mechanisms to go across address spaces, as we said. So you're talking in your application space, you want to talk to the servers, you're going to want to cross those address spaces. You use something called a remote method invocation, meaning that you'll look as if your application is calling a procedure, and what it turns into is a set of HTTP requests to the server at the back end. The server will take those requests and map them back into a procedure call on the right object, get the return values, return them again with the web, and they will again get mapped back on your machine into the results. So remote objects will be objects that can receive remote invocations following a procedure call, looking like a procedure call. Remote object reference will be some sort of string, perhaps a URL, that refers to a remote object, can be used instead of a pointer or an address. And a remote interface, well, that's going to be how you call these, how you actually invoke the procedure mechanisms, and typically it's going to look like some sort of web server in our implementations we're going to describe. All right, we talked about doing remote procedure calls, and now let's focus in on just how do you get semantics out of the remote procedure calls. If you remember, what we're doing is to send HTTP requests backwards and forwards between the application and the server. We're going to follow a protocol called SOAP, and what we're going to try and do is to fill in the background information so that the SOAP will seem natural to you. So all method calls, remote procedure calls across a network, because they can't operate on a common address space, because you're having to implement, if you like, a distributed system to do the method calls, what they're going to look like is something like this diagram. You have a request, and it's going to turn into a message that's sent over the network, and you're going to have a reply, which is sent into a message that comes back to you. And we're going to contrive to do that through HTTP using something like SOAP, the SOAP protocol. So your client will have some sequential code. It will say, do the operation, that particular piece of code will make a request message. It'll get sent over to a server. The server will get the request. It will find out what object is in the parameter list, and it will then execute the method associated with that object and use whatever other remaining parameters to fill in to call that method. Then when the object completes, it's going to send a reply. The reply is going to get transferred back through a GET on the HTTP, and your client will receive that and continue with all that information, doing whatever it next needs to do. So in general, a remote object itself will have several different method calls on it. It will look something like this. You'll have M1, M2, M3 saying being methods or procedures with parameters in there on the particular object, which is why we're calling them methods. There will be a remote object that's designated by the object handle in the parameters, and that remote object will have some internal data, has some state. The methods will call implementation methods, and then they're going to return values. So that interface is what's going to be provided by the coupling of your web server with whatever mechanism it has, middleware it has for executing the remote execution of those objects. So this is how you can talk to OpenStack and you can actually create instances. It's going to be through these type of remote objects. So you can have local method calls, you can have remote method calls. Local method calls would be to take all of this remote mechanism and simplify it and make one process on a machine talk to another process on the machine using the same mechanism. It's going to, that will sort of cut out all the layers, but of course it wouldn't serve our purpose of being allowed to create crowds and have very sophisticated operations. When you do a local method call on a single machine, the machines around, it's going to continue computing, it's going to follow through everything. You get exactly one answer for doing the computation. So we call that exactly once semantics. You call the method, it does it, you get the reply. When you do it remotely, though, there's all sorts of possibilities happen. You're not actually seeing what's happening to the remote site. You're not seeing what's happening to the network connection. The network connection could fail, the remote site could fail, and what happens to your procedure calls. So remote invocations are somewhat difficult in the sense that you can have failures and that can cause different types of semantics. You might call a remote method, it fails, and in frustration you do it again. Well, did it really fail? Or was it just slow in responding? Will you get two answers, or will you just get one answer? So there's some questions about semantics that arise because of the distributed systems nature of this type of cloud and this type of implementation. So what sort of failures can cause you interesting results? Let's take some simple examples, if you like, case study. One is that the correct function is called, it executes, it replies. Okay, so that's the nice easy one. Another one would be that you make a request and the system, the remote system crashes before it can reply. Another is that it crashed before it actually executed anything. So nothing got changed on the remote server. You would have to do it all over again. It might be that the network loses the request, so that a request never got there. That's a totally different case. It might be that the communication channels fails as it's trying to do the reply. Maybe you've got one of the routers in the network die or something similar. So there's a variety of different cases here. The last one, the client machine fails. It sent out a reply, but before receiving the reply, sent out the request, but before receiving the reply, it crashes. Then what happens? Do you have a state change in the server and the client is having to be rebooted and it won't remember that it sent the request? So all these different failure modes could occur, and you need some semantics to go with that in order to make it work. And so we have a sort of notion of invocation semantics. The middleware tries to make it as transparent as possible, tries to make it look like it's all happening on your machine, but sometimes it won't be able to do that. So although it tries to do exactly once semantics as much as possible, you can have other semantics. You can have at least once, so you're going to keep trying. You can have at most once, so if you try multiple times, only one operation is really going to occur remotely. What you would like to have happen on the remote site depends specifically on what you're trying to implement. And you can imagine that in the OpenStack scenario, if you're trying to bring up a machine, you bring up a server, you request a new server, well, if you do that and say the communication gets lost on the reply, you do it again, you don't want to have two servers, you would like to just have one server that was created. So you can see that that sort of semantics plays a role in what we're describing. So this is just a sort of summary of how invocation semantics works. You can retransmit request messages. You can filter out duplicates. You can re-execute procedures if they don't have any effect, if they're just getting status information. You can retransmit replies. What you're trying to do is to keep exactly once type of semantics, because that's a preferable way of handling the whole system. But there's various ways you can do that without really sort of affecting that sort of semantics by duplicating messages and so on. But you have to be very, very careful about doing it. We're not going to go into a great deal of detail about that, but each of these different sort of semantics has a definition, has a maybe it worked, maybe it didn't, or at least once. If you keep trying, at least once it's going to work, or at most once. Even if you do it lots of times, it'll do it at least once. It will do it at most once, rather, and have that effect. So there's different semantics that you can give with the middleware. Okay, now we're going to look at how remote procedure calls actually are implemented. We'll step through it. It's the same for RMI, same for SOAP. This will give you an idea of what mechanisms are required, and then we'll talk about particular ways that they're done in the web. So looking at the communication, remember we have a client that's trying to talk to a process. We're trying to implement a procedure effectively with the remote method invocation, and we have to actually convert it into a bunch of messages and an implementation on a server side. So split up the computation into two pieces, that which occurs on the client and that which occurs on the server, and there's going to be reply requests between the two. The client is generally known as a proxy. It's going to make the requests. There is a skeleton and a dispatcher on the server side that responds to the requests, executes the method, procedure, whatever, and returns the values back, having done the computation. And this can change the state of the server as well as providing different types of return values. So in this diagram, you will see that there's different objects that can be around in the client, and they can talk to different objects in the server. We're just going to look at one of those. So if we make a request, then what's going to occur? And in the first, we'll pick a object A. It's going to make a request through its proxy, and it's going to, that proxy will bundle up the parameters into a message, send that across the request to the server. At the server, there's a skeleton and dispatcher that receives the request. What it will do is to unbundle parameters, and then it will find the method that needs to be executed. It'll have to look at perhaps the object to determine which method it is, and then it's going to make that request, execute the remote object, get the return parameters. All of the operations together need to work in order for the procedure to act correctly. And as we mentioned in the previous set of slides, if something goes wrong, we can have a different semantics than a normal procedure call. And that's why we have those exactly once or at least once types of semantics. The proxy, it's responsible for making RMI transparent to the clients. It's the interface. It's like an API. It really separates out what the computation is on the client side from all the mechanism that's needed. The proxy is going to forward that request. That request will be formatted. It'll have a particular way of putting it into a message so that it can be easily decoded. That process of putting it into a message is called marshalling, and we'll cover that in a second. When it gets to the other side, it will have to be unmarshaled, and the actual method invoked. Marshalling is done mainly through compiling, a special marshalling compiler. It can be done by hand if necessary. It takes the parameter and transforms it into an external data representation, which is generally agreed everywhere as a sort of standard, and then it will package that and transmit it using TCP/IP across the network. The marshalling, as I said, was the action of taking those data values, converting them into the external data representation. Usually that external data representation contains all the information you need in order to be able to decode what are the parameters. So it will not only give, say, an integer, but it will say it's of type integer in the actual message. The unmarshalling, again, is done by a very, very simple script that takes the contents of the message, and using the information in the message, it is allowed to actually rebuild the parameter space again and the method invocation that's needed to go ahead. The remote reference module, when you're talking about remote methods, typically there'll be an object, and that object will be at the end of a URI. That's like a fancy URL. That method will be in a table associated with the object, and what happens in the message is to say, well, we want method 5 performed on that particular object. So it finds the object through the URL, and then it will index down to 5, find that particular method, unmarshal, and make the invocation. And when it's finished, then pretty much the reverse happens. You take the results of executing the method and you bundle them up into a message using the same sort of protocol and the same way of encoding the data, and you transmit it back. What happens when requests occur? Well, you have to make sure that all of the communication occurs, that you wait for a reply, that the reply, if it doesn't occur, causes some sort of semantics in the client to actually take account of the fact that something broke. On the other side, on the server side, you're going to receive the message, you're going to decode it, but you also have to take care of the fact that when you send the message back to the client, it may not actually get back to the client, and so there might be exceptions and other things. All of that is usually done by middleware because it's the same for every single object call, every single method call, and so we get a great deal of simplicity because everything is operating the same way. So in summary, remote method call, what we're doing is provided a procedure call between machines, between pieces of code on different machines. We have a stylized approach to do that. We have a client process. We have objects in that client process that want to talk to other remote objects, object B here. And what's going to happen is that it would talk to a proxy object instead on the local client. That bundles everything up, goes through a communication module, communicates to a remote service, and the communication module on the remote service unbundles it and then calls a dispatcher. The parameters are taken care of by a skeleton, and there's invocations on the object. Now you're going to see different instances of this as we talk. You're going to see this happen in Java. You're also going to see this happen just plain with HTTP using SOAP. But it's the same style of approach. Some of it's automated, some of it's done by hand, but it's doing exactly this type of operation. And in each case, when you get errors, you have to handle the errors, and it's exactly the same sort of approach to handling those errors, but it may be coded as a SOAP or it may be coded as a Java. Well, we're going to talk about using the web to do remote procedure calls. And I wanted to remind you about the Hypertext Transfer Protocol, HTTP, because that's going to be the vehicle with which we do this. It allows you to interlink text documents, very popular in the World Wide Web. I want to focus on two operations, get and post. They're going to be kind of critical to the way that the whole invocation mechanism works, and then we'll be talking about put later on. So if you have a browser, it's going to get information from the web server, and what it'll be doing is to get that information. It'll package up the request as HTML, forward it across to the web server in a message, TCP/IP. It will get a reply back, which will be the document that has been requested. SOAP is a simple object access protocol. It's essentially like a remote procedure call, but it's encoded as HTTP. It's transmitted by HTTP. It's coded in XML and can be decoded by any machine that really understands XML, which is pretty much every piece of software. The return value is again another XML document. And this very, very simple protocol underlines all the web service description language, WSDL. It's very simple. The middleware is based on web services. If you're going to provide any semantics to SOAP, it has to be done in terms of using other languages, Java or whatever, in order to provide the semantics you intend. Otherwise, what you're going to get is just the bare minimum, the HTML request and the response. Because coding things in SOAP is okay, it works, but it sometimes leads into complicated solutions. What people have done instead is to come up with an invention called REST, which is a representational state transfer type of scheme. It's a style of software architecture for distributed hypermedia systems such as the World Wide Web, and it was introduced to the world by Roy Fielding. He wrote HTTP specifications, and out of that he designed this REST protocol. And there's a collection now of network architecture principles which outline how you would use this type of approach to actually do communications, and they're defined and addressed and can be looked up on the web fairly straightforwardly. But let's look at REST and see what it's doing for us. So it wants to capture all of the characteristics of the way one encodes HTTP for the web, which made the web successful. And what it's trying to do is to go beyond the GET, and it's trying to provide state update and communication as you were getting a procedure call in a simple manner, and one which is easily programmable. So first of all of the items that will be addressed, all of the addresses, whether it's an object, a method, or whatever, we're going to use URLs for in the form of a URI, which is basically it can be, well, it's a string with whatever you like at the end that represents the object or the method that you're invoking. I'm going to use the HTTP protocol to carry all that data across. We're going to make a request, we're going to receive a response. Typically, what will then go on is to actually display the response on a browser. But that sort of sequence is the typical operations of REST. It uses HTTP protocol beyond POST and GET. It will actually use delete and some other types of operations occasionally. So REST isn't a standard as such. It's a way of doing things, best practices you might say. It uses several standards, obviously HTTP, obviously URLs. It codes the transmission of data and so on in XML and HTML and GIF and JPEG using sort of typical web methods, and it has typical sort of web data types. Its main concepts are that there are resources in the system, which will be nouns. So if you want to make a request about an employee, you would give the employee some sort of ID, in this case 12345, and then you would make a request about 12345 to the server. The request would be in the form of a verb, fetch his current salary or increase his salary or whatever. So there will be verbs that apply to the nouns. There's going to be some representations that you use to transmit the data, and typically it's XML. It will be constrained to the web languages. The resources, well, they could be anything you like. It's just a mapping of concept to a set of entities. You can name anything you like. So you could say, well, today's weather in Los Angeles. You could refer to, well, there's weather, there's Los Angeles. And if you want it to be today, you might even have a reference to today as an object. It's represented with a global identifier, and that global identifier is described as a string in HTTP. The only difference really between URIs and URLs is that URIs tend to be a single entity, a unique entity. So if you sort of want to talk about an aircraft, it might be that 747 over there. REST uses these to identify all sorts of resources, and there's some examples here. You could use it for books, you could use it for classes. It really doesn't matter what the noun is that you're identifying. As you can see, you can make up your own conventions about how to name it, but it should conform to looking like a URL and have that unique property that there is only one of those on the remote system. The verbs, they're the actions to be performed on the resources, and typically they can be simplified to just the straightforward HTTP requests: get, post, put, and delete. And so we'll be working with those with REST. The get is the method for asking for information. What happens is you would get a book. So get, and then you provide the URI, which in this description is an HTTP localhost/books. So it would identify, in this case, all of the books, or it ought to, all of the books, whatever that URL means, as what you are trying to retrieve. You could also say a specific book with an ISBN number. You could also say, well, I'll get all the authors. The post creates a resource. The put updates a resource. So post would be to put a book in local host's books. You could have a list of books, and you're going to transmit them over to post them in a remote machine. Putting a single book with the contents ISBN updates the book identified by ISBN 111. So you can use either of those to actually update a remote. Delete removes the resource identified by the URI. So if you want to delete a book, well, you would issue a delete and then the string. The data is represented or returned to the client for presentation. There's two main formats for that. You can return JavaScript, as in JSON. That's a specific way of representing JavaScript across messages. Alternatively, you could use XML because that's a kind of universal way of providing a reply. The JSON is very easy to accommodate with JavaScript. The XML, well, if you want to have Java or other sort of resource processing to provide the representation on your screen, then you might choose XML. So in XML, let's say you're asking for a course, then it would look like a bracketed pair, course slash course, and within that course there might be details about the course, like the course number and the name of the course. And those would have tags. Now what you see is actually everything in pairs, and the last element of the pair is a slash. The first element of the pair names the abstraction, if you like. They're all put between angle brackets to distinguish them from other things in the communication. JSON, on the other hand, looks like a record. It uses parentheses, and again it would be nested because we've got a course and then the details of the course, and you can see it looks something like a C record, except it's a strange syntax. It uses curly braces, and then it has sub-curly braces for individual elements within that. So they're both, in general, hierarchical formats. They both clearly label things in ASCII text. They can be understood by machines, and they're easily processable. So the general notion, then, of the REST architecture is you do gets and posts, deletes, and puts. You would do that to the web proxy server, to the server backend, which will process it. The server will, in turn, recognizing that it's a REST request, it will process it with the REST engine and do all of the updates according to your style of REST processing. Now, this can be very simple, it can be very complicated, but typically REST emphasizes making this as simple as possible and making the transactions backwards and forwards between the client and server as simple as possible so that it can be easily understood, easily debugged, and easily maintained. So some real-life examples. If you look at Google Maps, if you look at Google Ajax Search API, if you look at Yahoo Search API, if you look at Amazon Web Services, they're all using a REST architecture. They're all following that same sort of simple discipline about how to communicate. And as we go forward, when you're talking to, for example, Amazon, if you choose to use Amazon in your experiments, you will actually be using all of this protocol to accomplish communicating with the cloud. So it's worth mentioning, how does JSON differ from XML? What is JSON? Why is it so popular these days? JSON works with JavaScript. It's very efficient to use with JavaScript and is very familiar, if you like. If you already know JavaScript, then JSON is very, very simple to actually use. So we're looking at a lightweight data interchange format across the web. We're looking for one that's easy for humans to read, because then it's easy to program and it's easy to debug. It turns out that if it's easy for humans to read, it's also easy for machines to parse and generate, and there's a JSON.org that's dedicated to that cause. It really is just a subset of JavaScript. And if you know JavaScript, then JSON is just one of the structures that you program with within JavaScript. But now it's actually used to record what the documents are that you're passing in a message across the web. So what does it look like? Well, we mentioned that it had braces, and this expands what we described. It shows you that, in fact, those braces can designate various fields. Those fields can include different types of structures. Here we've got a first name, a last name, an address, and associated with first name we have instances of that name, i.e. John. Associated with last name we have Smith. Associated with address, well, we can go into a hierarchy. We can have another record and repeat the same structures. So you see street address, you see city, state, postal code, and then we can have instances of street address, 21 2nd Street, city, New York. So this is a generalizable format in a hierarchical manner to pretty much any data. And it tells you not only what the data is, the value of the data, like John Smith, but it tells you what is John. Well, it's his first name. It gives you some semantics to deal with the data structure. So these are basically name-value pairs. You have a name for the for John, and the value for John is obviously John, the letters, the person. And so in each of these different instances, that occurs again. If you're talking about address, there you have a complicated data structure associated with address. It's a hierarchical one. Those are called child properties, and basically they consist of a number of name-value pairs again. If you have a number, you can insert it, so postal code and the number in there. That number is a valid way. You don't need to put it in quotes because it will be actually encoded as a straightforward number from 0 to 10 up to however many digits. If you need more sophisticated data types, you can put them in between quotes and have strings. And there's some examples of phone numbers, 2 string arrays associated with phone numbers, and you can have any arbitrary number of those telephone numbers, and they're just a list associated with the name phone number. So why is this good? Well, JSON uses a sort of railway diagram type of scenario for coding and decoding its data structures, and pretty much you can use that directly for doing this messaging. So if you are thinking about how to analyze, to take the request you want, put it into a message, or to take a message and transcribe it back, then these railway diagrams allow you to follow a very, very simple algorithm to turn the data into a message or the message into the data. It starts off, well, you can see here, a very simple one for you have a string for the name and a value. What will happen is this will get decoded into a bigger railroad diagram describing, well, what's a string? Well, it starts with a quotation mark, and then you can put all sorts of things in the string, and then at the end there'll be another quotation mark, and that takes you off the railway diagram. So this is sort of like a shunting yard, if you like, for characters, but it's very simple. It's just a straightforward type of state machine type description. The key thing is that JavaScript will allow you to do this trivially, and so it makes use of JSON very simple. Now, some of the other data structures, the values get encoded into different types of railway diagrams. Different other data structures will get coded similarly. This one gets here coded into something that will recognize numbers. So you can sort of go down this list, and you can notice actually it's a sort of recursive descent algorithm that's being employed to actually decode these strings and transfer the data. And that's really one of the nice things about this is really a state machine based system where the transitions will take you to different diagrams, allow you to decode the diagrams, and then let you rebuild the values that you've got from it. So here we've got an array, and the array will consist of multiple values, and when you see the closing parenthesis, you know you're finished with the array. So those data structures are very simple. If you sit down and you want to compare that with XML, it's a great exercise. What you'll see is XML is very difficult to keep track of. It's still organized as a hierarchy. It's still machine and user readable. They both employ hierarchical data structures. JSON doesn't have a validation system because JavaScript essentially does that. XML, on the other hand, does have XSD that validates the data structure. It says it's okay. The namespaces, there are no namespaces, it's just what you write. The XML does have namespaces in case you should need them. Parsing, well, essentially there's just JavaScript. You can evaluate JavaScript data structure with an eval, just bring the thing in and it decodes it into JavaScript. It's fast. There are security issues with that, but it's very easy to write. Parsing, on the other hand, for XML, you need some sort of description of how to parse it. You need a parser. You need to understand how to organize things. There's a processor called XPath to do that, which is totally separate. So as you can see, there's more overhead with XML. In JavaScript, you can work with objects, runtime evaluation of types. It's all very simple. If you use JavaScript for XML, you can work with strings, but you might require additional parsing mechanisms to actually parse the XML and convert it into things you can use in the JavaScript. Security, both JSON and XML have their problems with security because in JSON it decodes it fairly automatically. You could get any sort of thing in a descriptor, and JSON would decode it, and if you can break in or cause some action that's detrimental, that is very easy to do. There are libraries to make that more resilient, but the basic mechanism is not very secure. The XML, the security is text parsing. It's not code execution, so there's a parser that would operate. So you have a little bit of distance between text parsing and the actual code that you're going to use in the server, but nevertheless, you could generally put anything in XML and the text parsing will break it apart. If it's correct XML, you would still need some sort of security at the processing level of the actual information you get out of the XML document. So in this set of slides, what we're going to be talking about is how lots of clients can talk to lots of services and scale the services according to how many clients we've got. We're going to use a load balancer to do that. So a request enters a router. It's forwarded around until it gets to the cloud. The cloud router is going to transmit the request to an appropriate server. The load balancer is the mechanism in the cloud that actually determines which service, which node in the cloud, which server is actually going to be used to provide the web service. So maybe we've got 10,000 nodes in the cloud and we make a web request. It will go to one of those 10,000 farmed out by the load balancer. There are all sorts of interesting questions about how load balancers operate, and we'll try and give you a quick overview of how that works. But in your MP, you'll actually be designing a simple one just to experiment with the whole idea. So we've got a request coming from the cloud, enters the router, and the load balancing server is going to determine which web server should process the request. Now, when you're sending it from the internet, it's going to go to a particular IP address. The router is going to take that IP address, deliver it to the load balancer. The load balancer will change the IP request. It will change the actual IP address to the particular IP, to the particular server in the cloud that's responsible for responding to you. Now, if you know from our discussions before, we're using a simple sort of REST protocol in interacting with the cloud, and that protocol implies very, very simple relationship between the request and what's serviced. As we are doing this, what we're going to do is to make sure that any particular server we choose has all the information that it needs to be able to respond to that particular REST request. So if I ask for a particular employee and their data, then what I would expect to happen is that the load balancer would send it to one of the servers that has that information. And there's presumably a large number, so it can load balance over all those servers so that you get good response time and you get a fair, quick reply to your web service. In this diagram, you will see that flow of how this operates. In particular, what you notice is that for every request, there has to be a reply, a response, which is going to go back to the client, which will reveal to the client the data that was fetched, and the client probably will display that on their screen. So there are dotted lines back through this mechanism. The load balancer has to keep account of those dotted lines. If it gets a request, it's going to find a server, but then that server has to be able to reply back to the correct client. So it's going to keep, if you like, a trail of how to return the packets from that request and funnel the particular request from the particular server back to the right client. So Google, for example, provides web search for the whole of the earth. Lots and lots of people do web searches. How is that organized? Well, the request, the web search request, goes in as an HTTP request. It will go forwarded to a Google web server, and it doesn't really matter where you are on the planet, you're going to say Google. But it will get served by a particular Google cloud, part of the cloud. In that cloud, there will be a unique web address for data requests. Now, that is going to talk in turn to all sorts of load balancers to actually answer that request. One of the things that it would do, just to indicate some of the additional add-ons to the load balancer, is it would determine out of all of the different data sources it has, it will determine which of those data sources is the most interesting from the point of view of your search question. So it will take your search query and it will look in various index servers for a response from that request. And the front end will actually sort of forward the packets, your requests, to those document servers corresponding to the correct indices of the query that you've made. So you're coming through, make a web request, it's going to take your query, it's going to index it, it's going to find from the index servers which document servers are the interesting ones. in all of those circumstances, you could have multiple index servers, you could have multiple document servers. And the load balancer is going to split up those packets to each of the appropriate index servers it's found, and to each of the document servers. It's going to choose one of those in order to reply to you, and it's going to keep track of all of that complexity. So we're going to stick to a very, very simple example, but this slide demonstrates as you're making requests, you can get into really sort of complex implementations within the cloud. Your load balancer is an integral part of providing this service, but there may be other parts to that service that the cloud will have to worry about. For example, if you're looking for something Google-wide and the whole universe, the whole world-wide, there may be so many different things that you have to find the right set of web servers to actually respond to your request. But it's all the same mechanism, and what we've described is really sort of fundamental to doing any of these types of requests. And here's just the sort of diagram processing elements. You're going to be talking to the front end here with your web request. It's going to do the processing and actually sort of figure out where it needs to find the index and find the documents. And down here you've got lots of worker processes that are going to be doing all of the processing. And your load balancing is going to make this all sort of seamless and very fast. So here's a, if you like, sort of diagram, block diagram of what's happened. You've got a query coming in. There's the Google Web Server. It may do various things like check your spelling. It may give you an ad. It may provide an update with news and books and so on. That would all be processed in the Google Web Server responding to your query. Then the query itself is going to go out to index servers, and some of these will be replicated, and these index servers will find the right item that you're looking for, but that item will be a document, but it won't reside on the index servers, it will reside on the document servers over here. So it's actually then going to respond to the web server. The web server is going to have to go back and find the document server. It will get the document, return the document to here. Then what's going to happen is it's going to integrate all of these advertising miscellaneous services and return a web page to you with all of this information on there. Where is the load balancers? The load balancers making sure that if you've got, say, the Olympics, or you have a really important news event, when there's queries for it, there are enough index servers, there's enough document servers, and the loads are spread over those index servers and the document servers to actually be able to process all of that, all of those flood of requests. So we have this idea of providing web service, but it can be a huge amount of information. That information is distributed over lots and lots of different nodes in the cloud. How do we do that? And this is just a sort of high-level view of how we're doing that, and we'll get to details later on. But if you have a lot of servers and you have a lot of data, enormous amount of data, there are ways, obviously, to devise serving this data. The data itself can be split up, so we could take this red one, and sort of pop it over onto a particular server, but then we don't have any replication, and so we can't do load balancing. So we might take one of these and put it on several different servers. That way there's two servers that can actually service the same request. Now in general, what we would like to do is to take all this data and map it. We can either split it up so that each element here goes onto a different server, or we can do this type of duplication so we can do load balancing. And so if one of the server farms dies, say, we have a spare copy. So a picture of what we're talking about here is we need replication. What we can do is to decide how much replication there is. In this case, we've sort of got six sets of replication. We can talk about where we're going to put that onto the web servers, and we can partition the data. So we can sort of say, well, okay, there's going to be 2 yellows over here on this set of machines. There's 2 blues over in this machines. There's a yellow and a white over this machines. We can have a very flexible way of allocating the data to the servers. And so in the load balancer itself, we need to accommodate all of that information, how things have been replicated, how they've been partitioned across the network internally in the cloud, so it's invisible to the cloud user, and it gives you the flexibility, first of all, of being able to respond to lots more users of the cloud, clients, and it also responds to crashes of systems within the cloud and updates. Perhaps this is being updated and so it's busy. Is there a spare copy of blue you could use somewhere else? So this can get very complicated. The load balancing approaches generally are the mechanism to overcome this difficulty. There are various different load balancers. We won't be talking about all of them this time, but just to give you awareness, there are load balancers that deal with content and locality. An example that would use DNS service to actually decide how to find the content. So the DNS service is relating machines to names, and what you would do is to associate the content and locality with the name of the server, and then use your DNS service to do it. Another way of approaching all of this is your load balancer might be size aware. It could be centralized, and what it does is to distribute over all the different nodes that have got all of the data, and the data might be split up between multiple nodes, so that the load balancer has to be aware of where that data is. Then a centralized type of operation might be very practical in doing this. Another type of load balancer is workload aware, where you have a lot of servers, but they're all serving different things, and you have a different response to the clients to trying to get the information off those servers. So if, let's say, all the clients want to see the 5:15 race at a horse track, then what you need to do is have the workload aware sort of type of system and duplicate the results of that race on multiple different servers, and having a distributed dispatcher that will actually go and spread the load over all of those different servers. So what we've seen is to process events efficiently, we need to do sort of optimizations with the load balancing. We're going to send and process requests to a web server that's files in the cache. We're going to make requests to that web server with the least amount of requests because we can get a really fast response. And then we're going to send and process those requests to a web server determined by the size of the requests. So those are the types of things that we're going to be doing with the load balancers. Okay, this video ties into your homework assignment. It's about load balancing. It builds on the first load balancing video, and what I'm going to explain is all the different ways that load balancers can be organized. We're not going to get you to do them all for the homework, but this will give you an appreciation of just how complicated those load balancers can become. So what you need to do is to get your HTTP request to the server, from the user to the server, to get the needed resources to actually provide the data from the HTTP. And what you're going to do is get that data and send it back to the client. And remember, you're going to go from multiple clients to multiple servers. And what we want to do is load balancing over all those servers. So when the load balancer receives the packet, and it's going to receive the packet the way we set up all the IP addresses, what it needs to do is to know that there is a server available, and it mustn't break the user's impression that they're working with the session. If you're clicking through a set of HTTP, web slides, web presence, whatever, you don't really want to have the knowledge that you're actually talking to a backend to interfere with the user's view of what's going on. Okay, so the user must always get to the same resource. The SLB must always ensure that that happens. And in order for that to work well, the SLB must know all the servers, know the IP ports, know the availability, understand the details of some protocols, FTP, SIP, and so on. And it may need to play with the network addresses, and so there may be a NAT, a network address translation, associated with it, which would take the incoming address on the packets and translate it into an address that is known inside the cloud, pass that through to the routers, get to the server. On the way back, it would need to fix that so that the packet actually looks as if it comes from the server the client requested, and so the NAT will also perhaps modify the packet coming back to make sure that it actually looks it's coming off the web server. So why do you load balance? Well, it's scaling. It's so that I can have a web service, say 20 servers serving 10,000 people, and then I can go to 20,000 people and double the number of web servers. It's ease of administration, maintenance. I don't have to know where everything is. I can lay it out on my cloud, and when I get it right, then I can turn everything on, and it's all managed for me. It's transparent. It removes the notion of physical servers from what's there. If I need to repair something, if I need to do maintenance, if some piece of the system fails, I can still provide my web service. And it gives you resource sharing. We can run multiple instances of a client service on a server, can be running on a different port for each instance, can load balance to different ports, whatever you want, whatever would fancy, and make your job easier as a cloud manager. There's a lot of load balancing algorithms. The ones that we need to deal with, most predominant, first will be the least connections. When I get a connection coming from a client, I find the server that has the least connections going to it, and I just send that request on to that particular server. You can modify that if you want to include the weight of the service. Some HTTP servers, like a search, may have more effort involved. In that case, what I can use is a weighted least connections, and I can send it to a server that has the least load, and I can adjust the weights so that that reflects how much load is required or is imposed on the server. I can do round robin if I want to do sort of just distribute it fairly. I can do weighted round robin, which also adds a weight. But they're very, very simple algorithms. They need to be because this is very, very fast at that front end. It's very transparent. So main goal is that you try and predict how best to take all those client requests and distribute them to the servers so the server can give really good responses. So how do SLB devices make decisions? There's several factors. One is it can obtain information from the packet headers, the IP addresses, the port numbers. It can also look beyond that. It can look at the HTTP cookies. It can look at the HTTP URL that's being requested. It can also look at the client certificate, the SSL certificate, and use that. Decisions are strictly based on flow counts. They can be based on what the application is, like search. It may take a little bit longer. The decisions can be based on essentially any parameter you want. For some protocols like FTP, as you're sending the data across, and of course FTP supports HTTP, it's the main protocol you would use, you would want to know how that FTP is set up and so on, so that the connections always connect to the right place. FTP has this association. Once you build it between the client and the server, the next HTTP request going down the FTP would also sort of go to that same server, so you need to sort of keep those in line. So if you're downloading a large file, say from a server, then what you need to do is have the load balancer keep track of that FTP request and make sure it always looks like a continuous stream. Otherwise, your TCP IP will get all upset. When a new flow arrives, you determine if the server exists, or the load balancer does. Determine the level of service required. Is this really fast? Is this an FTP? Is this, do I want to multiplex multiple FTPs and so I can get an average or do some other type of algorithm? You pick a real server and then you do all the things that are needed to actually get the communication across. The packet can be bridged, if you want, using layer 2, or it can be at layer 3 and layer 4, and even layer 5. And we'll describe those in a sec. There's various different architectures. Traditional SLB device sits between the clients and the servers, being load balanced. However, as you scale up, you may need a distributed SLB. And what it does is to sit off the side, and it has forwarding mechanisms to actually do the load balancer. And the SLB just provides those forwarding mechanisms the information they need to route traffic. And we'll show you that in a second. So this is the traditional view. You've got a NAT, incoming client, goes to the cloud, the SLB will do the NAT translation and send the request off to one of the servers. And what you notice is it could be two-way. The acknowledgements coming back from the server will go back to the SLB, will go back from the client. Now you would say, oh, that means the SLB is doing a lot of work, and of course it is. So another obvious optimization is just to send it straight back from the server to the client. But if you do that, then you need that NAT box in the way. You need to make sure that the addresses aren't messed up by doing that shortcut. Next, as we move on, you can do this at layer 3 and 4, and that gives you some more semantics. Now you can look at the destination IP address, the port. You can make load balancing decisions on some of the content of the packet. So you need to do all that before you actually send the packet onwards. So here's an example of that. The client sends his packet. The SLB now sort of does its decision for the server. It picks the server, and there's a request coming in, processed, sends it back to the client, and the rest of the flow continues through HTTP GET and server responses channeled through the SLB, and everything's nice. One of the issues, though, with all of this is just what role does the SLB device play in all of the communications. Sometimes it can just be transparent. It can just forward the packets forward. With 3 and 4, it may need to look at the packets, look at seeing what's the internals of the packet going backwards and forwards, as we saw with the previous slide. In layer 5, it has to terminate the TCP flow. Now we're dealing with high levels of protocol. It has to terminate the TCP flow for the amount of time before the SLB decision can be made, and then it's going to send that TCP connection onwards. And so there is sort of a handshake going on, and that's illustrated here. The client makes this request, the SLB thinks about it. It's says, okay, let's go ahead and do this. And then there's an acknowledgement going and some communication, and we do a GET, and that's synced to the server. The server then will reply, and that gets acknowledged. You have a further acknowledgement, and back comes the data from the GET, and everything's happy. But you've got multiple steps in this handshaking business. What you see is the SLB is really acting as an intermediary. The client actually makes the connection to the TCP connection to the SLB. The SLB then says, okay, that's right, I've got it, I've opened the port, everything's happy. And then the client makes its GET, and the SLB handles that GET. It goes off, finds the server it needed. It will then pass that request onto the server. So it's a sort of two-phase to get your packet across to start the flow. And in things like file transfer, that's what you're going to do, because you're going to negotiate bandwidths and other things. You want to know a lot more about what's going on. This allows you to do it. So, lots of work for the SLB. How do you make that fast? Well, you can build a distributed architecture. Here's a picture of the distributed architecture. You've got the packets coming into the cloud. The cloud will forward them. Instead of sending them to the SLB, it now sends them to a forwarding engine, which is a slave, if you like, of the SLB. So the SLB tells the forwarding engine what to do under all the different circumstances. If the FE doesn't know, it asks the SLB. And so in this way, we can have many more connections being forwarded and responded to in a distributed manner. The SLB is not in the direct line of all that data being transmitted. So here's an example. You set up a request from a client. It does a TCP sync. It then goes to the forwarder. The forwarder talks to the SLB. The SLB recognizes what it needs to do, sends back instructions, and it maps it to a service, server 2. Now what you do is to send that flow to the server 2. The server 2 responds, and now you've got a request going backwards and forwards between the client and server 2, avoiding the SLB, but keeping the FE busy. So you've distributed the load. So what you've seen here is how complicated SLB can be, how load balancing can be a really vital part in distributing the load, and it can cope with distributing the load at different protocol levels. And you can achieve different things, whether it's from sort of file transfer to distributing search requests to distributing cloud requests, as we've seen with RPCs. What's missing from this is just how did that flow get to the server? How did it go from the client to the server in a nice, easy manner? What we've seen is the distribution mechanism. Now we're going to turn our attention to how does the protocol actually work? And we're going to bring all this knowledge about RPCs and load balancers and everything else together into our sort of finale for the lecture one, which is actually transporting that data and what's used to transport that data. So join me in the next video. Okay, we've looked at RPCs, at the web, how we can use the web to support RPCs with things like SOAP. We've looked at formats for data over the net, and we've looked at load balancing. In this last lecture, we put it all together with how do you very effectively make development of web services, and how do you ease, if you like, all of the complexity. And you've already seen there's some complexity creeping in with load balancing. There's a little bit more we can deal with. And as we go forward, the reason for doing this is so that you don't have to, later on in the course, worry about this. What you will have learned in this last section is just how we get the data from the client to the application in a very reliable way. And so from now on, after this, you don't have to worry about all of the complexities of the cloud services that we're going to describe. So let's deal with this straightforwardly. Protocol buffers are an invention by Google. They're based off RPCs. They're very similar to RPCs. What they're doing is, for web requests, they're doing what RPCs requested. And RPCs were implemented initially, sort of Corba and .NET and so on. What's happened is those ideas have been used to implement the same type of support, but this time at the web level with protocol buffers. So it's a language-neutral, platform-neutral scheme. It's extensible. And what it does is to take the client request and it serializes it, transmits it to the server through all of that mechanism we were describing, and delivers it to the server. The server can use the serialized structured data to extract the data and then perform the various tasks. And we described some of the distributed services that can be provided, like an RPC or just a web request or anywhere in between. All of these are taken into account inside this sort of protocol buffer organization and automation. What we're going to see is the protocol buffers actually give you the code for the client and they give you the code for the server. So you just need to know what you want to do, and then the protocol buffer system will actually build for the client the mechanism to do it, and for the server the skeletons to actually accomplish the task. So here's an example schema for sending a request about a person. And this could be embedded in HTTP, it could be an RPC type of request that is being made, but whatever it is, it needs to pass this data structure. And this data structure is, well, it's going to be a person. It looks like a record, if you like. There's going to be an identifier required, and it's an integer, 32-bit. And there's this required name for it, and there's an optional string. And in the Google protocol buffers, they're actually labeled so you can easily access them, 1, 2, 3, 4, and you can see what those various parameters are. And that's the way the client and the server deal with those strings. But the software, the actual encoding for the packet and the decoding at the other end, is all done magically for you via a compiler that takes the protocol buffers and produces those pieces of the code that you want to use. Now, we know that the web is SOAP. It can be JSON. It can have different programming languages, C++, or whatever you choose to name. This particular approach allows you to generate the data serialization for any of those languages. And so it's very powerful, very useful, keeps everything consistent. You can start off in C++ and you can end up in Java or some other language. You don't care. It's all going to be taken care of you by this particular system. This is an example of what it would translate into for Ruby, for example. And I'm just giving you the data definition here. I'm not going to go into what the server and the client look like yet. But here what you see is the translation, if you wanted to implement this in Ruby, what it would actually translate to according to those translators from Google. Okay, now, because this was so successful, it had imitators. Thrift, I won't say it's just straight imitation because it also introduces some innovation. Thrift built on this idea, and it created more of a network stack that could be used for other things. In particular, what it allows you to do is to transmit files between clients and servers so that you can actually access directly distributed file systems. That's a big advantage if you think of, you've got the web and you've got files perhaps with details, FTP or whatever. If you can actually use some sort of file access mechanisms distributed file access mechanisms, then you can simplify everything. And if you can put all that into a package so that you don't have to actually program it, but what you do is to specify to the Thrift compiler what you want done, and it does it, then enormous benefits. So that is exactly what Hortonworks and Yahoo and Apache have put together. You can read all about it, Thrift, apache.org, and go to that web address at the bottom. It will explain, there's a paper which explains the concepts underlying Thrift, but I'm going to tell you about them anyway. So what Thrift does is to deal with servers. It would deal with single-threaded, event-driven servers. That's its speciality. It would deal with processes. You can say, I want an RPC, or you can say, well, I just want a video content. You just get it to the screen. You can specify events, asynchronous events coming in, like sort of notifications of the news. So you've got various different processes you can use. You can use various different protocols if you want it to be sent in JSON, or if you want it to be sent in clear text, or you want it compressed. There are options for all of these. And then for the transport, well, you can use raw Ethernet if you want. You can use TCP, you can use HTTP. In fact, any future protocols would also go there too. So you get flexibility in this generating system, and what it's going to deliver to you is a serialized structured data specifically for your application and for your server, given those specifications. So just to recap, I mentioned Hortonworks and all these other companies, but the idea, this sort of knitting together of everything, we have to actually acknowledge Facebook. So transport methods, as that's a topic that we haven't actually addressed. You want to open, close, read, write, flush a file. The server transport has actually the ability to listen to see if anything's happened to the file, accept and close, and it will allow you to read, write to and from a file on disk, on a remote disk. It will also, of course, let you do HTTP and all those other types of things. But having that richness for transportation really sort of makes you much more productive development-wise in building cloud services. Same thing with file transport. You can transport a file, you can transport it framed, which is for non-blocking servers. Just imagine a video stream, and you don't want to block, you just want to take what you can get out of the video stream and present it. Then you would use a T-frame transport for it. If you were building a complicated distributed memory system, you would use a T-memory transport. It uses memory for I/O. If you were going to do blocking, which is what mostly we do, you would be using a T-socket. If you were going to do compressed transport, then you would use the TZIP library. Server codes. What can we do with servers? Well, you're going to have servers that are non-blocking to match that transport, and you could build multi-threaded servers using the non-blocking I/O of systems. Well, it has a non-blocking server all built into this. You have a simple server. You also have a thread pool server. So you create so many threads. What it's going to do is to select one of those threads to operate for the moment as a pooled device to help you communicate. And then when it's finished, it's going to release it so that the actual creation of a process isn't needed. You just use threads. So lots of different server codes you can have, but they're all encoded as type within this system, and you can pick and choose, and it will generate the code for you. So again, the data structures get translated. This is an example schema for Thrift. Now you notice that I'm talking about what is Thrift's schema. This is the way it would look. It's a bit simpler than the protocol buffers, but it does exactly the same thing. In this case, it's a struct. It's very familiar if you know C++ or something equivalent. Okay, so that's your data structure. Now you're going to build a skeleton for the server and the code for the client. Thrift would do that automatically for you once you choose the different mechanisms for transport and different servers. I'm not going to go into great amount of detail, you can read about it, but essentially what happens is that you would say, well, I want this type of communication. The Thrift compiler would produce a stub for the client. You take the stub, you add your code to that stub. The stub does everything in the way of doing the serialization for the data structure and transmitting it. You also take the skeleton, you put that into your server. The server code then needs some development. It's how you're going to process that data. But all of the threading and all of the communication, all of the marshalling, getting the data into the packets, all that's going to be taken care of you, so it becomes really simple. So that's my quick update on Thrift, but it brings together all of these packages, what you see from client to server through the cloud. For any level of complexity, we have a bunch of tools that really helps in organizing and building these systems.
So what's the idea behind mobile backend as a service? Now let's say you want to develop a mobile app or a web app. What you will end up doing pretty much for any mobile app that you want to develop is you need to get it integrated with some databases. You need to have some backend servers created so that they can receive requests from this mobile app. Databases, you need to have networking support so that, okay, there's load balancing, and we've talked about load balancing before. You need to have load balancing involved. Many times your mobile app needs to have social network integration, Facebook, LinkedIn, whatnot. You need to have that little icon at the bottom. A lot of times, even like the user interface is more or less in the same sort of category. I mean, you would develop an app, you develop another app. They're kind of similar. So a lot of these problems have to be solved again and again and again for one app, another app. So people started to think, why should we reinvent the wheel every time? Yes, a lot of these mobile apps, as I said, they use cloud services for these things, but they still need to use them, right? So the idea is, what would happen if we put all of these different cloud services that you're using in one shop, one place? And that's the idea behind mobile backend as a service. So the general idea is that you need common services and among different apps, whether web apps or mobile apps. And you want to get away from implementing custom apps each time around. The stuff that you want to have in a mobile backend as a service sort of suite of apps or suite of APIs, cloud storage, and in the next week, next module, we will talk about cloud storage in different ways. But a lot of times, a developer wants to be at a higher level, doesn't want to deal with the API, different APIs. They just pick a mobile backend as a service suite, and cloud storage is somehow integrated in that. User management, different users want to log in. Again, that's one common use case for a lot of web apps. For a lot of apps, somebody needs to log in. What happens if the password is incorrect? What happens if they forgot their password? Some server has to authenticate. So a lot of this, instead of you doing that, you just let the framework handle that. Push notifications, apps are in users' mobile devices. They always have it. So a lot of apps want to send some information to the app through push notifications. Again, that's something that you can put into a suite of software SDKs. And as I mentioned, integration with some social networks is also another thing. So what people try to do is provide all of these in a one-shop model so that you don't need to go, for example, do Dropbox for your cloud storage and say Yahoo OpenID for user management, and then do set up another SDK for push notification, and then get some Facebook API. So they want to put everything in one place. There's a good number of these mobile backend as a service that have started to grow. Some of the major ones, and these are by no chance a complete list. It's just some of the things that are getting some traction. Appcelerator, AnyPresence, Appri, Built.io, Feedandry, Kinvi, TrueMobi, and even Apple itself has Apple CloudKit, which a lot of you as users should have been familiar with. Whenever you use iCloud, it's actually using this mobile backend as a service sort of idea, right? And some of you are probably familiar with Apple's version of it as users. Whenever you use iCloud, you need to sign into iCloud, and then the rest of the stuff happens. Apple CloudKit provides that sort of a mobile backend as a service to you. Now, a lot of these frameworks have some commonalities, but then there's difference in other parts. So some of the commonalities is, for example, a lot of them use similar components for databases, like MongoDB. It's an open source database, sort of a big data, cloudy database that we will get to talk about this sort of stuff in the next MOOC, our big data MOOC. And a lot of these mobile backend as a service suites use MongoDB to serve, for example, JSON objects. We talked about REST API. It's very common in these things to use REST API to make a call to another SDK or another service somewhere running on the cloud and get your results back. A lot of these build on the idea of microservices. We will talk about serverless architecture later on, but the idea is you just have a little snippet of code somewhere, and you don't really even care about what server it's running on. And a lot of these MBAAS suites kind of integrate that idea in their design. A lot of these, as I said, are talking about mobile back-end stuff. So a lot of DevOps sort of features are already integrated in these suites, and a lot of times they even help you with the front-end design. So they either, for example, give you a library that you can use, or a lot of times you just write what you want in XML or maybe JavaScript, and they go ahead and create the code for Apple iOS, Android, so on and so forth. But so these are some of the commonalities. But then there are, of course, different spectrum of services that some of these provide. So for example, some of them have better enterprise integration with some tools. For some of these names that I mentioned, for example, come from VMware, some come from Intel, some come from, so they have different levels of enterprise integration with that suite of tools. And again, there is a kind of wide spectrum of whether they allow you to run on your on-premise cloud or private cloud or public cloud. There is a wide set of differences. And of course, some of them actually have gone so even towards getting certification, compliance with certain standards. So for example, you have some of them that comply with HIPAA requirements, which is medical records requirements. PCI, it's the financial industry credit card sort of requirements, and so on and so forth, EU data security standards. Some of these MBAASs go ahead and do that, and then it's pretty much guaranteed that, okay, I'm going to go ahead and use this MBAAS to develop my app. By default, by standard, it comes with HIPAA compliance, and you know how easy that is. So so far, we've in our course, we've focused on a little bit lower level of detail than these frameworks would allow. So we talk about specific, for example, storage, cloud storage, talk about Amazon AWS infrastructure as a service, platform as a service. The idea again here is to integrate all of those and give you one shop. And it's a very new development. It's worth definitely looking into if you want to create an app.
and then we'll move on to some systems in the cloud. One of them is a file system called Ceph, which is used pretty generally. Certainly, that there are other file systems of a similar nature, but Ceph is really sort of archetypical. We'll show how that works and why that is such a big deal. And we'll then look at relational databases and things like HIVE, which allows you interactions. You can write SQL queries and get data back from really massive numbers of nodes in real fast time. And then finally sort of round that off, we're looking at TES, which is a full-scale database that is often used to support some of the cloud front ends that you actually play with every day. So this is our basis for the course. We have planned this out to gradually introduce you to all of the major components of the cloud, to approach it from a professional point of view. We're going to get you to program some parts of that so you actually understand some of the nuts and bolts. Now, the programming is nothing to be too scared at. You will actually be given lots of hints. So as long as you follow the hints, everything should go forward. It's not like you have to learn a whole new language to program anything, or even any language. You'll be able to find a lot of the detail in our slides and in our examples. But what we want you to do is to actually sort of get a feel for what these clouds look like and the fact that they are just programmable systems. They're really sort of software-defined architectures, and the software that we program with defines them and creates so many different variations. And that's what's intriguing. And of course, we'll lead up to the next course where we describe some of the architectures that have been built. So we've talked about HDFS, we've talked about, or we will talk about HBase, but underlying all of these different things, there's this notion of distributed file system. And way back, there was a distributed file system project that kind of gave a future look, which we never really sort of got implemented to a large extent. Ceph is almost the embodiment of that. It's a distributed file system that has the sort of logic, ways of accessing of Linux or Unix file systems, but it gives you a distributed store, and it gives you all of the parallelism and all of the redundancy and fault tolerance that you would like. It also is a rethink of just how do file systems work. When the file systems are built, they are built given the profiles of the jobs and the uses of the applications. And nowadays, with big data and large computations, we have different uses, we have different lifetimes, and so Ceph is accommodating some of those issues. So the motivation for Ceph, it's an emerging technology. It's providing an integrated, well-organized, distributed file store that takes into account what we are beginning to understand about big data. It's designed for performance, striped data over data servers, reliability, there's no single point of failure, it's scalable, and so it has adaptive metadata clusters. If we add more to it, the metadata can increase naturally and keep the performance moving. It's more general than HDFS, it has smaller files, and it has some rivals, yes, but it's leading amongst the pack of open source projects. It's leading the way to a new, fresh look at file systems for distributed computing. Cluster file systems have more or less similar ideas. They use ring-based hashing. Ceph uses a scheme called Crush, but today we won't get into that. So how do you build a really large distributed system? And I should point out here that Yahoo is actually using Ceph as a file system for petabytes of data, hundreds of petabytes of data, in fact, and achieving good performance out of it. So it does a divide and conquer. It takes away the metadata from the file systems and provides its own metadata server. It provides an object data server for all those actual pieces of data that it's stored in it. And then it has a monitoring system so it can self-adjust and make best use of all those distributed resources that it's got. It decouples the data from the metadata. The I/O is directly with object servers so that where the metadata resides and the servers for that don't get in the way of actually getting at the real data. It has a dynamic distributed metadata management system so that as you scale up the number of objects in your system, the metadata will scale, and it has reliable autonomic distributed storage, so it's placing the objects so that as you scale up, you're taking advantage of that distributed system, you're taking advantage of racks and how things are organized on those racks so that they are not sort of placing a single point of failure in a position where it could cause really serious harm to a big distributed system. So this is a diagram of the way that Ceph is built. And once again, you can see it's really broken down. It's taking the traditional file system. It's still got sort of many of the aspects of the file system, but it's breaking them down and making them distributed using lots of nodes in the system. And here we've got the clients. The clients are all sort of operating on this file system. They are all sort of making procedure calls to actually access the files using highly sort of evolved protocols to actually stream the data and get the data. Over here, you have a metadata cluster. What that is doing is providing all the directory information. It's mapping the names of your files down into the storage and identifying where all the objects, what all the parts of the objects are in your clusters. And that's, again, a distributed system. So as you scale the whole of Ceph, as this thing scales bigger and bigger, this can actually scale too and match the computational needs of what's going on. And here you've got your object storage cluster. It's again a distributed system, so if you want a larger storage, you can add to this. Everything is organized so that this operates cleanly. As you add to the storage cluster, the metadata will can be increased. Again, going back to your clients, what we see here is an attempt to get rid of all of that overhead of understanding a distributed file system you get in Hadoop file system, say, where you say Hadoop file system and then the command you want. Now what's happening is, well, you can run bash or your client code. You can use the Fuse libraries and actually sort of access this thing just as if it's POSIX, which is a real step forward. Now, why is all this really sort of interesting? Well, as you get big data and you're using more and more big data, the way we're using file systems actually changes. The way we have the metadata and the use of the metadata changes, because now the lifetimes of our data change. As we get more and more big data, we are accumulating it. Some of the lifetimes are not sort of in seconds or minutes. Now they could be years. They might be decades. Similarly, if you're streaming data in from Spark, whatever that we will hear about in the future, some of those, we will have a great deal of velocity in our data. We want to accommodate that in our storage systems. And again, in this system, we have adaptability through the distributed file stores that we've got here of being able to accommodate some of that distributed nature of the system. So we are decoupling data and the metadata. We're increasing the performance by limiting the interaction between clients and the servers. Decoupling is common in distributed file systems. It's what you would expect as we move forward. HDFS does that in same of name node, but name node is a bottleneck. Now we've removed that. Lustre and PaaS are somewhat similar in the sense of where they're trying to go, but Ceph is certainly state-of-the-art, a distributed file system, and is a great learning point. In contrast to other file systems, Ceph uses a function to calculate the block locations, and the reason for that is because it can then have a distributed metadata system, a distributed access, because that function, that's all that needs to be known for individual nodes to actually compute where is the storage. Overall, we have a metadata management system, and we put smarts into that system. It's dynamic, it can grow, but what it's doing is to distribute the load, accessing all of that metadata over multiple CPUs, over multiple servers. And that really allows you to get higher performance. If you remember with Unix, lots of small files, directory file information, and Unix file systems were organized with their inodes around that concept. Here you've got lots of distributed access. The metadata is organized around that concept, and so is the way that it's distributed amongst the storage. The metadata changes with the number of requests to even out the load amongst the metadata servers. The metadata servers can also quickly recover from failures by taking over neighborhood nodes. So this is very, very different from our traditional Linux systems. And it improves performance by leveling the metadata load across everything. So it's continually trying to balance all the performance of all the parts to give you the maximum parallel throughput for that file system. How about reliability? As we know, files, or at least disks, crash on a regular basis, and what you need to do is have a firm basis of replication underlying all of the store if you want reliability, and this system provides that. The data storage servers act on events all by themselves. They initiate replication. They improve performance by offloading decision-making to many data servers. They improve reliability by removing central control of the cluster and setting it out amongst all those distributed nodes. So I'm going to talk to you about HIVE, which is a database that runs on top of HDFS and uses MapReduce to do its computation. The whole idea was started at Facebook, and it was to look at data from nightly cron jobs. They were put into an Oracle database, but that proved to be a lot of overhead, and the data was very large. So they developed an ETL using hand-coded Python and developed their own language called HQL, which was a variant of SQL. And what HQL does, it's a query language for HIVE. It avoids some of the problems that you get into with if you have an eventually consistent sort of system, and you're looking at all these things in a distributed manner from multiple machines. Then HQL provides you a way to do that, and doesn't require you to have a rigid sort of SQL type of interpretation. So what we're looking at with HIVE is a translation of queries into MapReduce jobs, and this can run on top of Hadoop Yarn. It runs on top of Tez or Spark as well, which gives you alternate ways to actually implement it, and sometimes those can be faster. Again, note here that the database itself is not updated or changed in any form while this is all happening. You're assuming a read-only database, and it's going to focus primarily on the query part of the language SQL, the implementations. So there are missing pieces of SQL, if you like, in HQL, but they allow it to perform very fast. So Hive looks very similar to an SQL database. You can do a relational join on two tables. If you have a table of word counts from Shakespeare's collection of words in a book, and you have another table of word counts from Homer and one of his books, and you want to actually compare them, you can do so, and that would look like an algorithm like this. What you're doing to select from Shakespeare's in here, and you're going to get the frequency of the words that you have selected, and then you're going to join that information with the same thing applied to another select applied to Homer. So here's the Homer data with the words, and what you would like to do is just to look at the ones that have some sort of values in there. So we're asking that the frequency counts are bigger than 0, both in the Shakespeare and in the Homer database. And then we're going to order the whole result of that select so that what we have is a limit on what we're going to print out. It's going to be 10, and we will do it in descending order, and that's what's actually listed below, the 10 top frequency words that appear in the join between Shakespeare and Homer. And surprise, surprise, leads the pack there. So behind the scenes, what is that example actually doing? Well, what it does is to take the data from these two collections, and it creates an abstract syntax tree, which is sort of just basically a set of tuples, and the words from those. And as you can see, what is collected here is where those words occur. It looks like a syntax tree where you're taking the Shakespeare words, so you're taking the Homer words, and then you're applying different operators that are Hive primitives to those. And as you work through, you'll see that each of those Hive, the HQL has been translated into this more sort of primitive sort of language of looking at each individual item and applying a function to it. And what then occurs is you take all of these and you map them into one or more map-reduced jobs. So, for example, with the word, looking for counting the number of words, what you're going to do is be building a map-reduced job that counts the number of words from the Shakespeare job and then from the Homer job, and then you're going to go down here with the join, you're going to write a similar map-reduced job that maps these two things together. So, Hive, as you've seen, it's actually got a shell, and you can write pretty much that language into a shell. And the introductory tutorials from Hive on our Hortonworks builds that type of query in the shell like that. There's drivers that handle the sessions, fetch and execute. There's a compiler that does the parsing and planning and optimizing how the map reduces will be performed and what analysis goes on. And then there's an execution engine that takes all of this description, that sort of abstract syntax tree, and executes it as different map-reduced jobs with HDFS and all the metadata to build the results, which it then stores back in HDFS. Hive uses a traditional database to store its metadata. It's a sort of namespace containing a set of tables. Those table definitions contain column types, physical layout, holds partitioning data. It could actually be used to store data in a variety of different databases, depending upon what you want. But if you can map them into something like HBase, you can get a much faster implementation. The Hive has a warehouse directory in HDFS that's sort of built for Hive, and there's a tutorial that provides lots of examples on the warehouse in Hadoop works. The tables are stored in subdirectories of warehouse. The partitions from subdirectory of the tables allow you to access pieces of each of those tables on different machines, and then you're going to use MapReduce over the whole thing to actually aggregate it. The actual data is stored in flat files. They're delimited text or sequential files, and they can be customized to use any sort of format, but mostly just text files. So this whole thing sort of ends up looking like an HDFS with blocks holding ASCII text that's actually input to do the manipulations by your MapReduce programs. So I'm going to finish up talking about Pig and Hive by referring to TES, which is really the underlying magic that makes it all work. And TES is a sort of graph algorithm type of system, a data flow based on graphs for doing computations, and it's the magic that allows Pig and Hive to get mapped down to MapReduce and efficient operations on Yarn. What we're doing is to empower end users. We're giving them a really sort of expressive data flow definition, and then we're providing an interface on top, a language on top to use it. And at the level of TES, this expressive data flow has all sorts of different implementations that can take advantage of the underlying distributed system. It has a flexible input, processor, output, runtime model. It has a data type agnostic that allows you to be able to treat all the data types in a similar way. It has an easy to deploy simplification so that actually allocating resources to this is made easier. The execution performance is rather fast, and what we see is that where you've got MapReduce, sometimes you have to say, oh, I've done this map and now I've got this trivial reduce, I've got to do this reduce and do it, and then you've got another map afterwards. You could perhaps eliminate that reduce. You could perhaps alternatively eliminate a map. Well, that will be difficult with the MapReduce primitives, but with TES and with using Pig and Hive, it will do that optimization for you and make everything fast. It has optimal resource management. It sort of allocates the resources when needed. It will plan reconfiguration at runtime to get the maximum number of nodes doing your computation. It does dynamic physical data flow decisions to try and sort of get the resources, the data to the resources and the algorithm to the resources to do all of the magic required to do Pig and Hive efficiently. So, integrates Hive and Pig. As I said, you get extra MapReduce jobs when implemented with Hadoop compared with using TES just plain by itself on Yarn. When you think about it, that's natural. MapReduce is very formal. It's very sort of stylized. It's very structured, and it doesn't give you a lot of flexibility. Whereas with TES, describing the data flows, it can describe pretty much anything, and then all you need to do is to translate that into an implementation on Yarn. Here's some examples of what TES would do in the way of data flow. You can see various different map pieces here, and no corresponding reduces. The map creates HDFS files, and then the data flows down through here. You have some reduce at the end, producing your result on HDFS. And again, you can describe that very easily with TES. Pig and Hive will create such graphs, and when you optimize them, those reducers will pop out of the system, leaving you with that nice sort of clean graph. And here's a similar sort of structure. Now it's a little bit more complicated. You're doing some sort of distribution from two different nodes and aggregation of that. And then you've got two reducers down here taking samples from all of these systems and again producing a result. But what's key here is that the two map phases can be fed into other map phases, so you can get more subtle interactions, and there is no sort of overhead of intermediate reducers needed to actually construct that graph. I want to talk about Swift now. It's an example of an object store. Object stores have tremendous use in cloud systems. Swift provides you an object as a blob that you can access. It's accessible through the web, has web interfaces, and it really forms some of the backbone of the Apache OpenStack systems when you're trying to use those systems as, say, provisioning videos and so on, large objects that you want to handle to and you want to include, but you want to organize them efficiently on the storage. So we'll get around to describing Swift in a second. Let's first just look at why does one need this type of system as opposed to, say, a file system. This is really oriented around providing needs that have emerged from the web, from big databases that store huge items in them. For example, if you have a database of images, let's say they're MRI images, those MRI images might be multiple megabytes, and you want to store them. You don't want the database to be cluttered up with all of that object, and so you would have a pointer from the database to, well, a blob of data, a large binary store of data. So that's where they come from. They're named as blob. It's kind of a interesting sort of roundabout way of labeling that particular entity, but one of my favorite stories about blobs was that it came from a science fiction movie featuring Steve McQueen. A blob was a big lump of jelly that sort of went around devouring Manhattan. And you kind of feel that's the right thing for a huge amount of data. So the use case, if you want to store unstructured or structured data, but if it's unstructured data in particular and it's very large, it could be text, could be a binary like a VM image, you're going to use up a lot of space on a disk, and with typical databases, you would like the databases to be flexible in providing relations and joins and all this other stuff. You don't want it to be wasted sort of just recording a huge amount of one object. So move it out to a blob store and refer to it, and that's a perfect sort of solution. Typical uses: images, movies, audio, this sort of audio, signal data like earthquake data. It could actually record a large queue of messages. So if you get a lot of incoming LinkedIn messages going from one client to another, you could process them in a blob. Typically examples where they're used is LinkedIn. The LinkedIn data, if you look at the user page, it has lots and lots of detail about somebody's career. It might have their CVs, it might have pictures of them, it might have movies of their accomplishments. LinkedIn uses a system called Ambry to actually record those blobs, and Ambry has a sort of similar design to what we're talking about today, but a little bit more sophisticated, but let's go easy for the moment. it's usually, all these blobs are usually accessible over the web. And the handles to the data, the sort of pointers to the data, are usually URLs that can be embedded either in a database or in a web page where you could click and actually retrieve them from the site. Companies that use blob stores, well, Windows, Azure, Ambry we've mentioned, Facebook's warm blob storage system, Amazon's simple storage system S3, we'll talk about that in a second, and then Apache's OpenStack blob service, Swift, which is what we're talking about now. Why? Well, data has grown tremendously. It averages about 50% increase a year. A lot of that data, like half, is unstructured, or it's archival, or it's sort of a binary. People want to access that using technologies they know about, and typically that's HTTP. So the closest APIs that one can use for that would be something RESTful, doing a put and a get using HTTP. So that is exactly the avenue that all these blob stores have taken now, including S3. You actually write HTTP requests to get at the blob data. You would like it to be highly available, which means you're going to have redundant copies of the blob in different places, perhaps even in different places in the country in the case of Ambry. So there's no single point of failure. If the network goes down, in the Midwest, across the Mississippi, you're still going to be accessing the data from LinkedIn and Facebook on the east and west coasts. It's not going to matter. You want your data centers to be agile so you can change them and maneuver them around. Well, having an API that's organized in this manner allows you a great deal of flexibility in the way you construct your data centers and where you place them. It's open source, so you can build and you can look at the code. Oftentimes it's organized multi-region, so the same regions or different regions in the country, east, west coast, Europe, will see similar content from the blob stores, say on LinkedIn, totally geographically distributed, but there will be distribution of data between the blob stores in order to maintain the image that everything's the same in all the countries. There will be storage policies about it, what can you store, what you can retrieve, how much storage you can use. And oftentimes tricks will be used to actually make that storage both redundant and sort of smaller. So it's often a place you find erasure coding. In fact, in Swift you find erasure coding, where you are actually putting things on disk in a highly coded manner, so that even if one of the disks finds that one of the disks doesn't work, you can still reconstruct what was on that disk and use that in your distribution or access to data. So, looking at what you might do, if we were to put up a Swift server in Illinois, we would sort of provide a host for it, say swift.illinois.edu, and you would access the Swift elements by specifying our site, our host, in that URL. And then as part of the URL, you include what version of the data that you're going to actually look at. So we're going to look at Swift version 2 organization of the data. We would then specify what account the data belonged to. In this case, it could be me, so it could be Roy. And we would look at the container that was allocated to put all these objects, these blobs into. So, some container, favorite my blobs perhaps, and then the actual object itself, maybe one of these videos. And here just below I put the actual HTML you might use. So you might be doing a put, which would be one of these simple requests RESTful requests, and I'll be putting video into version 2 ROI my blobs class video, or if I want to retrieve it, I'll be doing get in the same manner, maybe accessing Rez's data from his blobs instead of my blobs, and a different recording. So here you've got a simple sort of structure, and it gets mapped onto, well, this is a simplified version of what Swift looks like. What we've got is 3 major pieces to this: a proxy, account, container, object sort of system that will choose which disk to use, and then all of the different disks that the data is recorded on. When I get web requests, what those would look like is URLs. They will go through a web front end. They will then be load balanced across a whole bunch of proxies. I've just put one proxy in here just for simplification. One of those proxies will pick up the request, and what it will do is to work out what that handle means in terms of where the item is stored on disk in the various, in the containers for objects we've got. And you see in the next level there's a block. What it's going to do is to keep track of which accounts are using which bits of disk, and the containers they're using, and then the objects within them is almost sort of like a directory. When you get a request, you're going to map those into those 3 parts, and that will tell you where to retrieve the data from the actual disks. Again, there might be some processing involved. So for example, you notice that there's 3 red squares, perhaps corresponding to a file, to a blob. You would want to retrieve those, put them together into a consistent view of what the blob is, and it might involve erasure encoding, in which case you're going to have to decode it to make sure that you've got all the right bits. So one of the key issues for a blob server is actually how do you record the blobs into the system. You can imagine lots of people uploading videos, and then what you want to do is to make sure that there's a lot of throughput through the whole system. So this diagram shows you how that might work. The client requests come in, they go through some sort of web server, they come to a load balancer. The load balancer is going to choose an arbitrary proxy. There's lots of proxies it could choose. It doesn't really matter which one. They will be implemented on different nodes with different networks so that you don't get any congestion. Then that request will be identified with certain object storage nodes. The objects that are stored will be on different nodes. I've labeled them yellow here. And what's going to happen is you will pass all of that data through to those nodes, record onto the disks associated with those nodes in the right way, using whatever encoding schemes. And you get a lot of parallelism going on because of the replication. After that's finished, what happens is that you get acknowledgements that all of this data has been written. And here you see that we've only got 2 acknowledgements. We haven't got a 3rd acknowledgement. This one never occurred. What it's going to do is to say, well, if there is a quorum of replies saying that, okay, everything was successfully stored, then you've stored it in Swift. And in this way, we can make it very available, and it doesn't really matter if there's machines that are down or whatever, as long as you have it recorded on several machines, a quorum enough of machines that it really is there to be able to retrieve later on, then it's all worked. So if you're doing read requests, that doesn't really matter, and you can just go and ask for a read. You go through the load balancer again, you go to a proxy. Proxy is going to pick one of the nodes and see if it can get the data from that node. If it doesn't, it'll go to another one. And you notice there's an acknowledgement. But it only needs one reply, really, because everything can be checksummed, so you know whether you've got it all. Now remember, those blocks were not just simple blocks. They're talking to a complicated set of disks and so on, but that's what's happening here. Details, well, you have these checksums associated with each object so that you know if you've stored it or retrieved it successfully. There's auditing, active replication. So for example, if a system loses one of the disks, what it's going to do is say, oh, I've lost some of the blob. So I'm going to now copy from from the other copies of the blob, I'm going to copy those copies to a new replicant just to make sure I have enough duplication in case another disk goes down. This system will work with any size disks. When it has different size disks, you can give it priorities, but that's all taken care of by the mechanisms. How does the addressing go? Well, we started out with the string. What the Swift does is to take the string and map it into things called partitions on the disks, and then find where all those disks are located and what it needs to retrieve. So effectively, you take the disk space, say you've got disk 1 to 8, and you'd put partitions on those disks. The reason for the partitions is so that you can spread out the Swift blobs across different partitions on different disks. So we would end up with 128 partitions, and what we're going to do is to spread blobs over enough of those partitions, perhaps a different partition on each of the different nodes, or each of the different disks, I beg your pardon, each of the different disks, so if one disk fails, you still got a copy. If you go to 2 nodes, what it actually does is to make the partitions bigger. You still get the same number of partitions, and the reason for doing that is it keeps the addressing the same. Now, to take the string, the HTTP string, and map it into which disk it is, what you have is an algorithm that takes the string and maps it through to the particular partition that it's stored on these machines, making sure there's a distribution and everything else. And that sort of that algorithm is based on hashing into a ring. The ring is really sort of just a hash map into those storage partitions. You can see you could have the alphabet organized around, say, the blob names, and they would indicate the actual storage locations as a sort of 2-dimensional array of where that particular item is stored. I'm not going to go into all of the details on that, and there's different ways to do that. The Swift is readable. You can find out about it if you like. There's papers about it. It is similar mechanisms on S3 and a lot of other blob storers, and if you want to follow that up, that would make a good reading. Well, no description of blob storage will be complete without giving you a little bit of detail about what is commercially available in terms of blob storage and what's easy to access and play with. Amazon S3 has been around for several years and provides a blob store, and that's what we're going to talk about now. Unfortunately, there aren't a great deal of papers, there aren't very many papers actually describing how Amazon S3 really works. But you can assume that Swift is somewhat similar to the way S3 works. So it's an online file storage web service provided by Amazon. What it provides is storage, blob storage, large chunks of video, images, whatever. You access it through web interfaces. It uses REST. Used to use SOAP, but now they're sort of backing off using SOAP. It does use BitTorrent. Wikipedia just gives a quick overview of its history and where it came from. The intention of Amazon S3 is a really scalable system, so you can have an infinite sort of storage for blobs, and it gives you very high availability, very low latency, sort of perfect for building things like web services, especially if you want to sell, lots of widgets on the web, and you need to power that web engine in appropriate ways. So the intention was to get really sort of high availability. Here it sort of says 99.99% availability, which is really very good. That means in a year it's not likely to actually go down at all. Typically the files are very large. The way it actually stores them is as max 5 terabyte chunks. You can actually split objects over more than one file, more than 5 terabytes. And I'm not going to describe how to do that, but that is a sort of measure that Amazon's built. The objects are stored in what users call buckets. So when I sign up for Amazon Web Services, I'm allowed to create different buckets, and in the different buckets I can put different objects. So it's a way of sort of organizing things. It's not really a hierarchical storage system. It's really flat. So these buckets, not quite the same things as directories. The user is allowed to assign keys to refer to objects, and those keys are actually just strings. They have to be unique, which makes it an interesting choice. But again, using the URLs and the sort of hierarchy offered by URLs, you can combine that into a key that is unique for accessing that object. The Amazon machine images that you often see, well, adverts about that, you have a VM and you can store your VM in Amazon and then retrieve it later and sort of run it on your Amazon EC2 node. That type of thing is also storable as a blob. And in fact, one of the motives for this, so you've got your VM, you've got all of the file structure and everything else, you can convert that into a bundle of objects, essentially one for each of those parts, and store that as a blob on the S3, and then when you want to run it again, it's still on S3, you can bring it back, instantiate it, and away you go. A lot of different companies have been using the S3 service. And it starts out, one of the bigger users that started out with it, SmugMug, which is recording pictures of people. So they sort of pioneered using this store. It can actually be used directly for Hadoop. So you can record, if you remember Hadoop, the way it uses the stores itself is as an append only and read at one end and sort of gradually move down a sort of sequential file. It has a very deliberate approach to using the files. Well, Blob Store will actually work for that. You can work your way down the blob. And so a lot of the Hadoop work can take advantage of the S3 file store. Netflix uses S3 for a lot of its metadata and also some of its pictures. Reddit does as well. Dropbox is also a user of S3, and so is Tumblr. It keeps its images there. So in brief, you have a bucket. A bucket's a container for objects. It describes location, logging, accounting, access control, and it has a name that's got to be unique. So gave a couple of examples there. If you want to supply just somewhere in Amazon, you can actually specify a name, bucket S3 Amazon AWS, and Amazon will look that string up and find where it is. If you want to say that, no, indeed you want the the AWS region on the, well, let's say you want AWS East Coast, you could actually specify that and direct Amazon to go retrieve the bucket from the East Coast. The bucket itself can hold any number of objects. I described its limitations there, but you can actually have objects that are bigger than that stored in multiple places. Again, you specify those pieces with a web request, and the form of that is, well, a bucket on Amazon use in a particular object as a string. And if you want to add your own name to this, you would say, well, you know, John Smith at S3 Amazon use, and photos of puppies. So the string really, it doesn't really matter in a sense what that string is. It can be organized around user attributes that are interesting, and what Amazon is going to do is to take that string and associate it with the actual data stored and allow you to put and get to that object. Here's an example of how you might do that. What you notice is same REST commands as in Swift. You can post, get, you can delete objects. In Amazon, you can list the keys present in the bucket, and you can filter them out, so you can try and reduce the number that you need to sort through. When you are using S3 or when you're using Swift, you can see how awkward, how difficult it would be to maintain some sort of integrity about the view of all the data inside the system. So S3 has a sort of weak consistency model, and so does Swift. What it does is to say, well, if things have been long enough since you actually updated everything in the stores, then they'll be consistent if you go and read them. But if you update them and look at them immediately, they may not actually be what you expected. They may sort of be partially updated and therefore a little bit inconsistent. This is called eventual consistency, that if you leave it for long enough, it will become consistent. If you're writing lots and lots of code and you're doing lots of parallel operations, you can be worried about this, or you might be worried about this. If you're building something like Amazon's sales, then this is not such a big concern. If you want to worry about sort of people bidding on objects and so on, you would not implement that with S3. So you achieve high availability by basically allowing lots of access, by replicating the data, and if your put request is successful, the data is stored. But if you get lots of writes at the same time, or you write an object and you try and read it, unless you've got a very, very fast system and there's not much load, the change may not propagate quickly enough. S3 might say that you don't have an entry for that key, and so it would miss. But if you come back later, you would find it. So you do have to wait. And a process replaces existing objects. Well, you might see the new one, or you might see the old one. If you delete an existing object, you still might see it. So you just have to wait for the system to get consistent. That's a bit of a handicap, but on the other hand, in a sense, it's a small price to pay for a marketplace of different system or different sales items that has a huge volume of commerce. This system is really designed for particular object or particular applications in mind, and it does it very well. So let's suppose you log into AWS and you're writing code to access AWS. You don't want to mess with perhaps the HTML, you could actually write command lines that do the same thing as the HTML. And here's some examples. Here you're making a bucket, first line. Then you are copying a local file into the bucket. What you've done is to identify that copy with a key, and then you can move that key, that object that has the key name, into a different bucket with a move instruction. You can list what's in a bucket. You can remove what's in a bucket if you know the key, and you can actually go and remove the bucket if you want. And there's help commands, and so it's all fairly simple and very intuitive if you going backwards and forwards between, say, building a web server that accesses these S3 items, these S3 objects, or writing code in, say, EC2 to actually access the AWS. It's a very intuitive correspondence between what you have to say in each case.
In this video, we will talk about cloud-based block store services. Now, to put this video in a bit of context, in previous lessons, we talked about Amazon S3 service, which is really an object storage service provided by a cloud provider, in this case, Amazon, right? So what's the difference between a block store and an object store? So in an object store like Amazon S3, what you have is a service that you can feed complete files to, and you don't have any other specific accesses. You don't have any sort of file system. In truth, even though Amazon S3 looks like a file system, it doesn't quite behave like a file system. Now, Amazon, of course, provides this other type of service as well. Provides you with things that are block level storage. Now, what is a block level storage device? Block level storage device is something that resembles a traditional hard drive, or in modern times, SSDs, for instance, right? So basically what the device, now in this case, virtual device, provides you is a whole bunch of little blocks of storage, just like what a hard drive would do. A hard drive really provides you a whole bunch of little blocks, sectors on the disk. Each block could be 4 kilobytes, 8 kilobytes, so it's very small. And then the file system that the operating system provides manages these, right? So it provides a level of abstraction on top of what the device, hard drive, or in this case, virtual hard drive, would provide, and basically build on top of that. Now, the first type of block storage that I want to talk about in this lesson, in this video, is instance store, right? So instance stores are a form of cloud-hosted temporary block level storage. Now, why do I put emphasis on the word temporary here? Because these are devices that in reality, when we are talking about the data center that is running your application, your cloud hosted service, EC2 instance, these are temporary storage devices allocated on the very same hard drive or SSD, on the physical hard drive that is co-located on the same EC2 machine that is running your EC2 instance. So what happens here is that if for whatever reason you lose that machine, and I will provide some case studies, you will lose all of the data stored on an instance store. So for example, if your EC2 cloud instance is stopped or is terminated, you lose access to your data. On the flip side of the coin, though, since these are co-located on the same physical machine, they typically offer higher throughput performance and bandwidth for the instance. These sort of instance stores are best used for temporary storage, but when you need high performance, for example, caching of temporary files. Of course, in this case, you would store your persistent data on a different type of servers, which I will talk about in the upcoming slides. But let's take a look at this graph for a second. See, like on the physical host computer 1, you have two types of instances, EC2 instances running, instance A and instance B, right? And then you have a couple of instance stores, ephemeral 0, 1, 2, 3, right? Note that if your EC2 instance is running on this physical machine and some other customer's instance is also running on the same machine, the physical hard drive or SSD that's hosted on that machine is divided between you guys. Of course, you don't access to somebody else's files and vice versa, but the device is really shared between you guys. So in this case, example, you have a host computer number 2 who's running an instance C, and that instance C has access only to instance store. If you're talking about instance store, the storage on the very same physical box. So let's talk about the lifetime, because I keep talking about the temporary nature of these. So data only persists on an instance store during the lifetime of an associated instance. That means an EC2 instance that is running on that very same machine, right? So if somehow, say you have an instance and you're running an operating system on top of it. If you reboot, you still have your instance on the very same machine. As long as the machine is thinking, it's still running your machine. It doesn't necessarily move from one physical box to another physical box. So your data store, instance store, in this case, persists. But if for many reasons, for example, if the underlying hard drive fails on that physical box that Amazon is hosting, or if it fails, your data is lost. Or for example, if the instance stops or terminates, when you stop an instance and when you launch it again, Amazon could very well go and launch it on a totally different physical box without telling you. And you're actually, if it's a true cloud environment, which in this case is, you don't even need to know ever what physical box you're running on, right? So now that you're running on a different physical box, now you have lost access to your instance store data. So if you want to, keep access to your data stored on instance store, you should never stop your EC2 instance or terminate, which in some cases might make sense. In some other cases, totally defeats the purpose of cloud computing. So it totally depends on what you're doing with your instance. Now, these are data stored on the physical hard drive, right? So if you want reliability, there are multiple things you can do. Assume you have a whole bunch of EC2 instances running on different machines, right? You can try to launch a sort of a distributed file system. And we've talked about different types of distributed file systems. For example, HDFS. You can try to launch a sort of an HDFS file system on top of instance stores. And then the file system tries to replicate file chunks across them. And then that sort of at least saves chunks if there is a physical failure with one of the disks. You can also try to periodically back up your files from your instance store into S3 or EBS. Now, I haven't talked about EBS. I'm going to go talk about EBS in the next slide. Last thing I want to talk about instance store is that the sizes are typically small. Depends on whether your EC2 instance is running on an SSD hosted box or an HDD hosted box, which is older generation of Amazon hardware. The newer generation, M3, M4, they typically only run on SSD machines. So if you're running on SSD boxes, you can typically get a rather small size for your instance store, something between 80 gigabytes to 320 gigabytes, depending on the EC2 instance type you choose. If you choose the really large storage one instances, for example, X1.32X large, you can go up to 3,800 gigabytes, almost 4 terabytes of instance storage. But of course, those instances are pretty expensive. If you go with HDD instances, you can get up to 1.5 terabytes almost of instance store. So now moving on to the other type of block store service provided by Amazon. Now this is called EBS, Elastic Block Store. Now what they mean by elastic means that now, unlike the instance store, where it is really tied to the physical SSD or hard drive that is on the machine, this one is elastic. It has more cloud features, right? What happens in reality is that these are sort of software written services that mimic what a hard drive would provide, but they are typically accessed over network without you knowing about it, of course. All you see is a hard drive, or what looks like a hard drive, that you attach to your instance. But in reality, what happens is that they are run in some other machine, and your EC2 instance accesses these storage or virtual storage devices over a network, unless you go for EBS optimized EC2 instances, in which case the cloud infrastructure tries to play some games and try to either put the EBS machine closer or on the same box that you're running. But all of those are, of course, hidden to you. The elastic nature of EBS means that they play nicer with the rest of the services that the cloud tries to provide. So, for example, what you can do is you can attach and disconnect these sort of devices while your EC2 instances are running from your EC2 instances. So your EC2 instance is running, you can say, hey, attach this EBS volume as if you are, for example, attaching a USB hard drive to your machine. And you can detach it the same way. So you can imagine that the data on EBS volumes, unlike the instance store that I talked about, persist independently of the life of an instance. You can attach, detach. They are much more reliable, and they keep the data. You use this sort of EBS volumes when the data must be quickly accessible and also requires long-term persistence. They also support encryption, so you can just designate the EBS type as if you can just turn on a feature and say, I want encryption, and without you trying to implement, say, an encrypted file system on top of it, it will just automatically encrypt the blocks. The file size is also, the EBS size could also be much more easier to control. It can be up to 16 terabytes in size. There are actually different types of EBS instances provided by Amazon in this case. So the 4 types that they provide as of right now, 2016, are, I've provided some information about them here. So we start from general purpose SSD-backed EBSs that typically support 100 IOPS, that's IO operations per second per gigabytes. That's kind of a sustained access rate. It can burst up to 3,000 and in the maximum 10,000 IO per second, and a typical 160 megabytes per second throughput. Now you can also go for, instead of a general purpose, you can go for provisioned IOPS SSD type EBS. They're called IO1. In this case, you as a customer can say, hey, I want this specific minimum level of performance from my hard drive. And then, of course, the cloud infrastructure tries to make sure that, with all sorts of tricks that they try to do, and where they put your EC2 instance and where they put the EBS storage and whatnot, they will try to make sure that the guarantees are satisfied, right? So in this case, you can request up to 20,000 IOPS and 320 megabytes per second of throughput, and you can provision them. Now, there are two other options. These two other options are magnetic hard drive based storage options. Of course, it's still EBS. You don't care, but the choice of what EBS type you use, you pick only affects the performance, not how you interact with it. So in the case of STL1, you have low-cost magnetic storage based on hard drive. It provides pretty good throughputs, up to 500 megabytes per second, right? This is actually really good when you have big data sort of workloads, when you have large sequential workloads, for example, MapReduce, Amazon Elastic MapReduce, EMR, sort of an ETL, the sort of workloads that typical enterprises use, data warehousing, log processing. When you do that sort of big data workload, Hadoop log processing, these sort of things, that type of hard drive backed instance provides very good performance. And finally, there is inexpensive magnetic cold HDD sort of EBS storages that the throughput is half as much as the previous case, 250 megabytes per second, but of course it's less expensive. So to wrap up, the block storage services they basically mimic the functionality of a hard drive that you would attach or detach. And they're really the basic blocks of storage in the cloud environment. And of course, as I mentioned, they behave much more like a hard drive than what Amazon S3 would provide, which is a big file-based storage system that we've covered in previous videos. In this video, we will talk about another cloud storage service provided by Amazon. And of course, we talk about Amazon in this case because it's kind of a common cloud provider, but it's really a case study, right? So other cloud providers provide similar services. Now, Amazon Glacier is an archival storage service. This is unlike the previous two types of Amazon storage services we talked about, Amazon S3, which was a file. It was really an object storage system that would provide you buckets, and you can just put a whole file in it or not. And then the second type was block storage-based services. So we had Amazon EBS, Elastic Block Store, and Instance Store, as that kind of mimic a hard drive. Now, Amazon AWS Glacier, if you want to actually extend that analogy, it basically mimics a tape drive, right? So typically in enterprises, when you want to create an archive of your data, especially if it's large amount of data, you use a tape drive system to back up your archives. You take out the tape drive, you put it in some sort of a very secure storage environment, maybe like in an old mine or something, abandoned mine or something, and you don't touch it, right? Anytime that you want to get that data out, again, you have to send somebody to go grab that tape, come back, put the tape in the machine, and then load it. So a couple hours of latency required to access your data. So it's basically the same sort of idea here for Amazon Glacier. It's very low cost. It's only the 0.007 cents per gigabyte in now 2016 per month. So it's very low cost. It's very durable. So the facilities that are designed to store your data, and Amazon doesn't quite clarify whether it's really like tape or not, but it probably is. They guarantee an average annual durability of 99 point a whole bunch of nines. So it's very durable, and it's guaranteed for your files to remain there pretty much forever. Each single archive that you want to put in Glacier can archive up to 40 terabytes of information. And then, of course, archives are themselves organized in terms of vaults, and you can have as many vaults as you want, or a whole bunch of vaults per user account. So basically, if you want to archive a huge amount of data, you can just use Amazon Glacier. Now, the main access point to Amazon Glacier is Amazon S3. So you don't directly read files from Glacier, or you don't directly write to a file from your application or web service or whatever into Amazon Glacier. You do your work with S3, and then once your data in S3 is kind of old, I mean, you still keep your data in S3 up to, I don't know, maybe a month or 2 or 3. And once you're pretty sure that, okay, the data is pretty much old, nobody is ever going to use it, pretty much nobody's ever going to use it again, but you have to still keep it for maybe regulatory reasons or whatnot, then you move them to Glacier. It typically, so for example, when you put data in Glacier and you want to read them back, it typically takes between 3 to 5 hours to prepare your download request, right? So you say, hey, I want that archive. It takes 5 hours for it to be ready. And after that, you have a 24-hour window to download it from the staging location, or the file will be removed from the staging location, and then you have to submit the request again. And all of these, of course, have add costs. So it's very inexpensive storage only for the storage. If you want to use it, a whole bunch of costs will get added on. So you use Glacier for data that you really never want to touch again. So just taking a quick look at this diagram from Amazon itself. So you see you can, to access data on Glacier, you create a vault. To be able to figure out who can access or not, you can use the Amazon sort of IAM, user access management tools. And basically what you do is you work with your data inside S3, and then you upload your archives to Glacier, and anytime you want to actually download them back, it takes, again, as it says on the diagram, 3 to 5 hours to initiate the job and track the job, and then 5 hours after that, your download job is ready to go. So again, to wrap up this service, basically, it's only for archive. Do not use it for day-to-day activities. Only really use it, the best use case for this is where you want to store data, probably never touch the data again. You need to store the data for regulatory reasons. That's when you use Amazon Glacier. In this video, we'll talk about kind of a new service that Amazon has provided. It's, of course, in the category of cloud-based storage services. And here we have a service called EFS, Elastic File System. Now, to provide the motivation of why this service exists and how it differs from the other sort of cloud-based storage services that Amazon provides, we should actually take a look back to see what we talked about, and we had, of course, videos on those. So the first thing that we talked about was Amazon S3. Amazon S3 is large and distributed. You can store huge amounts of files. Each file could be very large, pretty much, practically unlimited in size. But it's really an object storage. It's not really a file system. It doesn't quite give you performance guarantees. And even worse, it has eventual consistency model. You upload a file, you try to download the file again, oh, it doesn't exist. What happens? Oh, you have to wait like 30 seconds. So Amazon S3 is not really a file system. It's big and large. It's distributed. Now, the other type of things that we talked about, we have block storage, like two types that we talked about, elastic block store that is more durable and persistent for data. And there's instance store that's run on the same physical box. They're not persistent, they're temporary, but have very high performance, good for caches. These are small storage options that mimic a hard drive. Yes, of course, an enterprise, think of a really large IT shop in a large, I don't know, Fortune 500 sort of company. Yes, they can actually build their own virtual cluster of 2,000, for example, EC2 instances or whatever number, and they can attach whatever number, 16, 32 number of EBS volumes to each of those and mimic a cluster, really, just a virtual one, and then build a distributed file system on top of these. A very viable option. This is what people used to do up until last year. But this requires operational expertise of running the cluster. And a lot of these companies have that, but that incurs a lot of costs, hiring IT people, system admins, and a lot of these. And now you move this whole sort of operation to a cloud, maybe you reduce some of the costs of running your own servers, but then you now require even more expertise for people to run now a virtual cluster, which is maybe one layer of abstraction over top of physical boxes, so you have even more interesting challenges to solve, right? And of course, we talked about Glacier. Glacier can store really large files, but it's only good for archival storage. If anytime you want to read something from it, you have 5 hours of delay until the data goes back to S3, and then you have to spend a whole bunch of costs. And then eventually, the file ends up on S3, which, as we started, doesn't quite make it as a file system, right? So there is a gap here for large enterprise customers that need large distributed file systems. EFS is an attempt by Amazon to provide a fully NFS version 4. NFS stands for Network File System. So it's a standard, of course, and a lot of file system, Gluster, NFS comply with this. So EFS is Amazon's attempt to provide such a service in their own cloud environment. The EFS is SSD backed, so access times are actually very good. It's highly available, highly durable. And this is very interesting because files, directories, links are stored redundantly, so there are multiple copies across multiple availability zones within an AWS region. So that's one interesting thing, and I'll have a chart comparing AWS EFS with EBS in the next slide, so I won't steal the thunder. But the difference here is that you can have EFS is backed for reliability purposes and durability across multiple availability zones automatically without you anything about it. And even nicer, you don't need to pre-provision capacity for EFS. It grows or shrinks as needed, and of course, as many other cloud services, you only pay for what you use. So let's take a quick comparison at how the Elastic File System EFS differs from EBS. So from a performance point of view, you see that EFS provides sort of a low latency, which is good. That's what you want. It's consistent. EBS is small volume. It provides pretty fast latency, so the low latency is lowest, pretty fast access. Of course, the data is consistent. The latency access is usually consistent. The throughput scale for an EBS, which mimics one hard drive, is usually a couple gigabytes per second at most. Typically less than that, 250 megabytes per second. In the best case, maybe like a gigabyte per second. In EFS, of course, it's a distributed system, right? Distributed storage. It's comprised out of a whole bunch of SSD-backed devices. So it obviously can support multiple gigabytes per second data access or throughput rate. Now, both of these are provide redundancy and durability. EBS, of course, is durable and redundant, but it's in a single availability zone. And we've talked about availability zones in Amazon infrastructure in other videos. But so an EBS provides redundancy within a single availability zone, while EFS automatically stores its data across multiple availability zones, and as a result provides even better redundancy and durability guarantees. And one EBS is usually attached to one single EC2 instance in one single availability zone. So if you want any more redundancy than that, you have to architect the system, a distributed system, using multiple EC2 instances and multiple EBS attached volumes. While an EFS storage automatically provides connection to, thousands of EC2 instances attached to it from multiple availability zones, and these all file accesses can come concurrently. And so, just finally taking a look at the different use cases. For an EBS, it's basically used for example, a boot volume, or when you have a small transactional non-SQL, or maybe even a non-SQL database, but you have 1 or 2 or 15 or 16 or a handful of EBS instances connected to one EC2 instance, right? While EFS provides for really huge big data analytics. It's trying to target big data analytics, log processing, media processing workflows, web services, even home directories like the traditional NFS trying to do. So to wrap up, this is a new service provided by Amazon, and it allows you to do a big distributed system, big distributed storage file system. It's a file system. It's consistent. It's very durable, and it's typically used for large enterprise customers. Dropbox has been one of the first movers in the area of user-facing cloud storage, right? Now, let's talk about Dropbox. It offers, of course, cloud-based file storage. Now, the specific niche that Dropbox tries to target, and it's of course not the only player in that domain, but it's one of the early movers, and their offering is quite used across the industry, is they want to be good user-facing cloud-based file storage, right? So they want to provide easily synchronized files across multiple devices. So if you install Dropbox client on your phone and on your Windows machine and your Linux machine and Mac machine and web-based integration, they want to make sure that the file synchronization works very well across all your devices. They want to make sure that you can access your files through web interfaces as well as native clients. Now, the interesting thing about clouds, about Dropbox, is that it itself uses clouds. So it's an example of a successful company that uses cloud services and then gives cloud services. The way it actually works is that Dropbox itself keeps metadata of files in its own servers, which is probably a small amount of information compared to files themselves. That's the typical story about metadata, right? Metadata is information about a file. that information is not probably that much huge. Your file could be a video file, could be gigabytes of information. Metadata about it is probably much smaller. So Dropbox itself keeps metadata in its own servers. It stores the files on Amazon S3. And of course, we've talked about Amazon S3 in our previous videos. And as you remember, S3 is organized as just a bucket storage. So you just put files in it. It's not quite a very well organized file system. For that sort of stuff, Dropbox manages their own metadata system. So let's take a quick look at that. But before that, to run their logic, Amazon also uses EC2 instances. And we've talked about that a lot in the previous modules even. So as I mentioned, the architecture is as follows. You, of course, user, are using your Windows or Mac machine here. And of course, your mobile devices you can use. When you need to access a file, you talk to the metadata service, which Dropbox itself is running. And it includes databases, metadata, and then, of course, notification services. So whenever, for example, a file changes or something, it sends you a notification. And then, of course, you have the files themselves stored in a cloud-based storage. Now, it's public information that Dropbox uses Amazon S3 to store its files. And then, to do the logic of accessing the files, or for instance, encoding, decoding, encryption, rest of stuff, the logic runs on Amazon EC2 instances. So it's a very interesting architecture. Now, for you guys to be able to utilize Dropbox, they have provided you some API. So it's not only that you can access Dropbox by installing their software on your laptop or your mobile. You can also use Dropbox in your own applications, and it's one of actually the quickest ways to make your mobile apps or web apps or maybe desktop, laptop sort of applications, cloud-based applications by storing files in the cloud in Dropbox or reading data off of cloud from a user's Dropbox. And in this case, you don't even need to worry about how to manage that because the users have their own Dropbox accounts. All you need to do is utilize their API, their libraries, and all of the magic behind the library takes care of a lot of things, including authentication, including figuring out what files the user has got there and whatnot. So there are two levels of API provided by Dropbox to access cloud files in an application. The easier API that I will probably talk a little bit more about in this video is called drop-in. Basically here, what they have provided are cross-platform user interfaced components that you literally can integrate them within your application in minutes. It's actually very easy. I'll show you hopefully to some extent in the next slide. There are two components to this. There's a chooser that you integrate in your application. The user gets a nice list. I'll talk about that in the next slide. And then you can download a file from user's Dropbox into your application in the phone or anywhere. And then there's a saver that once you have saved some file for your application, then you can upload it to user's Dropbox. Then, of course, there is the core API, which I'll talk a little bit about as well. It's designed really for more advanced functionality, for searching, revisions, restoring files, finding the difference between two different files, so on and so forth. It's very detailed. It's good for deeper integration of Dropbox API in your applications. Let's talk about the drop-in API first. Now, drop-in API is the simpler of the two APIs. Here you have two simple objects. You have the chooser object and saver object. The chooser object allows you to download a file from a user's Dropbox into your app. There are bindings, libraries for JavaScript Android SDK and iOS SDK for your mobile apps. Now, the second object is called Saver. It's actually even simpler. You have a file in your app. You want to just upload it to a user's Dropbox. At the moment, it's implemented only on web and mobile web, but it's actually a very simple solution. Just have a file, you want to upload it. We'll talk about this in a second. So these objects handle pretty much all the complicated and intricate details of authentication, which involves the OAuth authentication protocol, file browsing, and rest of the things that you need to implement. So it's very simple. You just, in your code, you say, I want this chooser object. And when user clicks on it, everything else is pretty much handled automatically by that object. So you do that. You just integrate the chooser object. And then when the user clicks, you can see a screenshot from a iOS app, in this case, is shown. You can see that it figures out all of the list of the files, all of the list of the folders. You can go scroll through the files and go in, go out, go back up, and eventually click a file that the user can click a file to be downloaded. Now, once that step is done, the object will return the control to your program with a set of return values, which include the number one, the most important one, the URL to access the file from Dropbox. So now we can open the file from that URL. It returns the file name, the file size, icon for the file in case you need it for whatever reason, and the set of thumbnails at different resolutions. It all returns all of those stuff to you. Now, the second object here is the Saver object, which is even simpler. All you need to do when you want to instantiate this Saver object is you want to pass in a URL for the file to be stored. A file name, it's the local file name on your own app, in the, for example, handheld device, and a set of options that are required. Now, when the user clicks on Save to Dropbox, again, now that object takes control, shows the user a nice UI of where they want to store the file in their Dropbox, and then when the user says save, it just returns to you. It does everything for you. So these are actually very simple. Now, the other API here we're talking about is the Core API. Now, Core API gives you complete access to control everything about the user's Dropbox account. It's implemented in many different languages. There are bindings for Python, Ruby, PHP, Java, and then, of course, Android and iOS, and even OS X have their own SDKs. And, of course, there's always HTTP. You don't want to not include the web apps. It's based on the whole thing. The whole SDKs is based on HTTP and OAuth, Open Authentication. It supports OAuth version 1 and version 2. And basically, it has a whole bunch of low-level calls to access and manipulate a user's Dropbox account. So you can do, you can create URLs, you can upload files, you can download files, you can get a list of files, you can remove files. Get a list of folders, even more interesting stuff. You can access a file's metadata, all the information about the file's history in Dropbox. You can get deltas, so you can check whether a file has changed from the last time that you have accessed it and how much has it changed, what has changed. You can get all of those information through this set of APIs. And another interesting thing is managing file sharing. So one of the good usages of cloud file storage is not only you can access your files, you can let other people share the file with you with different levels of access. Sometimes you want to allow them to be able to do whatever, remove, modify, edit, see. Sometimes you just want to allow them to see the file but not touch it. Through the low-level Core API, you can also manage all those accesses as well. So it's great if you want to integrate Dropbox with all its bells and whistles in your app. Otherwise, If you just want to give your app very quick makeover, you can also use the drop-in API.